You've worked through many problems. A lot of them. Maybe 100. Maybe 300. Maybe even more. But then a new interview question shows up, and your mind goes blank. That is the trap of random grinding. You remember solutions, but you do not recognize patterns fast enough under pressure. This video is different. This is PatternMastery 100 interview questions, organized around the patterns phone companies keep reusing. And every solution follows one system. Basics. Breakdown. Assess. Structure. Implement. Check. All solutions will be implemented using JavaScript. So do not watch this like entertainment. Watch it like training. Pause. Think first. Find the pattern. Then compare your thinking. By the end of this session, you will not just know more problems. You will start seeing problems differently. What if your map detecting skills decided whether you got the job? Number of islands is a PatternMastery 100 must-solve, and a recurring favorite at Google, Meta, and Amazon for grid DFS/BFS mastery. Over 30% of candidates get lost handling visited cells or edge cases. If you can handle this, you'll be ready for any connected component problem in an interview. Let's solve number of islands using the basic method, breaking down the problem step by step, so you can handle any matrix traversal with confidence. Given a 2D grid of ones, land, and zeros, water, count the number of islands, groups of horizontally or vertically connected land. An island is surrounded by water and is formed by connecting adjacent lands. 2D grid of characters 1, land, and 0, water, integer, total number of islands. Think about processing satellite images to count disconnected land masses, or identifying clusters in a social network or a game map. Interviewers might ask, how would you efficiently find all clusters or groups in a connectivity map? What's tricky? You must explore all connected ones for each island and ensure each cell is counted only once. Need to avoid double counting or missing isolated cells. Both DFS, recursion or stack, and BFS, queue, work, but must mark cells as visited. Loop through every cell in the grid. When you find a 1, it's a new island. Increment your count. Use DFS, or BFS, to mark all connected ones as visited, for example, change to 0 or mark in a visited set. Repeat until all cells are processed. Let's clarify. For each new one, you flood fill the island, ensuring every connected cell is covered before moving on. 4 directions per cell. Up, down, left, right, no diagonals. Edge cases. Empty grid, return 0. One giant island, should count as 1. Many tiny islands, single cells, count each. Initialize island count to 0. Loop through all grid cells. If cell is 1, run DFS/BFS from this cell to mark all connected ones. Increment island count, for DFS/BFS. For each cell, if in bounds and 1, mark as visited, 0 or visited set. Recurse or queue all 4 directions. Return island count. Let's try to implement it using solution 1. Time complexity, OMN. The concept discussion. We're counting how many separate islands exist in the grid, where 1 means land and 0 means water. The strategy is, whenever we find a land cell that hasn't been visited, we've discovered a brand new island, so we increase the count. Then we run DFS to flood fill that entire island, meaning we walk outward in 4 directions and turn all connected land cells into water, 0, so we don't count the same island twice. Repeat this across the whole grid, and the final count is the number of islands. This function scans the whole grid. Every time it finds fresh land, it counts 1 island and uses DFS to erase that island from the grid so it won't be counted again. First we handle the edge case. If the grid doesn't exist or is empty, there can't be any islands. Then we store the grid size and set up a count variable to track how many separate islands we find. This DFS is the island eraser. It only continues if the cell is inside the grid and is land 1. Once it's valid land, we immediately flip it to 0 to mark it as visited, like syncing that piece of land. Then we expand in 4 directions to sync any land connected to it. By the time DFS finishes, the entire connected island has been wiped out. Now we sweep through every cell. If we see one, that means we've found land that hasn't been visited yet, so it must be the start of a brand new island. We increment count, then call DFS to sync the whole island in one go. That prevents double counting when we keep scanning. After the grid is fully scanned and every discovered island has been sunk, count holds the number of islands, so we return it. And that's how this algorithm works. It first checks the grid and sets up the dimensions plus a counter, then it scans for new land cells and uses DFS to sync each full connected island so it's counted exactly once. Efficient, simple, and elegant. Let's test our function using this grid input. Each 1 represents land, each 0 represents water, and an island is formed by land connected up, down, left, or right. Now we scan the grid cell by cell. The moment we find a 1, that means we just discovered a new island, so we increase our island count by 1. Right away at the top left area, we hit land, and we run DFS to flood fill that entire connected landmass. DFS marks every connected one as 0, so we don't count the same island twice. In this test case, all the land cells are connected together as one big chunk. Even though there are a couple of zeros inside the shape, there's still a continuous path through adjacent land that keeps it all part of the same island. So after DFS finishes, there are no other ones left in the grid to start a second island count. And that's exactly what our program outputs. 1. That matches the expected result because the grid contains one connected land region, so there's only one island. So, our implementation is correct. The algorithm successfully counts islands by scanning once and using DFS to mark visited land, efficient and accurate. Let's try to implement it using solution 2. Time complexity. OMN. The concept discussion. This BFS approach still counts islands the same way. Scan the grid, and whenever we find a 1 that hasn't been visited, that's a brand new island. The difference is how we wipe out that island. Instead of DFS diving deep, BFS uses a queue to expand outward level by level. We put the first land cell into the queue, then repeatedly pull a cell out and add its neighboring land cells. Every land cell we touch gets flipped to 0 so we never count it twice. When the queue empties, that entire island has been fully explored and removed. This function scans the grid. When it finds land, it counts one island and uses BFS to turn all connected land into water so that island can't be counted again. First we handle the empty grid case, then store MN for boundaries. We set up count to track how many islands we find. And we prepare DIRs, which represents the 4 directions we're allowed to move: up, down, left, and right. This double loop is the island detector. The moment we see a 1, we found the start of a fresh island, so we increment count. Right away, we mark that cell as 0 to claim it as visited. Then we start a BFS from it using a queue. The goal of that BFS is to find every land cell connected to this starting point and sync it. Here's the BFS engine. We keep pulling land cells from the queue and checking their 4 neighbors. If a neighbor is valid and still 1, it belongs to the same island, so we immediately flip it to 0 and add it to the queue. That flip first, then push move is important. It prevents the same cell from being added multiple times, and it guarantees each land cell is processed only once. Once the scan is done, every island has been counted exactly once, and the grid has been updated so no island can be double counted. So we return count. And that's how this algorithm works. It first sets up the grid boundaries, a direction list, and an island counter. Then it scans for fresh land and uses BFS with a queue to sync every connected land cell so each island is counted once. Efficient, simple, and elegant. Let's test our function using this grid. Each 1 is land and each 0 is water, and islands are land cells connected up, down, left, or right. We scan every cell. When we find a 1, that's a brand new island, so we increment count. Then we immediately run a BFS flood fill starting from that cell using a queue. As we pop cells from the queue, we look in the 4 directions. Any neighboring one is part of the same island. We mark it as 0 and push it into the queue. That way, the entire island gets erased so it won't be counted again later. In this input, we end up finding 3 separate land groups. One big block in the top left, that's island number 1. A single land cell in the middle, island number 2. And a connected pair at the bottom right, island number 3. And that's exactly what our program outputs, 3, matching the expected result. So the output makes perfect sense because there are 3 distinct land clusters that aren't connected to each other. So, our implementation is correct. The algorithm successfully counts islands by scanning the grid and using BFS to mark each discovered island, efficient and accurate. Alright, quick recap to wrap up number of islands. Conceptually, we're given a grid of land and water, where an island is a group of connected land cells, only in the up, down, left, right directions. The goal is to count how many separate land clusters exist, basically like grouping regions inside a matrix. The big challenge here is avoiding double counting the same island. As soon as we discover a land cell, we can't treat nearby land as separate islands. We have to fully explore that entire connected region. That's why DFS or BFS both work perfectly here, using the classic flood fill pattern. And once a cell is marked visited, it should never be processed again. The plan is simple and repeatable. Scan every cell in the grid. If we see land, that means we found a new island, so we increment our counter. Then we flood fill outward from that cell to mark the entire island as visited, so we don't count it again later. We created a DFS or BFS helper, added boundary checks, skipped water cells, and immediately marked land as visited, either with a visited tracker or by flipping it so it won't be revisited. The code executed on LeetCode with no errors. We confirmed there were no overlaps or double counting. It worked on empty grids and dense land, handled separated clusters correctly, and all test cases passed. The main takeaway is that scan plus flood fill is the core grid traversal pattern. One island equals one full traversal starting from a land cell, and once you master that, a lot of matrix and graph style problems become routine. Clone graph. If you want to ace technical interviews at FONG and beyond, clone graph is a classic you must master. This PatternMastery 100 essential tests whether you truly understand recursion, graph traversal, and deep copying data structures. Did you know that a significant portion of candidates lose points here by shallow copying nodes, missing cycles, or failing to preserve graph structure? By getting this one right, you'll stand out in any interview and be ready for a whole family of graph problems. Here's the breakdown. You're given a node from a connected undirected graph, where each node contains a value and a list of neighbors. Your job? Return a deep clone of the graph, a new set of nodes, with the same structure and connections as the original, but no shared nodes. You can't just return the same nodes or rewire incorrectly. Cycles and shared neighbors make this tricky, so you need to carefully manage which nodes you've already cloned. Let's assess the challenges. Graphs can have cycles, so a naive recursive or iterative copy may loop forever. Nodes might be shared among neighbors. If you clone each node multiple times, the structure gets corrupted. We need a way to remember which nodes we've already cloned, so we can reuse the correct references. Use a hash map, dictionary, to track each original node and its corresponding clone. Traverse the graph, BFS or DFS. For each node, if it hasn't been cloned, make a new node and put it in the map. Then, recursively/iteratively clone all its neighbors. Here's our plan. Edge case. If the input node is none, return none. Create a map, old to new equals, to track original to clone nodes. Define a helper, DFS or BFS. If a node is already in the map, return its clone. Otherwise, clone the node, add it to the map, and recursively clone all neighbors. Return the clone for the input node. Let's try to implement it using solution 1. Time complexity is O(n) plus m. Space complexity is O(n). This solution uses DFS recursion to copy a graph. The tricky part about graphs is they can have cycles. That means you can come back to a node you have already visited. So the key strategy is to keep a map that links each original node to its cloned copy. When we first encounter a node, we create its clone and store it in the map right away. Then we recursively clone its neighbors and attach those cloned neighbors to the clone's neighbor list. If we ever see the same original node again, we do not clone it again. We reuse the existing copy from the map. That prevents infinite loops, and it guarantees every node is cloned exactly once. Before we start, we assume the graph uses a node structure like this. Each node has a value, and each node has a list of neighbor nodes it connects to. When we clone the graph, we create brand new node objects with the same values, and we rebuild the same neighbor relationships. But we do not point to the original nodes. First, we handle the simplest situation. If the input node does not exist, there is no graph to copy. So we return null immediately. Next, we create a map called cloned. This is the heart of the solution. It remembers which original nodes have already been copied. So we can safely handle cycles and shared neighbors without duplicating nodes. Now we define a DFS helper. The first thing it does is check the map. If this node was already cloned earlier, we immediately return the saved copy. This single check is what stops cycles from causing infinite recursion. If this node has not been cloned yet, we create a new node with the same value. Then we store it in the map right away. We store it before cloning neighbors. That is important because neighbors might point back to this node, and we want that lookup to work immediately. Next, we walk through the current node's neighbors. For each neighbor, we recursively get its cloned version. Then we push that clone neighbor into the clone node's neighbors list. This builds the same connections as the original graph, but it uses cloned nodes. Once all neighbor links are attached, we return the cloned node. That returned clone becomes the neighbor reference for other nodes higher up in the recursion. Finally, we start the DFS from the given starting node. And the returned clone is the entry point to the fully copied graph. And that's how this algorithm works. It first checks for an empty graph and sets up a map to remember clone nodes. Then it runs DFS to create each node once and recursively wire up clone neighbors while reusing clones from the map to handle cycles. Efficient, simple, and elegant. Test case check. Clone graph using DFS. Let's test our function using this input. 2, 4, 1, 3. 2, 4, 1, 3. These lists represent the neighbors of each node in the graph. For example, node 1 connects to nodes 2 and 4, node 2 connects to nodes 1 and 3, and so on. Here's why the solution works. We perform a DFS traversal of the graph. Whenever we encounter a node, we create a copy of it and store the mapping in a dictionary. Then we recursively clone each of its neighbors. If we revisit a node we've already cloned, we simply return the existing copy, preventing infinite loops in cyclic graphs. And that's exactly what our program outputs. 2, 4, 1, 3. 2, 4, 1, 3. It perfectly matches the expected clone structure, confirming that the graph has been duplicated accurately. Wrap up. So, our implementation is correct. The algorithm successfully creates a full deep copy of the graph using DFS and a hash map, efficient, accurate, and reliable. Let's try to implement it using solution 2. Time complexity is O(n) plus m. Space complexity is O(n). We are cloning a graph using BFS, which stands for breadth first search, with a map to keep track of what we have already copied. The key idea is simple. Every time we discover a node, we create its clone once. Then we store the original node and its clone together in a map. As we explore edges, meaning neighbors, we connect the clone nodes together in the same pattern as the original graph. This prevents infinite loops in cyclic graphs, and it avoids cloning the same node multiple times. Before we start, we assume the graph uses a node structure like this. Each node has a value, and each node has a list of neighbor nodes it connects to. When we clone the graph, we create brand new node objects with the same values, and we rebuild the same neighbor relationships. But we do not point to the original nodes. This function takes one starting node. It tries to copy the entire connected graph from that starting point. The first quick check is important. If the input is empty, there is nothing to clone. So we return null immediately. Now we set up our core tools. The map called cloned is our memory. It links each original node to its cloned copy. We start by cloning the first node right away. Then we prepare a BFS queue to explore the graph level by level. Instead of removing from the front of the queue, which can be slow, we use a head pointer. That head pointer moves forward through the array. This loop drives the exploration. As long as there are nodes waiting in the queue, we take the next one. That becomes the current node we are expanding. BFS ensures we eventually visit every reachable node from the starting point. This is the heart of the cloning process. For each neighbor of the current node, we first check if we have already cloned that neighbor. If we have not, we create its clone. We store it in the map. And we add the original neighbor to the queue so we can explore its neighbors later. Either way, we then connect the cloned current node to the cloned neighbor. We do that by pushing the cloned neighbor into the cloned current node's neighbors list. So we are doing two things at once. We make sure every node is cloned exactly once. And we recreate every connection in the cloned graph. Once BFS finishes, we have cloned every reachable node. And we have rebuilt all the neighbor links. The final answer is the clone of the starting node. From that node, you can access the entire cloned graph structure. And that's how this algorithm works. It first sets up a clone map and a BFS queue starting from the given node, then explores the graph while cloning nodes once and reconnecting their neighbor links in the copied graph. Efficient, simple, and elegant. Test case check. Clone graph using BFS. Let's test our function using this input. This represents a graph with just one node, and that node has no neighbors. In other words, it's a single isolated node with an empty adjacency list. Here's why the solution works. We start by cloning the initial node and placing it in a BFS queue. Then we process the queue level by level. For each node, we look at all its neighbors. If a neighbor hasn't been cloned yet, we create it and push it into the queue. Then we connect the cloned node to its cloned neighbors. And that's exactly what our program outputs. This confirms that the BFS cloning logic works correctly even for the smallest possible graph. Wrap up. So, our implementation is correct. The algorithm successfully clones the graph, even in minimal cases, using a clean BFS traversal and a mapping of original to cloned nodes. Efficient, accurate, and reliable. Clone graph. Let's do a recap. So, we just tackled one of the trickiest graph problems in interviews, clone graph. It's a true test of your understanding of recursion, traversal, and deep copying complex structures. Once you master this, you'll be ready for an entire class of graph and network-related problems that interviewers love to ask. Breakdown recap. At its core, this problem asks us to create a deep copy of a connected graph, meaning we build entirely new nodes that mirror the original connections perfectly. The catch? Graphs can contain cycles, so careless recursion can loop forever or duplicate nodes. Assess recap. We compared possible approaches. Brute force copying fails because of repeated nodes, while using recursion with memory tracking works beautifully. The key insight was to use a hash map to store already cloned nodes, so every original node maps to exactly one copy. This ensures no duplication and handles cycles cleanly. Structure recap. Our plan was simple yet powerful. Handle the base case when the graph is empty. Use DFS to explore and clone each node. Store each clone in the map, then recursively connect its neighbors. That's it. A clean, recursive structure that mirrors the graph one layer at a time. Implement recap. We implemented the DFS-based solution, ran it through LeetCode, and it executed flawlessly. No infinite loops, no shallow copies, and no structural mismatches. The cloned graph preserved every connection while remaining fully independent of the original. Check recap. After running multiple test cases, the cloned adjacency lists matched perfectly. All cycles, neighbor relationships, and node values aligned as expected. All test cases passed with optimal performance. Closing insight. The big takeaway? Clone graph is all about thinking recursively, breaking complex structures into smaller, familiar problems. Once you grasp how to track references and prevent duplication, you unlock the mindset needed for tackling any advanced graph or tree problem in technical interviews.
You thought your job was safe until you got that email. Now you're back on LeetCode remembering you forgot everything about trees and graphs. Interviewer says, solve this in O of n. Your brain says, 404, solution not found. Don't be that person. Subscribe to PatternMastery.com and master the coding patterns FANG companies actually test.
Can you spot cycles before they wreck a project? Course Schedule is a Pattern Mastery 100 classic. Frequently asked at Google, Amazon, and Meta for its blend of graph, topological sort, and cycle detection. Over 40% of candidates either miss edge cases or get tangled in the graph logic. If you master this, you'll ace any dependency or order check problem in interviews. Let's break down Course Schedule with the basic method, a stepwise approach that builds deep understanding for any cycle or topological ordering question. Let's break down the problem. You're given num courses, number of courses, and a list of prerequisite pairs. Can you finish all courses? Each pair, A, B, means, to take course A, you must first finish course B. The courses form a directed graph. Your task is to check if there's any cycle, which would make it impossible to finish all courses. Integer num courses list of prerequisite pairs. Boolean. True if all courses can be finished, false otherwise. Think of project tasks or college courses, where some steps must happen before others. Interviewers might ask, how would you check for circular dependencies in a build system or workflow manager? What's tricky? You need to detect cycles in a directed graph, classic topological sort. Multiple valid orderings may exist. Must efficiently track visited nodes and recursion stack. Build an adjacency list to represent course dependencies. Use DFS to detect cycles. Mark each node as not visited, 0 visiting, 1 visited, 2 for each node. If already fully visited, skip. If visiting, and you re-enter it, you found a cycle. Recursively DFS all neighbors. If any cycle is found, return false. Otherwise, return true. Let's clarify. The recursion stack, visiting, is key. It tracks the current path. Alternatively, BFS, Kahn's algorithm, within degrees works as well, but DFS is easier to explain in interviews. Edge cases. No prerequisites. Always return true. Disconnected graph, some courses with no dependencies. Multiple cycles. Build adjacency list from prerequisites. Initialize state array for all nodes. For each node, DFS. If node is visiting, return false, cycle. If node is visited, skip. Mark as visiting. DFS all neighbors. After neighbors, mark as visited. If no cycles, return true. Let's try to implement it using solution 1. Time complexity. Num courses plus prerequisites. Length. The concept discussion. We're solving course schedule by modeling courses as a directed graph. An arrow goes from a prerequisite to the course it unlocks. Then we run DFS, depth first search, to detect cycles. A cycle means this course depends on itself indirectly, so it's impossible to finish. To catch cycles, we track each course in one of 3 states: not visited yet, currently in the DFS path, or fully completed. If we ever re-enter a course that's currently in the path, that's a cycle. Alright, this CanFinish function is the full solution. It takes the number of courses and a list of prerequisite pairs, and its job is simple. Return true if we can complete everything, or false if there's a dependency loop that makes it impossible. First, we build a graph. Think of graph X as, what courses become available after I finish course X? So for each pair, course, prereq, we add an arrow from prereq to course. That way, from a prerequisite, we can quickly see what it unlocks next. Next, we create a visited array to track progress for every course. We use 3 states. 0 means we haven't touched it yet. 1 means we're currently exploring it in the DFS path. 2 means we've fully explored it and confirmed it's safe. This is the key idea that lets us detect cycles reliably. Now we define the DFS helper. This function tries to confirm, starting from this course, can I follow the dependency paths without getting stuck in a loop? Here's the big logic. If we hit a course marked visiting, state 1, we've looped back into our current path, that's a cycle, so we return false. If we hit a course already marked visited, state 2, we already proved it's safe earlier, so we can skip the work and return true. Otherwise, we mark the course as visiting, explore everything it leads to, and if all paths are safe, we mark it visited and return true. Finally, we run DFS starting from every course. Why do we do that? Because the graph might have multiple disconnected parts, like separate groups of courses that don't relate to each other. If any DFS call finds a cycle, we immediately return false. But if every course checks out clean, then no cycles exist anywhere, and we return true. And that's the full picture. Build the dependency graph, track states, use DFS to detect cycles, and verify every course can be processed safely. And that's how this algorithm works. It first builds the dependency graph and initializes the visit states, then runs DFS with cycle detection across all courses to confirm no circular prerequisites exist. Efficient, simple, and elegant. Alright, let's test our function with this input. Num courses equals 2 and prerequisites equals 1, 0. This means we have 2 courses, 0 and 1, and the pair, 1, 0, tells us, to take course 1, you must first complete course 0. Now we build a directed graph from prerequisites. So we create an edge 0, 1, because course 0 unlocks course 1. Then we run DFS to check for cycles. If we ever revisit a node that's currently being explored, that would mean a loop, and then finishing all courses would be impossible. In this case, starting from course 0, we go to course 1, and course 1 doesn't point back to anything. So we successfully finish exploring without detecting a cycle, which means the course plan is valid. And that's exactly what the program returns. True. That makes sense because you can simply take course 0 first, then course 1, and you're done. The code passes the test case. So, our implementation is correct. The algorithm successfully detects whether a cycle exists using DFS, efficient and accurate. Let's try to implement it using solution 2. Time complexity. Num courses plus prerequisites. Length. The concept discussion. This approach uses topological sort, Kahn's algorithm. The idea is to count how many prerequisites each course still needs before it can be taken. That's the in-degree. Any course with in-degree 0 is ready to go right now, so we put it into a queue. Then we repeatedly take a ready course, complete it, and reduce the in-degree of the courses it unlocks. If we can process all courses this way, there's no cycle and we can finish. If we get stuck early, some courses never reach in-degree 0. That means there's a loop somewhere. This CanFinish function solves the problem by trying to take courses in a valid order. If we can keep picking courses that have no remaining prerequisites until we've taken them all, we return true. If not, we return false. First, we build 2 key tools. The graph tells us, after finishing this course, what courses does it unlock? The in-degree array tells us, how many prerequisites does this course still need? Every time we see course, prereq, we add course to the list unlocked by prereq, and we also increase in-degree course, because that course has one more required step before it can be taken. Next, we find all courses that are immediately available, meaning they have 0 prerequisites. Those are our starting points, so we push them into a queue. You can think of this queue as the list of ready-to-take courses. Now comes the core workflow. While we still have ready courses in the queue, we take one out, which represents completing that course. We increase count to track how many courses we've successfully completed. Then we look at the courses it unlocks. For each unlocked course, we reduce its in-degree because one prerequisite has just been satisfied. If any unlocked course reaches in-degree 0, it becomes ready, so we push it into the queue. That's how availability spreads through the graph. At the end, we check if we completed all courses. If count equals num courses, we successfully found an order to take everything, so true. If count is smaller, it means some courses never became available, usually because they're trapped in a cycle, so false. And that's how this algorithm works. It first builds the graph and in-degree counts while collecting all starting courses with 0 prerequisites, then repeatedly processes ready courses and reduces in-degrees to unlock new courses until it either completes all of them or gets stuck. Efficient, simple, and elegant. Okay, up next, let's run a real test on this one. We've got num courses equals 2 and prerequisites equals 1, 0, 0, 1. That means there are 2 courses, 0 and 1. But here's the problem. Course 1 depends on course 0, and course 0 depends on course 1. With Kahn's algorithm, we track in-degree, which is basically how many prerequisites each course still needs before it can be taken. From the input, course 1 has prereq 0, so in-degree 1 becomes 1. Course 0 has prereq 1, so in-degree 0 becomes 1. So now in-degree looks like in-degree 0 equals 1. In-degree 1 equals 1. Next, we try to add courses with in-degree 0 into the queue, meaning courses we can start immediately. But in this case, none of them have in-degree 0. Both courses are waiting on each other. So the queue starts empty. The loop never runs, and count stays 0, meaning we couldn't complete any course at all. And that's why the function returns false, which matches the expected output. The result makes perfect sense because this prerequisite setup forms a cycle, so there's no valid order to finish both courses. So, our implementation is correct. The algorithm successfully uses in-degrees and a queue to detect cycles, and when no starting course exists, it correctly concludes the schedule can't be completed. Alright, quick recap to wrap up course schedule. At its core, this problem turns courses and prerequisites into a directed graph. Each prerequisite pair basically says, you can only take course A after course B. So the real question becomes simple. Can we finish everything, or does the graph contain a cycle? Because if there's a cycle, that means the requirements loop forever, and finishing all courses is impossible. From there, we focused on the key insight. We only fail when dependencies loop back. So cycle detection is the entire problem. We also noted there are 2 solid ways to do that. DFS with state marking or BFS using in-degrees, and we went with DFS because it's a direct and fast way to spot cycles. The plan was straightforward. Build an adjacency list from the prerequisites, then track each course using 3 states, unvisited, visiting, and visited. We run DFS from every course to handle disconnected parts of the graph. And the moment DFS reaches a node that's already marked visiting, we've detected a cycle. After setting up the graph and the state tracking, we ran the solution, and it executed cleanly on LeetCode with no errors. We also validated the logic through the LeetCode run, confirmed the behavior matched expectations, handled edge cases correctly, and all test cases passed. The big takeaway is that this problem is really a topological sort mindset. Schedules break when cycles exist. Once you can reliably detect cycles, you can reason about a lot of real systems, and a ton of graph interview problems start feeling way more manageable.
Quiet room. Shared screen. One question. No clue. That silence is expensive. PatternMastery.com.
Ready to test your multi-source graph skills? Pacific Atlantic Waterflow is a PatternMastery 100 standout, and a frequent challenge at Google and Amazon for Grid DFS/BFS Mastery. More than 30% of candidates stumble on multi-source propagation or state tracking. Master this and you'll be ready for any two-way reachability problem in grids or graphs. Let's solve Pacific Atlantic Waterflow using the basic approach, a robust method for systematic, interview-ready solutions. Given an MXN grid of heights, return all coordinates where water can flow to both the Pacific and Atlantic Oceans. Water can flow from a cell to neighboring cells with equal or lower heights. The Pacific touches the left and top edges. The Atlantic touches the right and bottom edges. 2D grid of integers, heights list of coordinate pairs, row, col, where water can flow to both oceans. Think about rainwater flow on a terrain map. Where could water reach both rivers? Interviewers might ask, how would you find all meeting points in a network from multiple start sources? What's tricky? Water flows uphill in this reverse sense. We can visit a cell if it's equal/higher than the previous, simulating water flowing down from it. Need to find cells that can reach both oceans, not just one. Must avoid redundant searches, propagate from oceans inward, not from each cell out. For each ocean, mark all cells that can flow into it. Pacific, start from all top and left edge cells. Atlantic, start from all bottom and right edge cells. From each ocean border, use DFS, or BFS, to move to neighboring cells of equal or higher height, reverse water flow. Collect cells reachable by both DFS runs. The intersection is the answer. Let's clarify. 2 visited sets, one for Pacific, one for Atlantic. Each DFS only goes uphill, to equal or higher height. Final answer is the intersection of the 2 sets. Edge cases. Empty grid, return. Single row/column, all cells touch both oceans. Flat terrain, all cells can reach both. Initialize 2 visited sets for Pacific and Atlantic. For all Pacific border cells, top row, left call, DFS/BFS and mark all reachable. For all Atlantic border cells, bottom row, right call, DFS/BFS and mark all reachable. Result equals intersection of both visited sets. Let's try to implement it using solution 1. Time complexity, OMN. The concept discussion. We want all grid cells where water can flow to both the Pacific and Atlantic. Instead of starting from every cell and trying to reach the oceans, which is slow, we flip the thinking, we start DFS from the ocean borders inward. But we only move from a cell to a neighbor if the neighbor is higher or equal, because that means water from that higher neighbor could flow down to the current cell and eventually reach the ocean. We do this twice, once for the Pacific borders, once for the Atlantic borders. Any cell marked reachable in both searches is our answer. This function builds 2 reachability maps, one for the Pacific and one for the Atlantic, then finds the cells that can reach both. The trick is we explore from the oceans inward, marking which cells could eventually drain into each ocean. First we grab the grid size, then we create 2 same-sized Boolean grids, PAC and ATL. If PAC IJ is true, it means that cell can reach the Pacific. Same idea for ATL and the Atlantic. We're basically building 2 can water reach this ocean maps. This DFS marks cells as reachable for a given ocean. The important rule is the height check. We only move to a neighbor if it's higher or equal. Why? Because we're exploring in reverse. If the neighbor is higher, water from that neighbor could flow down into the current cell, and since the current cell can reach the ocean, the neighbor can too. So we're basically expanding the ocean's influence uphill across the map. Now we run DFS from every border cell that touches the Pacific. That's the top row and the left column. Each DFS spreads inward, marking every cell that could eventually drain into the Pacific. Same idea for the Atlantic, but its borders are the bottom row and the right column. After this, ATL tells us every cell that can drain into the Atlantic. Finally, we scan the whole grid and collect the cells that are marked true in both maps. Those are the cells where water can reach the Pacific and the Atlantic, so they go straight into our result. And that's how this algorithm works. It first sets up 2 ocean reachability grids and a DFS that expands from borders uphill, then it floods inward from both oceans and collects the cells marked reachable by both. Efficient, simple, and elegant. Let's test our function using this input grid. Each number represents the height of a cell in the map, and water can flow from a cell to its neighbors if it can move downhill or flat. Our goal is to find all coordinates where water can flow to both oceans, the Pacific, top and left edges, and the Atlantic, bottom and right edges. Instead of simulating water flowing out from every cell, the solution does something smarter. We run DFS from the ocean borders inward. First, we start DFS from the top row and left column to mark everything that can reach the Pacific. Then we start DFS from the bottom row and right column to mark everything that can reach the Atlantic. And here's the key rule in DFS. We only move from a cell to a neighbor if the neighbor's height is greater than or equal to the current cell. That reversal works because we're walking the paths water could have taken in reverse. After both DFS runs, any cell marked reachable in both PAC and ATL is a valid answer, meaning water from that cell has a route to both sides. And that's exactly what we get. 0,4, 1,3, 1,4, 2,2, 3,0, 3,1, 4,0. These positions make sense because each one sits on a path of heights that can connect back to the Pacific edges, and also connect back to the Atlantic edges, so water has a valid downhill route to both oceans. So, our implementation is correct. The algorithm successfully identifies all cells that can reach both oceans by doing 2 boundary DFS passes, efficient and accurate. Let's try to implement it using solution 2. Time complexity, OMN, the concept discussion. This time we use BFS, breadth first search, starting from the ocean borders, just like the DFS idea, but instead of diving deep, we expand layer by layer using queues. We still reverse the water flow. From the ocean edges, we only move into neighbors that are higher or equal in height. because that means water from those neighbors could flow down to the ocean. We run BFS twice, once from the Pacific borders and once from the Atlantic borders. Any cell reachable in both BFS runs is part of the answer. This function creates two BFS waves, one starting from the Pacific edges and one from the Atlantic edges. Each wave marks which cells can eventually flow to that ocean. Then we intersect those results to get the final coordinates. First we grab the grid dimensions. Then we create two Boolean grids, PAC and ATL, to remember which cells are reachable for each ocean. And since this is BFS, we also create two queues, one queue to expand from the Pacific borders, and another to expand from the Atlantic borders. Now we load the queues with the starting points, the cells touching each ocean. Pacific touches the top row and left column, so we push those into QPAC and mark them reachable. Atlantic touches the bottom row and right column, so we push those into QATL and mark them reachable. This is like placing two sets of starting wave sources on the edges. To move around the grid, we use four directions: down, up, right, and left. That keeps the BFS consistent and easy to manage. This loop runs BFS from the Pacific borders. Each time we pull a cell from the queue, we try to push its neighbors. But notice the key rule: we only move into a neighbor if it's higher or equal. That's because we're reversing the flow. If the neighbor is higher, water from that neighbor could flow down into the current cell, and since the current cell can reach the Pacific, the neighbor can too. So this BFS marks every cell that can eventually drain into the Pacific. Now we repeat the same BFS logic for the Atlantic. The only difference is we're expanding from the Atlantic border cells we seeded earlier. By the end of this loop, ATL tells us every cell that can drain into the Atlantic. Finally, we scan the whole grid and collect cells that are reachable in both maps. If a cell is true in PAC and ATL, it means water from there can reach both oceans, so we add its coordinates to the answer. And that's how this algorithm works. It first seeds two BFS queues from the Pacific and Atlantic borders and prepares reachability maps, then it expands inward uphill to mark all cells that can drain into each ocean and finally intersects those maps to collect the cells that reach both. Efficient, simple, and elegant. Let's test our function using this input. 1. This is a 1x1 grid, so there's only a single cell at coordinate 0, 0, and its height is 1. Just like before, we're figuring out which cells can reach the Pacific and which can reach the Atlantic, but this version uses BFS with two queues. For the Pacific, we start from the top row and left column. In a 1x1 grid, that's immediately the cell, 0, 0, so it's marked reachable. For the Atlantic, we start from the bottom row and right column. In a 1x1 grid, that's also the same cell, 0, 0, so it gets marked reachable there too. And since there are no other cells to expand to, both BFS loops finish right away, but we've already confirmed that 0, 0 reaches both oceans. And that's exactly what our program outputs, 0, 0, which matches the expected answer. That result makes perfect sense because the single cell touches every border at once, so water can flow to both oceans from it. So, our implementation is correct. The algorithm successfully finds all cells that can reach both oceans by running two boundary-based BFS passes, efficient and accurate. Alright, quick recap to wrap up Pacific-Atlantic water flow. Conceptually, we're working with a grid of heights, where water can move from a cell to its neighbors only if the neighbor is equal or lower. The goal is to find all cells where water can eventually reach both oceans, the Pacific on the top and left edges, and the Atlantic on the bottom and right edges. The core insight was not to simulate water from every cell outward. That gets expensive fast. Instead, we reverse the flow. Start from the oceans and move inward. In that reversed view, we only travel to cells that are equal or higher, since that represents valid downhill flow in the original direction. We run this process twice, once per ocean, then take the intersection of the results. The plan was clean. Create two visited maps, one for Pacific reachable and one for Atlantic reachable. Then traverse inward starting from the Pacific borders, top row and left column, and separately from the Atlantic borders, bottom row and right column. The final answer is simply the cells marked reachable in both maps. We set up a DFS or BFS helper that expands uphill in the reverse direction, launched traversals from each ocean's border cells, marked visited positions correctly, and the solution ran cleanly on LeetCode with no errors. We verified the reachability logic across different terrains, confirmed the intersection produced the correct set of coordinates with no missing or extra cells, and all test cases passed. The big takeaway is that reverse thinking is the trick. Start from the goal and work backward. Two boundary traversals beat brute force almost every time, And once you master this pattern, a lot of grid graph problems get way easier.
Breakdown. Assess. Structure. Implement. Check. 5 steps. Way less panic. PatternMastery.com.
Have you ever tried to find someone's longest streak of daily activity from a messy log? That's exactly what LeetCode's longest consecutive sequence asks. One of the PatternMastery 100 essentials, and a problem that stumped even experienced engineers at companies like Google, Netflix, and Facebook. In interviews, getting this ON trick is a game changer. Let's apply the basic approach. A strategy broader than STAR because it's designed for breaking down technical challenges and system designs, not just behavioral questions. We're given an unsorted array of integers and asked, what's the length of the longest run of numbers that appear consecutively, regardless of order? For example, 100, 4, 200, 1, 3, 2, yields, 1, 2, 3, 4 length, 4. Edge cases, handle empty arrays, negatives, duplicates, anything the interviewer throws at you. Suppose you're designing a fitness app. You get a list of dates a user logged workouts. How do you instantly show their longest streak, no matter the order the logs came in? This problem is exactly that challenge. If you sort and count, you get ON log n. Good, but not great. The best solution uses a hash set for O1 lookups and only starts streaks at the true beginning of each run. Num, 1 isn't present. That way, you never double count or waste work, making the algorithm ON. Add all numbers to a set so we can check for any number in constant time. For each number, only start counting a sequence if there's no smaller number in the set. Count up from each streak start, tracking how long the run goes. Update the max streak found along the way. Return the result. Let's walk through the logic as if we're coding together. Let's try to implement it using solution 1. Time complexity. ON log n. The concept discussion. The goal is to find the length of the longest run of numbers that go up by 1 each time, like 4, 5, 6, 7. This solution does it in 2 big moves. Remove duplicates, because repeated numbers can mess up counting a clean consecutive run. Sort the numbers, so any consecutive sequence will appear next to each other. Then we do a simple linear scan. Keep a current streak counter while numbers stay consecutive, and whenever the streak breaks, we update longest and reset current back to 1. This function cleans the input, sorts it, then walks through once to measure the longest consecutive streak. First, we handle the simplest case. If there are no numbers, there can't be any sequence, so we return 0 right away. Next, we remove duplicates using a set, then turn it back into an array and sort it. This is super important because once the numbers are sorted, any consecutive sequence, like 10, 11, 12, will appear right next to each other, making it easy to count. Now we set up 2 counters. Current tracks the length of the streak we're currently in. Longest remembers the best streak we've seen so far. We start both at 1 because a single number is always a consecutive sequence of length 1. Here we walk through the sorted array from left to right. If the current number is exactly 1 more than the previous, we're still consecutive, so we grow current. If it's not, the streak is broken, so we compare current with longest, update longest if needed, and reset current back to 1 to start a fresh streak. Finally, we return the best streak length. We take math.max longest, current, because the longest streak might end at the very last element. So we do one last comparison to be safe. And that's how this algorithm works. It first removes duplicates and sorts the numbers to line up any consecutive runs, then it scans once to expand streaks when numbers increase by 1 and resets when the streak breaks while tracking the best length. Efficient, simple, and elegant. Let's test our function using this input array. 100, 4, 200, 1, 3, 2. These numbers are unsorted, and we're trying to find the longest streak of consecutive integers that appear in the array. Since this solution uses sorting plus a linear scan, the first thing it does is remove duplicates with a set, then it sorts the numbers. So the array effectively becomes 1, 2, 3, 4, 100, 200. Now we scan from left to right. 1 to 2 is consecutive streak becomes 2. 2 to 3 is consecutive streak becomes 3. 3 to 4 is consecutive streak becomes 4. Then 4 to 100 breaks the chain. So we lock in that streak length of 4. Nothing later beats that, because 100 and 200 are isolated. And that's exactly what our program outputs, 4. That output makes total sense because the longest consecutive sequence here is 1, 2, 3, 4, which contains 4 numbers. So, our implementation is correct. The algorithm successfully finds the longest consecutive run by sorting once and doing a single clean pass, efficient and accurate. Let's try to implement it using solution 2. Time complexity, ON. The concept discussion. This solution avoids sorting by using a hash set for fast lookups. The key trick is, we only start counting a sequence when we're at the beginning of that sequence. How do we know we're at the beginning? If num1 is not in the set, then num must be the first number in its consecutive run. From there, we keep checking num plus 1, num plus 2, and so on, growing the streak until it stops. We track the longest streak length across all starts. This function builds a set for fast membership checks, finds sequence starting points, expands each sequence forward, and keeps the best length. First we put all numbers into a set. This lets us ask, does this number exist? Really quickly. We also set longest to 0, because if the input is empty, the correct answer should stay 0. Now we loop through the set's unique numbers. Here's the big efficiency trick. We don't try to build a sequence from every number. Instead, we only start when num looks like the first number of a sequence. After checking all possible starting points, longest holds the length of the longest consecutive sequence, so we return it. And that's how this algorithm works. It first stores all numbers in a hash set for quick lookups, then it only starts counting from true sequence beginnings and expands forward to measure each run while tracking the maximum length. Efficient, simple, and elegant. Let's test our function using this input array. 0, 3, 7, 2, 5, 8, 4, 6, 0, 1. These numbers can be in any order, and we want the longest sequence of consecutive integers that appear in the array. This solution loads everything into a set, so lookups are fast, and duplicates don't matter, like the extra 0 here. Then we only start counting when we find a number that's the start of a sequence, meaning num1 is not in the set. In this input, 0 is a sequence start because -1 isn't in the set. From there, we walk forward. 0, 1, 2, 3, 4, 5, 6, 7, 8. That's a continuous chain of 9 numbers. Other numbers like 3, 4, 5, and so on don't start new scans, because they do have a previous number in the set, so we avoid repeated work. And that's exactly what our program outputs, 9, matching the expected result. That output makes perfect sense because the longest consecutive run is 0 through 8, and that sequence contains 9 elements. So, our implementation is correct. The algorithm efficiently finds the longest consecutive sequence by only expanding from true sequence starts, fast and accurate. Alright, quick recap to wrap up longest consecutive sequence. Here we're given a bunch of unsorted numbers, and the order doesn't matter at all. The goal is to find the length of the longest streak of consecutive integers hidden inside that disorder. And importantly, we're returning the streak length, not the actual sequence. We started with the obvious idea. Sorting would work, but it costs O(n) log n. The better insight is using a hash set for fast lookups. Then the key optimization is this. We only start counting when we're at a true beginning of a sequence. A number is a sequence start if its predecessor is missing, meaning num1 isn't in the set. The plan is clean. Put every number into a set. Then for each number, check if it begins a streak. If it does, expand forward, num plus 1, num plus 2, and so on, until the streak breaks. Keep track of the maximum streak length we ever see. We built the set once, skipped numbers that clearly have a predecessor, and only expanded from true starts to avoid repeated work. The solution ran cleanly on LeetCode with no errors. We validated across tricky cases, duplicates, negative numbers, scattered inputs, and it still works without sorting. It also behaves correctly on empty arrays and single-element inputs, and all test cases passed. The real trick isn't counting faster, it's starting fewer times. Hash set lookups plus start detection turns this into an O(n) solution. Master this pattern, and a lot of array problems start unlocking.
The interviewer smiled. Not because you were right, because they knew you were lost. Learn to spot the pattern before they spot the panic. PatternMastery.com.
Imagine you're decoding an alien language with only a list of sorted words. Can you reconstruct the whole alphabet? Alien Dictionary is a PatternMastery 100 Super Challenge. Regularly asked at Google, Meta, and Amazon to test your grasp of graph theory, topological sorting, and string manipulation. Over 40% of candidates either miss edge cases or get tangled in cycle detection. Master this, and you'll shine on advanced ordering problems. Let's break down Alien Dictionary using the basic method, giving you a foolproof plan for any graph-based string ordering challenge. Given a list of words sorted according to an unknown alphabet, return a string representing the alphabet's order. If no valid order exists, cycle, return. List of words, all lowercase letters, possibly with overlaps and missing letters, a string of characters, the alien alphabet order, or if invalid. Suppose you're designing a search tool for a new language, or analyzing a secret code with custom rules. An interviewer might ask, how would you deduce task dependencies from log order, or infer a dictionary structure from partial data? What's tricky? You need to infer order constraints between letters by comparing adjacent words. Must detect cycles. If two letters are required to come before each other, there's no valid order. Not all letters may be present in the input, and some may be missing from certain orderings. Build a graph. Each unique letter is a node. For every pair of adjacent words, find the first position where they differ. That's a precedence constraint. Edge. Topological sort. Apply Kahn's algorithm, BFS, or DFS to produce a valid order. Use an in-degree map to track how many incoming edges each node has. Add nodes with 0 in degree to the result. Decrease in degree as edges are used. Cycle detection. If at the end, you haven't used all letters, result is shorter than unique letters, there's a cycle. Let's clarify. If a word is a prefix of another but comes later, it's invalid, for example, ABC, AB. All letters in words must appear in the output. Edge cases. Empty word list. Return. Words with same prefix. Skip until the first difference. Cycle in constraints. Return. Initialize a graph, adjacency list, and in degree dictionary for all unique letters. Compare each pair of adjacent words. For each character, find the first mismatch. Add an edge from char 1 to char 2. Char 1 comes before char 2. If one word is a prefix of the other and is longer, return. Topological sort. Add all nodes with 0 in degree to a queue, while queue isn't empty. Pop from queue, append to result. Decrease in degree for neighbors. If in degree becomes 0, add to queue. If result length equals the number of unique letters, return as a string. Otherwise, return, cycle or invalid input. Let's try to implement it using solution 1. Time complexity, OV plus E. The concept discussion. We're given words already sorted in an alien language, and we need to figure out the letter order. The key idea is to build a graph of letter rules. If letter A must come before B, we add an edge of B. We discover these rules by comparing each adjacent pair of words and finding the first position where they differ. That first mismatch tells us the ordering rule. After we build all rules, we run topological sorting, Kahn's algorithm, to produce a valid letter order. If we detect an invalid case, like a longer word coming before its exact prefix, or we can't include all letters, cycle, we return an empty string. This function builds a letter graph from the word list, then uses topological sorting to return a valid character order, or an empty string if it's impossible. First, we gather every unique character that appears anywhere in the input. Even if a letter doesn't have any rules pointing to or from it, it still needs to show up in the final answer. We set up adjective as a graph that stores what each letter must come before. In degree to count how many rules are pointing into each letter, basically how many prerequisites that letter still has before it can be placed. Now we build the rules by looking at words 2 at a time, because the list is already sorted in alien order. We compare W1 and W2, and the first character position where they differ tells us the rule, W1J, must come before W2J. That's the only rule we need from that pair, so we stop comparing after that first mismatch. Now we start topological sorting. Any letter with in-degree 0 has no prerequisites, meaning it can safely appear next in the order. We push all such letters into a queue to begin processing. This loop builds the final character order. We repeatedly take a letter from the queue, add it to the output, and then remove its outgoing rules by decreasing the in-degree of its neighbors. If any neighbor drops to in-degree 0, it becomes ready, so it joins the queue. This continues until no more letters can be placed. At the end, we check if we successfully placed all characters. If yes, we join them into a string and return it. If not, it means a cycle or contradiction prevented some letters from ever reaching in-degree 0, so we return an empty string. And that's how this algorithm works. It first collects all letters and builds a dependency graph by comparing adjacent words for the first mismatch, then it topologically sorts the letters with a queue by repeatedly taking 0 in-degree characters and unlocking the next ones, until it either forms a full valid order, or detects an impossible cycle. Efficient, simple, and elegant. Let's test our function using this input list of words. WRT, WRF, ET, RFTT. These are words already sorted in an alien language, and our job is to figure out a valid character order that makes this sorting possible. First, the code collects every unique character it sees and sets up an in-degree map, how many prerequisites a letter has, and an adjacency list, which letters must come after another. Then we compare each pair of neighboring words to find the first character where they differ. That's where we learn a rule. Let's walk through the key comparisons. WRT versus WRF. First difference is T versus F, so TF. WRF versus first difference is W versus E, so WE. Versus ET. First difference is R versus T, so RT. ET versus RFTT. First difference is E versus R, so ER. So we've built a chain of dependencies that basically forces WERTF. After that, we run a BFS topological sort. Start with letters that have in-degree 0, no prerequisites. Pop them into the result. And decrease in-degrees of their neighbors. And the final output is WERT, exactly matching the expected answer. That output makes perfect sense because it satisfies every rule we discovered from the sorted word list. W comes before E before R before T, and T before F. So, our implementation is correct. The algorithm successfully reconstructs the alien alphabet using graph constraints and topological sorting, efficient and accurate. Let's try to implement it using solution 2. Time complexity, OV plus E. The concept discussion. This DFS-based solution still builds a graph of letter rules, but instead of using a Q-cons algorithm, it uses DFS topological sorting. We compare neighboring words to find the first differing character, and that gives us a must-come-before rule like a B. After building the graph, we run DFS across all characters. We track each character's visit state: unvisited, visiting, currently in the recursion path, and visited, fully done. If we ever revisit a visiting character, that means there's a cycle, so the order is impossible. Otherwise, we add characters to an output list after exploring their neighbors, then reverse at the end to get the correct order. This function creates a dependency graph between letters, then uses DFS with cycle detection to build a topological ordering, or returns an empty string if it's impossible. First, we collect every unique character that appears in the word list. That ensures our final answer includes letters even if they don't participate in any rule. Then we create an adjacency list entry for each character, basically a place to store what letters must come after this one. Next, we build the graph rules by walking through word pairs. Since the words are already sorted in alien order, we only need to find the first mismatch between each consecutive pair. That mismatch gives a direct ordering rule. The character from the first word must come before the character from the second word. Now we prepare for DFS. We track each character's state. 0 means unvisited. 1 means visiting, currently in the DFS path. 2 means visited, fully processed. We also keep an order list to build the final answer, and a valid flag that flips to false if we detect a cycle. See. This DFS does two jobs at once. Cycle detection. If we ever enter a character that's already marked as visiting, that means we looped back into the current recursion path, so the graph has a cycle and the ordering is impossible. Build ordering. We add a character to order only after exploring all of its neighbors. That add later behavior naturally creates a topological ordering. We run DFS starting from every character that hasn't been visited yet. This matters because the graph might not be one connected piece. There may be separate groups of letters with no relationship to each other. If any DFS run detects a cycle, we stop and return an empty string. Because we pushed characters after finishing their neighbors, order is built in reverse topological order. So we reverse it at the end to get the correct alien alphabet order as a string. And that's how this algorithm works. It first collects all characters, and builds a dependency graph from the first mismatches in adjacent words, then it runs DFS with cycle detection and post-order stacking to produce a topological order, reversing at the end to return the final alien alphabet string. Efficient, simple, and elegant. Let's test our function using this input. Z, X. These are words already sorted in an alien dictionary, so the order tells us something about how the alien alphabet is arranged. First, the code gathers every unique character from all words. Here that's just Z, X. Then it compares adjacent words to build ordering rules. We compare Z and X. The first characters differ immediately. Z versus X, so we learn the rule, ZX, meaning Z must come before X in the alien alphabet. After building the graph, this solution uses DFS topological sorting with states. 0 equals unvisited. 1 equals visiting, currently in recursion. If we see this again, it's a cycle. 2 equals visited, fully processed. We DFS from each character. When DFS finishes a letter, we push it into order, then we reverse order at the end to get the correct topological order. Since there's no cycle here and the only dependency is Z before X, the final ordering comes out cleanly. And that's exactly what our program outputs, ZX, matching the expected result. That output makes perfect sense because the sorted input words force Z to appear before X, and our DFS-based ordering respects that. So, our implementation is correct. The algorithm successfully builds character precedence rules and produces a valid alien alphabet using DFS topological sorting, efficient and accurate. Alright, quick recap to wrap up Alien Dictionary. Conceptually, we're given a list of words that are already sorted, but in an unknown alphabet. Each unique letter becomes a node in a graph, and we compare adjacent words to figure out ordering rules. The first place two words differ tells us the key constraint. One letter must come before the other, which becomes a directed edge in the graph. The core idea is that this isn't really a language problem. It's an ordering constraints problem. A valid alphabet order only exists if those constraints don't create a cycle. That's why topological sort is the right tool. It builds a valid ordering when possible. We also have to watch for tricky cases like prefix conflicts and letters that appear but don't connect to anything. Those still need to be included. The plan was, first, initialize the graph using all unique letters across all words. Then compare each adjacent pair of words and add a directed edge based on the first mismatch. Track an in-degree count for each letter. Finally, run topological sorting by starting with all letters that have in-degree 0 and building the order from there. We built the adjacency and in-degree structures carefully, avoided duplicate edges, checked the invalid prefix case early and returned empty immediately when needed, then ran a standard topological sort approach. The solution ran cleanly on LeetCode with no errors. We confirmed it behaves correctly on valid dictionaries, returns an empty result when a cycle makes ordering impossible, and also returns empty for the invalid prefix scenario. And of course, all test cases passed. The key takeaway is, turn sorted words into graph edges, then let topological sort reveal the hidden alphabet. And cycle detection is the ultimate truth test. Master this pattern, and a lot of ordering problems become straightforward.
Rejected. 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 At some point, it is not bad luck. It is bad prep. PatternMastery.com.
Ever need to check if a network is robust, fully connected, and loop-free? Graph Valid Tree is a PatternMastery 100 favorite, used by Google, Apple, and Meta to test your core understanding of graph cycles and connectivity. Over 30% of candidates get tripped up on edge cases like cycles or disconnected graphs. Master this and you'll breeze through network design and validation problems. Let's break down Graph Valid Tree with a basic method, ensuring you can confidently tackle any connectivity or acyclicity question in interviews. Given n nodes labeled 0 to n1 and a list of undirected edges, determine if these edges form a valid tree. A valid tree is connected. There's a path between every pair of nodes. Acyclic, no cycles. Integer n, number of nodes, list of undirected edges. Boolean, true if the graph forms a valid tree, false otherwise. Imagine verifying a computer network or electrical grid, no redundant paths, cycles, but every device must be connected. An interviewer might ask, how would you validate that a topology is a tree and not a forest or a cycle? What's tricky? Must check both connectedness and absence of cycles. Some solutions miss edge cases, disconnected graphs, or graphs with exactly one cycle. For a tree, exactly n1 edges for n nodes. Edge count check, if there aren't exactly n1 edges, it can't be a tree. Connectedness check, use DFS/BFS to visit all nodes from node 0. If you visit all nodes, count equals n, the graph is connected. If any node is unreachable, it's disconnected. Cycle check, if any edge leads back to a previously visited node, not the parent, it's a cycle. Edge count shortcut, if the edge count is correct and you visit all nodes without cycles, it must be a tree. Let's clarify. Using union find, disjoint set union, DSU, is also common. Detects cycles as you add edges and checks if all nodes are ultimately connected. Edge cases. Disconnected components, not a tree. Extra edges, more than n1, must have a cycle. Single node, n equals 1, edges equals 0, valid tree. Edge count, return false if len edges, equals n1, DFS/BFS. Build adjacency list from edges. Start from node 0, mark nodes as visited. If during traversal, revisit a node that's not the parent, it's a cycle, return false. After traversal, check if all nodes are visited, connected. Return true if no cycles and all nodes visited. Let's try to implement it using solution 1. Time complexity, O(n plus e). The concept discussion. To confirm an undirected graph is a valid tree, we need two things: 1, no cycles, and 2, everything is connected. There's a super helpful shortcut here. For an undirected graph with n nodes, it can only be a tree if it has exactly n1 edges. So we first check that. If it fails, we instantly return false. If it passes, we then run BFS from node 0 to verify connectivity, meaning we can reach all nodes. If BFS visits all n nodes, it's connected, and because we already confirmed the edge count is n1, it must be a tree. This function first verifies the edge count rule for trees, then uses BFS to ensure the graph is fully connected. This is the fast gatekeeper. A tree with n nodes must have exactly n1 edges. If there are fewer edges, the graph can't be fully connected. If there are more edges, there must be a cycle. So if this check fails, we don't even need BFS. Next we build an adjacency list so we can efficiently explore neighbors. Since the graph is undirected, every edge connects both ways, so we add v to u's list and u to v's list. Now we start BFS from node 0. We create a visited set to avoid revisiting nodes, and a queue to process nodes in BFS order. Marking 0 visited right away ensures it won't be added again. This is the BFS engine. We repeatedly pull a node from the queue, look at all its neighbors, and push any unvisited neighbor into the queue. By the end, visited contains exactly the set of nodes reachable from node 0. Finally, we verify connectivity. If BFS visited all n nodes, the graph is connected. And since we already confirmed there are exactly n1 edges, that combination guarantees the graph forms a valid tree. And that's how this algorithm works. It first checks the tree edge rule that edges must equal n-1, then it runs BFS from node 0 to confirm every node is reachable, proving the graph is connected and therefore a valid tree. Efficient, simple, and elegant. Let's test our function using this input. We have n equals 5 nodes, labeled 0 through 4, and these edges define how the nodes are connected. First, the code checks a key tree rule. A valid tree with n nodes must have exactly n1 edges. Here, n1 equals 4, and we do have 4 edges, so we pass that quick filter. Next, we build an adjacency list and run a BFS starting from node 0, marking nodes as visited as we go. From node 0, we can reach node 1, 2, and 3 directly. Then from node 1, we can reach node 4. So by the end of BFS, every node 0, 1, 2, 3, 4 gets visited, meaning the graph is fully connected. And since we already confirmed the edge count is n1, that also guarantees there's no cycle. Connected plus no cycles equals exactly what a tree is. And that's exactly what our program outputs, true, matching the expected result. The output makes perfect sense because all nodes are connected in one clean structure with no extra edges creating loops. So, our implementation is correct. The algorithm verifies the tree property by checking edge count and confirming connectivity with BFS, efficient and accurate. Let's try to implement it using solution 2. Time complexity. The concept discussion. A valid tree in an undirected graph must have no cycles and be fully connected. We again use the key rule. A tree with n nodes must have exactly n1 edges, so we check that first. Then we use union find, disjoint set, to detect cycles as we connect nodes. Union find groups nodes into components. When we process an edge, u, v, we try to merge the two components. If u and v are already in the same component, adding that edge would create a cycle, so it's not a tree. If we successfully union every edge without a cycle, then with the edge count check, the graph must be a valid tree. This version checks the edge rule, then uses union find to ensure no cycles appear while connecting all nodes. This is the fast filter. If the number of edges isn't exactly n1, it can't be a tree. Too many edges means a cycle exists. Too few means it can't be fully connected. Now we set up union find. Initially, every node is its own parent, meaning every node starts in its own separate component. The rank array helps us keep the structure balanced so operations stay fast. Find answers. Which component does this node belong to? It climbs up to the leader, root. The extra step here is path compression. After finding the root, we point nodes directly to it. That makes future lookups much faster. Union tries to connect two nodes by merging their components. If they already share the same root, that means they're already connected, and adding this edge would form a loop, so we return false to signal a cycle. Otherwise, we merge the smaller rank tree under the bigger one to keep things balanced, and return true to show the union succeeded. Now we run through every edge and union its endpoints. The moment union returns false, we've detected a cycle, so we immediately return false, not a tree. If we successfully union every edge with no cycle detected, then we return true. combined with the earlier one edge rule, that guarantees the graph is connected and cycle-free, in other words, a valid tree. And that's how this algorithm works. It first checks the required edge count n-1, then it uses union find to merge components edge by edge while detecting cycles, and if no union ever forms a cycle, the graph is a valid tree. Efficient, simple, and elegant. Let's test our function with n equals 5 nodes, 0 through 4, and these edges, 0, 1, 1, 2, 2, 3, 1, 3, 1, 4. Each pair means there's a direct connection between those two nodes. Right away, the code applies the tree rule. A valid tree with n nodes must have exactly one edges. Here, one equals 4, but we actually have 5 edges. And that's already enough to conclude it can't be a tree, because having extra edges guarantees there's at least one cycle somewhere. So the function returns false immediately, without even needing to run union find. And if we did think about it structurally, you can see the loop, 1 2 3 1 forms a cycle because edges, 1, 2, 2, 3, and 1, 3 connect back around. And that's exactly what our program outputs, false, matching the expected result. The output makes perfect sense because the graph has too many edges and contains a cycle, so it cannot be a valid tree. So, our implementation is correct. The algorithm quickly rejects non-trees using the n-1 edge check, and it would also catch cycles via union find when needed, efficient and accurate. Alright, quick recap to wrap up graph valid tree. We're given n nodes and a list of undirected edges, and we're checking whether the graph forms a valid tree. A true tree has to satisfy two rules at the same time. It must be connected, meaning every node is reachable, and acyclic, meaning there are no loops. The key insight is that a valid tree always has exactly n-1 edges. If there are too few, the graph can't be fully connected. If there are too many, a cycle must exist. So the edge count becomes the fastest filter. Then we confirm the rest by verifying connectivity or detecting cycles during traversal. The plan was, first check that the edge count equals n1. Then build an adjacency list so we can traverse efficiently. After that, run DFS or BFS starting from node 0, and make sure we end up visiting every node. During traversal, we marked nodes as visited to avoid repeats, explored neighbors to cover the whole graph, and if using DFS, we tracked the parent so we don't mistake the back and forth undirected edge for a fake cycle. The solution ran cleanly on LeetCode with no errors. We validated that it correctly rejects graphs with the wrong edge count, detects disconnected components, detects cyclic structures, and all test cases passed. The main takeaway is simple. A tree is connected plus acyclic. The n-1 edge rule is the quickest filter, and then traversal confirms everything else. Master this, and graph fundamentals start feeling automatic.
This is not another random playlist. It is a roadmap, patterns, structure, repetition. The stuff that actually sticks. PatternMastery.com.
Can you map out all the islands in a complex network? Number of connected components in an undirected graph is a PatternMastery 100 essential. Frequently asked at Google, Facebook, and Amazon to test your ability to traverse graphs and count isolated clusters. Over 30% of candidates overlook singleton nodes or double-count connections. Master this, and you'll be equipped for any graph or network connectivity problem. Let's solve number of connected components in an undirected graph using the basic method, so you never miss a node or count. Integer n, number of nodes, list of undirected edges. Integer, total number of connected components. Imagine mapping isolated local networks in a city, or identifying separate user groups in a social app. An interviewer might ask, how would you count all the isolated clusters in a computer network or database? What's tricky? Need to visit every node, even those with no connections, singleton components. Must avoid double counting, mark each node as visited as you explore. Both DFS and BFS work well here. Union find, DSU, is great for optimizing. Build an adjacency list from the edge list. Initialize a visited set or array. Loop through all nodes 0 to n1. If a node isn't visited, it's the start of a new component. Increment the count. Run DFS/BFS from that node, marking all reachable nodes as visited. Continue until all nodes are visited. Let's clarify. Single nodes with no edges count as their own components. Each DFS/BFS call finds exactly one component. Edge cases. Disconnected graph, multiple clusters. All nodes connected, one component. No edges, all singletons. Build an adjacency list from edges. Initialize a visited set or array. For every node from 0 to n1. If not visited, Increment components count. Run dfs/bfs to mark all reachable nodes as visited. Return components count. Let's try to implement it using solution 1. Time complexity. O(n plus e). The concept discussion. We're counting how many separate groups exist in an undirected graph. A connected component is a set of nodes where every node can reach every other node in that set. The strategy is straightforward. Build an adjacency list, then scan through all nodes. Whenever we find a node we haven't visited, that means we just discovered a new component, so we increment the counter and run a DFS from that node to mark the entire component as visited. Repeat until every node has been visited. This function builds the graph, then repeatedly launches a DFS from each unvisited node. Each launch corresponds to one connected component. First, we turn the edge list into an adjacency list so it's easy to find neighbors quickly. Since the graph is undirected, every edge goes both ways, so we add each endpoint to the other's neighbor list. We create a visited set to remember which nodes we've already explored, and a components counter to track how many separate groups we've found. This DFS is implemented with a stack, so we don't rely on recursion. Starting from one node, it keeps expanding to all reachable neighbors, marking them visited. When this finishes, it means we've fully covered that node's entire connected component. Now we loop through every node. If a node hasn't been visited, that means it belongs to a component we haven't discovered yet. So we mark it visited. Run DFS to visit everything connected to it. Increment components because that DFS launch represents one whole connected component. After scanning all nodes, components is the total number of connected components, so we return it. And that's how this algorithm works. It first builds the adjacency list and initializes a visited set plus a component counter. Then it scans every node and launches a DFS from each unvisited node to mark its entire group, counting how many separate groups exist. Efficient, simple, and elegant. Let's test our function with n equals 5 nodes, labeled 0 to 4, and the edges, 0, 1, 1, 2, 3, 4. Each edge shows a two-way connection, since this is an undirected graph. First, we build an adjacency list so every node knows its neighbors. Then we loop through every node, and whenever we find a node that hasn't been visited yet, that means we've discovered a new connected component. At that point we run an iterative DFS using a stack to visit everything reachable from that start node. Here's what happens. Starting at 0, DFS reaches 1, and from 1 it reaches 2. So, 0, 1, 2, is one full component. Later, when we get to node 3, it hasn't been visited yet, so that's a second component. DFS from 3 reaches 4, so, 3, 4, becomes the second component. No other nodes are left unvisited after that. And that's exactly what our program outputs, too, matching the expected result. The output makes perfect sense because the graph is split into two separate groups, one cluster of 0, 1, 2, and another cluster of 3 to 4, with no edges connecting the two. So, our implementation is correct. The algorithm accurately counts connected components by scanning all nodes and using DFS to mark each group, efficient and accurate. Let's try to implement it using solution 2. Time complexity, O(n plus e). The concept discussion. With union find, we treat each node as starting in its own separate group, so initially we haven't components. Every edge, u, v, tries to merge the groups containing u and v. If they were in different groups, merging reduces the total component count by 1. If they were already in the same group, that edge doesn't change anything. After processing all edges, the remaining number of groups is exactly the number of connected components. This function uses union find to merge nodes into groups, shrinking the component count each time a real merge happens. First we set up union find. Each node starts as its own leader, meaning every node begins in its own component. The rank array helps us keep the structure balanced so our operations stay fast. Find tells us which group a node belongs to by returning its leader. The extra improvement here is path compression. After we discover the leader, we rewrite pointers so future lookups are quicker. Union tries to connect two nodes by merging their groups. If both nodes already share the same leader, they're already in the same component, so nothing changes and we return false. Otherwise, we attach the smaller ranked leader under the bigger ranked leader to keep the structure shallow, and return true to show a merge really happened. This is the counting trick. Start with n components, because each node alone is its own component at first. Then for each edge, if union successfully merges two different components, we reduce the component count by 1. If the edge connects nodes already in the same component, we don't subtract, because the number of components didn't change. After all edges are processed, Components is exactly how many connected groups remain in the graph, so we return it. And that's how this algorithm works. It first initializes every node as its own component using union find, then it processes each edge to merge components and decreases the count only when a real merge happens, leaving the final number of connected components. Efficient, simple, and elegant. Let's test our function with n equals 5 nodes, 0 through 4, and these edges, 0, 1, 1, 2, 2, 3, 3, 4. This is an undirected graph, so each edge connects both ways. S solution uses union find. We start by assuming every node is its own component. So, components equals n equals 5. Then we process each edge and union the two endpoints. Union 0, 1 merges two separate sets components becomes 4. Union 1, 2 merges another new node into that set components becomes 3. Union 2, 3 merges again components becomes 2. Union 3, 4 merges again components becomes 1. Since every union here successfully connects two previously separate groups, we keep decreasing the component count, and by the end, all nodes are connected in one chain. And that's exactly what our program outputs, 1, matching the expected result. That output makes perfect sense because the edges form a single connected path, 0, 1, 2, 3, 4, so there's only one connected component. So, our implementation is correct. The algorithm accurately counts components by starting with n groups and reducing the count on each successful union, efficient and accurate. Alright, quick recap to wrap up number of connected components. We're given n nodes and undirected edges, and we want to count how many separate groups exist. A connected component is simply a set of nodes where every node can reach every other node in that group. And yes, this includes isolated nodes that have no edges at all, because those still count as their own component. The core challenge is making sure we cover every node, even the ones with no neighbors, without double counting anything. That's why we rely on a visited tracker. Once a node is part of a discovered group, it shouldn't be processed again. From there, DFS or BFS naturally explores one whole group at a time, and we also noted union find as a strong alternative that merges nodes into groups efficiently. The plan was, build an adjacency list from the edge list, keep a visited set or array, then scan nodes from 0 to n, 1. Every time we encounter an unvisited node, that means we've found a new component, so we increment the count and traverse outward to mark everything in that component as visited. We started traversal from each unvisited node, marked nodes visited as soon as they were discovered, and continued until the entire component was explored. The solution ran cleanly on LeetCode with no errors. We verified it works for disconnected graphs and fully connected graphs, correctly counts isolated nodes as their own components, handles graphs with no edges, and all test cases passed. The key takeaway is, one full traversal equals one component. Every new unvisited node signals a new group. Whether you use DFS, BFS, or union find, the idea is the same, and once you've got this down, graph counting problems start feeling easy.
LeetCode says medium. Your nervous system says boss fight. That is your sign you need pattern training. PatternMastery.com.
Minimum height trees looks innocent, until you try every root and blow up to ON squared. Bong interviewers love this because the optimal trick is stunningly simple. Peel the tree from the outside in until 1 to 2 centers remain. Master this, and you'll be ready for graph center/diameter problems on the spot. Let's attack it with basics. We're given n nodes labeled 0, n1 forming a tree, connected, acyclic, and an edge list. We need all node labels that can be roots producing minimum height. A tree's minimum height roots are exactly its centers, 1 or 2. Brute force, run BFS/DFS from each node to compute height ON squared. Instead, observe, if we trim leaves layer by layer, like topological sorting, the last 1 to 2 nodes left are the centers. Why? Because removing leaves doesn't change centers. We're shrinking toward the core. Complexity. ON time and ON space. Handle tiny cases. If n less than or equal to 2, return 0, n1. Build an adjacency list and a degree array. Initialize a queue with all leaves, degree 1. While more than 2 nodes remain, pop current leaves, reduce neighbor degrees, and collect new leaves. Return the last batch of nodes in the queue. They're the centers. Let's try to implement it using solution 1. Efficiency overview. The time complexity is big O of n, and the space complexity is also big O of n, where n is the number of nodes. This is highly efficient, as we only traverse the graph a constant number of times. Concept discussion. We are looking for the center nodes of the graph. The intuition is that the minimum height trees must lie somewhere near the center of the longest path, the diameter. We can find these centers by iteratively removing the outermost nodes, which are the leaves, layer by layer. This process is similar to peeling an onion. Since the maximum number of central nodes in a tree is 2, we stop when only 1 or 2 nodes remain. These remaining nodes are the roots of the minimum height trees. We start by defining the function and handling the simplest edge case. If there is only one node, that node is the root of the MHT. In the next step, we set up our adjacency list representation of the graph, which allows us to quickly look up neighbors. Simultaneously, we initialize an array to store the degree of each node. We iterate through the input edges to populate the graph and calculate the degree for every node. The process begins by identifying all the initial leaves. In a tree structure, a leaf is defined as any node with a degree of exactly 1. We load all these initial leaf nodes into our queue for the first round of trimming. This loop drives the entire trimming process. We continue removing layers of leaves as long as more than 2 nodes remain. Since minimum height trees can have at most 2 roots, once we reach 2 or fewer nodes, the centers have been found. Inside the loop, we process all leaves currently in the queue, representing one layer of the graph. We decrement the count of remaining nodes by the size of the current leaf layer. The next queue will hold the new nodes that become leaves after the current layer is removed. For every leaf being removed, we iterate through its neighbors. Removing the leaf effectively decreases the neighbor's degree count. If a neighbor's degree drops to 1, it means that neighbor has just become a new leaf, and we add it to the next queue for the next round of trimming. Once the while loop terminates, the queue contains only the remaining central nodes, 1 or 2. We return this queue as our final list of minimum height tree roots. And that's how this algorithm works. It first sets up the graph and identifies initial leaves, then gradually trims the outermost leaf layer until only the 1 or 2 central nodes remain. Efficient, simple, and elegant. Now that we've implemented our solution to find the minimum height trees, it's time to test it with an actual input. This helps us see how the algorithm trims leaves from the tree level by level to identify the root nodes that produce the minimum height. We'll walk through the input, observe how the leaves are removed, and confirm that the output matches the expected result. Let's test the function using this input. We have n equals 4, representing 4 nodes labeled from 0 to 3, and an edges array defining the connections between them. This tree structure forms a star centered at node 1, which connects to nodes 0, 2, and 3. Here's why the solution works. The algorithm builds a graph and counts the degree of each node. It then identifies the initial leaves, which are nodes with only one connection. One layer at a time, it removes these leaves and updates the degrees of their neighbors. This process continues until at most 2 nodes remain. Those remaining nodes are the roots of the minimum height trees. For this example, the initial leaves are 0, 2, and 3. After trimming them, only node 1 remains, which is the root of the minimum height tree. And that is exactly what the program outputs. 1. This verifies that the code works correctly and passes this test case. So our implementation is correct. The algorithm successfully identifies the center nodes that minimize the height of the tree. It handles the given structure accurately and returns the expected output. The BFS-style trimming ensures efficiency and guarantees that the minimal height roots are found. Let's try to implement it using Solution 2. Efficiency overview. The time complexity is big O of n, and the space complexity is also big O of n, as we perform 2 breadth-first searches over the graph. Concept discussion. This solution utilizes the property that the root of a minimum height tree must always lie at the exact center, or centers, of the longest path in the graph, known as the tree's diameter. We find this diameter by performing 2 breadth-first searches. The first BFS finds the furthest node from an arbitrary starting point, one end of the diameter. The second BFS, starting from that endpoint, finds the absolute furthest node, the other end of the diameter. Once we have the full diameter path, we simply identify the middle 1 or 2 nodes, which are our MHT roots. We start by handling the base case of one node. Then we initialize the adjacency list representation of our graph by iterating through all the edges. Next, we define our essential breadth-first search helper function. It takes a starting node. We set up a queue for traversal, a parent array to trace the path back later, and a visited array to prevent cycles. This while loop is the standard BFS execution. It systematically explores all reachable nodes layer by layer. Importantly, it ensures we record the parent of every node found, and the loop returns the last node visited, which is the farthest node from the start node. This is the 2-step approach to finding the diameter. We start the first BFS arbitrarily from node 0 to find one endpoint of the diameter. Then, we start the second BFS from this endpoint to guarantee finding the opposite endpoint. which is the absolute furthest node in the entire tree. Using the parent array recorded during the second BFS, we trace the path backward from the final furthest node all the way to its starting point, the other diameter endpoint. This gives us the full path representing the diameter. Finally, we locate the center or centers of the path. If the path length is odd, there is a single center node found by integer division. If the path length is even, there are two center nodes. These center nodes are the roots of our minimum height trees. And that's how this algorithm works. It first performs two breadth-first searches to find the tree diameter, then identifies the middle one or two nodes of that path. Efficient, simple, and elegant. Before checking the output, let's understand the problem. We are given n equals 6 nodes, edges equals 3, 0, 3, 1, 3, 2, 3, 4, 5, 4. The goal is to find all roots of minimum height trees, nodes that produce the smallest height when chosen as tree roots. Let's test our function with this input. Here, we have a tree with 6 nodes, connected as described by the edges. Here's why the solution works. Build the graph. Represent nodes as adjacency lists. Use BFS to find tree diameter. First BFS from any node, here, node 0, finds one endpoint of the diameter, Nadia. Second BFS from Nadia finds the other endpoint, Nodeb, and keeps track of parent pointers to reconstruct the path. Identify middle nodes. The diameter path is the longest path in the tree. Nodes in the middle of this path are the roots of MHTs. If the path length is even, there are two middle nodes. If odd, one middle node. Step by step with this input. BFS from 0 farthest node is 5, BFS from 5 farthest node is 3, diameter path, 5, 4, 3, 0, or similar middle nodes, 3, 4. These nodes will produce minimum tree height when chosen as roots. And that is exactly what the program outputs, 3, 4. This confirms our code works correctly for this test case. So, our implementation is correct. It successfully identifies MHT roots, efficient, accurate, and reliable. Our implementation is correct. It accurately finds the diameter of the tree. It correctly identifies middle nodes as MHTs. Let's wrap up the minimum height trees problem. At first, it seems like you just need to pick the best root, but trying every node quickly explodes into ON squared. The clever trick here? We don't search from the roots outward, we peel the tree inward. Breakdown recap. We're given n nodes forming a connected, acyclic graph, a tree. Our goal is to find all possible root nodes that produce the minimum height when the tree is rooted there. In simple terms, we're looking for the tree's centers, the points that minimize the longest path to any leaf. Assess recap. The brute force approach would be to run BFS or DFS from every node to measure height, but that's too slow. Instead, we realize that the tree's centers can be found by trimming leaves layer by layer, just like peeling an onion. Each round, we remove the outermost leaves until only one or two nodes remain, which are the centers of the tree. Structure recap. We handled small cases first. If there are two or fewer nodes, we just return all of them. Then we built an adjacency list and tracked the degree of each node. Next, we added all current leaves to a queue, and while more than two nodes remained, we kept removing those leaves, updating their neighbors, and collecting new ones as they appeared. The final remaining nodes are our centers. Implement recap. After coding this peeling logic, we ran it on LeetCode, and the solution executed smoothly without any errors. Check recap. We verified it across multiple test cases, and each time, the output correctly identified the minimum height tree roots. Closing insight. The big lesson? Sometimes, finding the center of a problem means working from the outside in. By trimming layer by layer, we let the structure reveal its own core, efficiently, cleanly, and in linear time.
Honestly, I only did patterns. Then they got the offer. PatternMastery.com.
What happens when an interviewer wants to truly test your algorithmic efficiency? Merge Case Sorted Lists is a PatternMastery 100 heavyweight and a frequent guest at Google, Amazon, and Microsoft interviews. Over 40% of candidates get slowed down by the complexity and pointer management. Master this, and you'll prove you can handle multi-list merges, priority queues, and advanced patterns. Let's attack Merge Case Sorted Lists with the basic problem-solving framework, a stepwise guide for turning chaos into clarity, even in the toughest coding rounds. Let's break it down. Given an array of k-linked lists, each sorted in ascending order, merge them all into one sorted linked list and return its head. Example, input, 145, 134, 26. Output, 1, 1, 2, 3, 4, 4, 5, 6. Real-world example. Think about a system that needs to combine multiple log files, each sorted by timestamp, into a single unified log for analysis. A classic interview extension. How would you merge sorted streams from different servers in real time? Let's assess it. What's tricky here? Naive approach. Merge the lists one by one using the two-list merge logic, kilonewton, time, where n is total nodes, works, but not optimal. Optimal approach. Use a min heap, priority queue, to always pick the smallest head among the k-lists, giving you on log k time. Let's think step by step. Push the first node of each list into a min heap, keyed by node value. Repeatedly pop the smallest node from the heap, attach it to the merged list, and if there's a next node in that list, push it into the heap. Continue until the heap is empty. Let's dig deeper. Why a heap? It guarantees that at each step, you can efficiently, in O log k, get the smallest remaining node across all lists. Using a dummy node for the result list keeps the code clean and bug-free. Edge cases? Some lists may be empty. All lists empty? Output should be null. Here's the structure. Create a dummy head for the result list and a current pointer. Initialize a min heap and insert the first node of each list if not null. While the heap isn't empty, pop the node with the smallest value. Attach it to the current pointer. If the pop node has a next, push that next node into the heap. Move current forward. Return dummy.next. Let's try to implement it using solution 1. Time and space complexity. This approach achieves an optimal time complexity of big O of n log k and uses big O of k space, where n is the total number of nodes and k is the number of lists. We are solving this by leveraging a min heap, also known as a priority queue. The key idea is simple. We want to always know which of the k lists has the absolute smallest next element. By storing the current head of every list in a minute heap, the smallest element is always instantly accessible at the top. We continuously pull the smallest element, add it to our result list, and then replace it in the heap with its successor from the original list. First, we define the main function and initialize an empty array called heap. Since JavaScript does not have a built-in priority queue, we will manually implement the heap functions using this array. The pushHeap function handles adding a new node to the heap while maintaining the minHeap property. When a new node is added to the end, it is bubbled up by comparing it to its parent and swapping them if the child is smaller. This ensures the smallest element remains near the top. The popHeap function extracts the smallest element, which is always at index 0. It then replaces the top element with the last element of the array and bubbles down that element to its correct position. This restores the minHeap property so the next smallest node is ready at the top. Next, we iterate through all the input linked lists and push the head node of every non-empty list into our minHeap. This sets up our priority queue with the starting element from each of the k-lists. Now we set up a dummy node to simplify the list creation process. We also initialize a current pointer pointing to the dummy node. Then we enter a loop that runs as long as the heap is not empty. In each iteration, we extract the smallest node globally using popHeap, append it to our result list by setting current.next to this node, and advance the current pointer. If the extracted node has a next element, we immediately push that successor node back into the heap, ready for the next comparison. Finally, we return the next property of the dummy node, which is the head of our newly merged, fully sorted linked list. And that is how this algorithm works. It first initializes a min heap with the heads of all k-lists, then repeatedly extracts the smallest available node and replaces it with its successor until the entire list is merged. Efficient, simple, and elegant. Now let's solve solution 1, merging k-sorted linked lists using a min heap. We'll see how to efficiently pick the smallest node among multiple lists using a heap. Step by step, we'll understand how the heap helps us maintain order. Time complexity is O(n) log k, where n is the total number of nodes across all lists, and k is the number of lists. Each node is pushed and popped from the heap once, which takes log k per operation. The idea: use a min heap to always know which list has the smallest current node. Push the head of each list. Let's try to implement it using solution 2. Time and space complexity. This approach also achieves an optimal time complexity of big O of n log k, but uses only big O of one auxiliary space, ignoring the recursion stack. We use a divide and conquer strategy, which is like running a tournament. We recursively break the large problem, merging k-lists, into smaller problems, merging two lists. We solve the small problems and then combine those results. By merging lists in pairs, we maintain sorted order efficiently across all stages until only one final, sorted list remains. First, we define the main merging function. We handle the simple edge case. If we are given no lists at all, we immediately return null. Next, we define a crucial helper function called merge2lists. This function takes two already sorted linked lists, L1 and L2, and merges them into a single sorted list. We set up a dummy node and a current pointer pointing to it. Then, we iterate while both L1 and L2 are not null. At each step, we compare the current nodes of L1 and L2. Whichever node has the smaller value is linked to the current pointer of our result list. We then advance the corresponding list pointer and also advance the current pointer. Once one of the lists is exhausted, we attach the remainder of the other list directly. Finally, we return dummy.next, which points to the head of the merged list. After that, we implement a recursive function called mergeRange. This function performs the divide and conquer logic. If the range start equals end, we have reached a single list, which is the base case, so we simply return that list. Otherwise, we find the middle index, recursively call mergeRange on the left half and the right half, and then use our merge2lists helper to combine the two results into one merge list. Finally, we initiate the recursive merging process by calling mergeRange over the entire array of input lists, starting from index 0 up to the last index. The result of this top-level call is our final, fully merged, and sorted list. And that is how this algorithm works. It first recursively divides the k-lists into pairs, then merges those pairs together using a standard two-list merge function, reducing the problem set by half in each step until only one sorted list remains. Efficient, simple, and elegant. Let's test our function to merge multiple sorted linked lists with 1, 4, 5, 1, 3, 4, and 2, 6. It merges two lists at a time until all lists combine into 1, 1, 2, 3, 4, 4, 5, 6. For empty input, it returns. This approach efficiently merges multiple lists, keeps order, and works reliably for any input. Breakdown recap. We're given an array of k-sorted linked lists and need to merge them all into one fully sorted linked list. Conceptually, it's about combining multiple sorted sequences into a single unified list. Assess recap. A naive approach would merge the lists one by one using two-list logic, but that's slow. The optimal approach leverages a min-heap, priority queue, to always select the smallest node across all lists. This reduces the complexity significantly and makes it efficient even for many lists. Structure recap. Here's the plan. Create a dummy head for the merged list and a current pointer. Initialize a min-heap and push the first node of each list, if not null. While the heap isn't empty, pop the smallest node, attach it to the merged list, and if that node has a next, push it into the heap. Move the current pointer forward and continue. At the end, return the merged list. Implement recap. We implemented this using a min-heap, storing tuples of node value, node, to ensure proper ordering. Running it on LeetCode, the solution executed cleanly and efficiently merged all lists without errors. Check recap. We verified the logic across all general cases and edge cases. The solution runs in on log k, time with OK space for the heap and produces correct results consistently. Closing insight. The key takeaway? When merging multiple sorted sequences, a min-heap is the most effective tool. It lets you efficiently track and select the smallest current element, keeping the process clean, fast, and scalable for any number of lists. Have you ever heard that reversing a linked list is the fundamental question in any software engineering interview? Reverse linked list is a true PatternMastery 100 staple and frequently shows up at Facebook, Google, and Amazon. Missing this? You're out. Over 40% of candidates get tripped up by edge cases here. Let's guarantee you're not one of them. Let's attack reverse linked list using the basic problem-solving framework, which brings structure and confidence to every interview challenge. Ready? Here we go. Given the head of a singly linked list, our goal is to reverse the list so the nodes point in the opposite direction, and return the new head. Input: head node of a singly linked list, like 1, 2, 3, 4, 5, null. Output: head node of the reverse list, for example, 5, 4, 3, 2, 1. Think about undo operations in text editors. Each action is stored in a list, but when you undo you need to traverse those actions in reverse order. How do you efficiently reverse that structure? Interviewers might even ask, how would you print a linked list in reverse order, or reverse a playlist queue? What makes this tricky? You can't just flip pointers all at once. You need to avoid losing your place in the list. Naive mistake. If you just set node.next equals prev without remembering the next node, you lose the rest of the list. Think step by step. We'll traverse the list with a current pointer. For each node, we'll save the next node, so we don't lose it. Reverse the current node's pointer to point to the previous node. Move the previous and current pointers forward. Let's go even deeper. Imagine you're physically turning each train car around on a track. If you detach a car without remembering where the next is, you'll derail. That's why you always store the next node before changing any links. Edge cases? Empty list, head equals null. Single node, should return the same node. Classic multi-node lists. Here's the plan. Let's try to implement it using solution 1. This iterative approach is very efficient, achieving a time complexity of big O of n, and an excellent space complexity of big O of 1. We are solving the linked list reversal problem using an iterative approach. The core strategy is to maintain 3 main pointers: previous, current, and next. In each step of iteration, we temporarily store the next node, redirect the current node's pointer to the previous node, and then advance all 3 pointers forward. This effectively unlinks the current node from its original sequence and relinks it to the front of the reversed portion. Here is the code. var reverse list equals function head, let prev equals null, let current equals head. We define a function that takes the head of the list. We initialize 2 crucial pointers. Prev starts at null, representing the end of our new reversed list, and current starts at the head of the original list, indicating the node we are currently processing. Next, we enter a loop, while current does not equal null. This loop continues as long as there are nodes left to process. It ensures that every element in the original linked list is visited exactly once. The next step is critical. Const next node equals current.next. Before breaking the forward link of the current node, we safely store a reference to the node that comes immediately after it. We call this next node. Now, we reverse the current node. Current.next equals prev. We change the next pointer of the current node to point backward, specifically to the node stored in prev. This node now officially joins the reversed portion of the list. Then, we move the pointers forward. Prev equals current, current equals next node. The current node becomes the new prev node, as it is now the start of the reversed list. The current pointer then moves to the next node we saved earlier, preparing for the next iteration. Finally, after the loop finishes, return prev. The current pointer will be null, meaning we have processed all nodes. The prev pointer, which was tracking the last node processed, now points to the new head of the fully reversed linked list, which we return. And that's how this algorithm works. It first sets up the necessary pointers to keep track of the node before and the node after the current one. Then, in a single loop, it redirects the current node's pointer backward until the entire list is reversed. Efficient, simple, and elegant. Now that we've implemented our reverse list function, let's see how it works with a sample linked list. This test will show if the function correctly reverses all the nodes, turning the last node into the first, and so on. Let's test it with this input. 1, 2, 3, 4, 5. This represents a singly linked list. 1, 2, 3, 4, 5. Our goal is to reverse the order of the nodes. Here's how it works. We start with prev as none and cur at the head. For each node, we temporarily store the next node, then reverse the pointer so cur.next points to prev. We move prev a and cur forward and repeat until the end. Step by step, the nodes get reversed. 1, 2, 3, 4, 5 becomes 5, 4, 3, 2, 1. The output is 5, 4, 3, 2, 1, exactly what we expect. This confirms our function works correctly. In summary, our implementation successfully reverses the linked list, handles any list length, and does it efficiently with O(n) time and O(1) extra space. Simple, accurate, and reliable. Let's try to implement it using solution 2. This recursive approach achieves a time complexity of big O of n because we visit every node once. However, due to the function call stack, the space complexity is big O of n. We are tackling the linked list reversal using recursion. The key idea here is to rely on the function stack to automatically reverse the pointers as the function calls return. We recursively call the function until we reach the very last node, which will be the new head. As the recursion unwinds, we take the current node and attach it to the end of the sublist that has already been reversed by the deeper calls. This turns the reversal process inside out. Here is the code. var reverse list equals function head, if head equals null or head.next equals null return head. We define our recursive function. The base case is crucial. If the list is empty or contains only one node, it is already reversed, so we simply return the head. This stops the recursion. Next, we call recursively. Const new head equals reverse list head.next. This is the deep dive into recursion. We call reverse list on the rest of the list, starting from head.next. This call will eventually return the true final new head of the entire reversed list. We store this result because every subsequent step will return this exact same pointer. Now comes the reversal step, head.next.next equals head. This is where the magic happens as the stack unwinds. We are currently at head. Head.next is the node immediately following us. Let's call it node B. We want node B to now point back to head. So we take node B's next pointer, head.next.next, and make it point back to head. Then, we prevent cycles. Head.next equals null. To ensure we do not create a cycle in the list, we set the original forward link of the current head node to null. This prevents the current node from pointing forward into the list it just joined. Finally, we return the new head. Return new head. Every function call simply returns the new head found by the deepest recursive call. This ensures that the original caller always receives the correct starting point of the fully reversed list. And that is how this algorithm works. It first identifies the base case to stop recursion, then recursively reverses the sublist, and finally unwinds the stack to connect the current node to the end of the already reversed segment. Efficient, simple, and elegant. Let's see how our recursive solution reverses a linked list step by step. We'll test it with a simple input, 1, 2. This represents a linked list, 1, 2. Our goal is to reverse it so that the last node becomes the first. Here's how it works. The algorithm uses recursion to reach the end of the list. When it hits the last node, which is 2, it starts reversing the pointers. Each node points back to the previous one. For example, node 2 points to node 1 instead of none, and the original head becomes the new tail with its next set to none. The recursion returns the new head, which is 2. Step by step for 1, 2. We call reverse list 1, which calls reverse list 2. Node 2 becomes the new head, and node 1's next pointer is set to none. The final list is 2, 1. The output is 2, 1, exactly what we expected. This confirms our function correctly reverses the linked list. In summary, our recursive implementation efficiently reaches the end, reverses the pointers step by step, and updates the head and tail accurately. It works even for small lists, making the solution clear, accurate, and reliable. Breakdown recap. Conceptually, the task is simple. Take a singly linked list and reverse the direction of all its pointers so that the last node becomes the new head. If you think about it, this is like undoing actions in a text editor. You want to traverse everything in reverse order. Assess recap. The tricky part is managing the pointers. You can't just flip links randomly. If you lose track of the next node, the rest of the list is gone. So we compared approaches and chose a safe, iterative method. Traverse the list while keeping track of the previous, current, and next nodes, reversing links step by step. Structure recap. Our plan was straightforward. Initialize 2 pointers, previous and current. For each node, first store the next node. Reverse the current node's pointer to the previous node. Move previous and current forward. Repeat until the end. At the end, previous points to the new head. Implement recap. We implemented this iterative approach, carefully updating pointers at each step. Running it on LeetCode, the code executed cleanly, without errors or lost links. Check recap. We verified the logic with multiple test cases, multi-node lists, single-node lists, and empty lists. Each time, the nodes were correctly reversed, and all edge cases passed. Time complexity is O(n), and space is O(1), efficient and elegant. Closing insight. The key takeaway? Reversing a linked list is about thinking ahead. Always track your next step before changing links. A small precaution that ensures you never lose the rest of the list. Master this, and you'll handle one of the most classic interview questions with confidence.
You thought your job was safe until you got that email. Now you're back on LeetCode remembering you forgot everything about trees and graphs. Interviewer says, solve this in O of n. Your brain says, 404, solution not found. Don't be that person. Subscribe to PatternMastery.com and master the coding patterns FANG companies actually test.
Detect loop in linked list. This question came up during my on-site at Amazon. What looked like a simple linked list problem turned out to be a test of whether I understood Floyd's cycle detection algorithm, something a lot of candidates overlook. And over 40% of candidates freeze on this logic. Today, we'll make sure you never get tripped up by a sneaky loop again. Let's crush this blind 75 must know with a foolproof strategy. First, Let's break down the problem. Given the head of a singly linked list, we need to determine if there's a cycle, meaning, does any node link back to a previous node instead of ending with null? As you see in the image, node 5 points back to node 2, forming a loop. If there's a cycle, we return true. If not, we return false. It's that simple. Let's assess our options. One brute force way is to remember every node we've seen using a hash set. But that needs extra space. Is there a slicker way? Yes. The classic tortoise and hare method uses 2 pointers. One moves 1 step at a time, slow, the other moves 2 steps at a time, fast. If there's a cycle, fast will eventually catch slow. If not, fast will hit null. This technique gives us on time and o1 space, super efficient. Now, let's structure our approach. Start both slow and fast pointers at the head. Move slow by 1 node, fast by 2 nodes each loop. If at any point slow equals fast, we found a cycle, return true. If fast hits null, the end, there's no cycle, return false. Let's try to implement it using solution 1. This approach uses Floyd's tortoise and hare algorithm, giving us excellent performance with big O of n time complexity and big O of 1 space complexity. The idea behind the tortoise and hare approach is simple. Use 2 pointers moving at different speeds. The slow pointer moves 1 step at a time, and the fast pointer moves 2 steps at a time. If there is a cycle in the list, the fast pointer will eventually catch up to the slow pointer inside the cycle. If there is no cycle, the fast pointer will reach the end of the list, which is null. Here is the code. var hasCycle equals function head. We define the hasCycle function, which accepts the head of the linked list. This function is designed to return a boolean indicating whether a cycle is present. Next, we initialize pointers. Let slow equals head, let fast equals head. We initialize our 2 pointers, slow and fast, both starting at the beginning of the linked list, which is the head node. Then, we enter the main loop, while fast is not equal to null and fast.next is not equal to null. The main loop continues as long as the fast pointer can safely move forward 2 steps. If fast or fast.next is null, we have reached the end of the list, meaning there is no cycle. Inside the loop, we advance the pointers. Slow equals slow.next, fast equals fast.next.next. The slow pointer takes 1 step, while the fast pointer takes 2 steps. This speed difference is what enables the detection of a cycle. Next, we check for convergence. If slow is equal to fast, return true. If, at any point, the slow pointer becomes equal to the fast pointer, it means they have met inside a cycle, and we immediately return true. Finally, if the loop finishes without the pointers meeting, we return false. If the fast pointer hits the end of the list, we conclude that no cycle exists, and we return false. And that is how this algorithm works. It first sets up 2 pointers moving at different speeds, then uses their convergence to determine if a cycle is present. Efficient, simple, and elegant. Let's check if our hasCycle function works. We want to see if a linked list contains a cycle, where a node points back to a previous node instead of none. We test it with 3, 2, 0, -4, and pos equals 1, meaning -4 points back to node 2, forming a cycle. The function uses a set to track visited nodes. As we move through the list, we add each node to the set. When we reach a node already in the set, we detect a cycle and return true. The output is true, confirming the function works. This implementation correctly detects cycles in any list, is simple, and efficient with on time and space. Let's try to implement it using solution 2. This approach uses a hash set, achieving big O of n time complexity because we visit each node at most once, but it requires big O of n space complexity to store the references to the visited nodes. The hash set approach relies on memory. We traverse the linked list node by node. For every node we encounter, we store a reference to it in a set. If we ever encounter a node whose reference is already stored in the set, it means we have reached this node before, confirming the presence of a cycle. If we reach the end of the list, a null node, without encountering a duplicate, there is no cycle. Here is the code. var hasCycle equals function head. We define our hasCycle function. Inside, we immediately initialize a new set, which we call scene. This set will store the references of all the nodes we have already visited. We also initialize a current pointer starting at the head. Next, we enter the loop, while current is not equal to null. We begin traversing the list. The loop continues as long as our current pointer points to a valid node and hasn't reached the end of the list, null. Inside the loop, we check if scene.hasCurrent return true. This is the core detection logic. Before processing the current node, we check if its reference already exists in our scene set. If it does, We have found a node we've seen before, proving there is a cycle, and we return true. If the node is new, we add it to the set in advance, scene.addCurrent, current equals current.next. If the node is new, we add its reference to the scene set, marking it as visited. Then, we advance the current pointer to the next node in the list. Finally, if the loop completes without returning, we return false. If the loop completes because current became null, it means we reached the end of the linked list without ever finding a repeated node, confirming there is no cycle. We return false. And that is how this algorithm works. It first sets up a hash set to track visited nodes, then iterates through the list, using the set to quickly identify if any node has been encountered before. Efficient, simple, and elegant. Now that we've implemented our solution to detect cycles in a linked list, let's see it in action. We test it with 1, 2, and pos equals 0, meaning node 2 points back to node 1, forming a cycle. The function uses 2 pointers, slow moves 1 step at a time, and fast moves 2 steps. If a cycle exists, fast will eventually meet slow. Otherwise, fast reaches the end. For this input, slow and fast meet, confirming a cycle. The output is true, showing that the implementation correctly detects the cycle. This two-pointer approach efficiently identifies cycles, works for any list, and is simple, accurate, and reliable. Breakdown recap. Conceptually, we're given a singly linked list, and we need to determine if it contains a cycle, that is, if any node points back to a previous node instead of ending with null. If a cycle exists, we return true, otherwise, false. Assess recap. We looked at different approaches. A brute force method is to store visited nodes in a hash set, but that uses extra space. A more elegant solution is the tortoise and hare technique, 2 pointers moving at different speeds. If there's a cycle, the faster pointer eventually catches up to the slower one. If not, the fast pointer reaches the end of the list. This method gives O(n) time with O1 space, highly efficient. Structure recap. Our approach was straightforward. Initialize slow and fast pointers at the head. Move slow 1 step at a time, fast 2 steps. If they meet at any point, a cycle exists, return true. If fast reaches null, no cycle exists, return false. Implement recap. We implemented this using the classic 2-pointer method. Running it on LeetCode, the code executed cleanly, detecting cycles or confirming acyclic lists without errors. Check recap. We verified it with multiple cases. Lists with cycles, like one where node 5 points back to node 2, correctly returned true. Lists without cycles returned false. This confirmed that the logic works as expected in all scenarios. Closing insight. The key takeaway? Cycle detection is all about pointer strategy. By carefully moving slow and fast pointers, you can catch loops efficiently, using constant space, a small trick that demonstrates big mastery over linked lists.
Quiet room. Shared screen. One question. No clue. That silence is expensive. PatternMastery.com.
What happens when an interviewer wants to truly test your algorithmic efficiency? Merge case sorted lists is a PatternMastery 100 heavyweight and a frequent guest at Google, Amazon, and Microsoft interviews. Over 40% of candidates get slowed down by the complexity in pointer management. Master this, and you'll prove you can handle multi-list merges, priority queues, and advanced patterns. Let's attack merge case sorted lists with the basic problem-solving framework. A stepwise guide for turning chaos into clarity, even in the toughest coding rounds. Let's break it down. Given an array of k-linked lists, each sorted in ascending order, merge them all into one sorted linked list and return its head. Example, input, 145, 134, 26. Output, 1, 1, 2, 3, 4, 4, 5, 6. Real-world example. Think about a system that needs to combine multiple log files, each sorted by timestamp, into a single unified log for analysis. A classic interview extension. How would you merge sorted streams from different servers in real time? Let's assess it. What's tricky here? Naive approach. Merge the lists one by one using the two-list merge logic, O(kilonewton), time, where n is total nodes, works, but not optimal. Optimal approach. Use a min heap, priority queue, to always pick the smallest head among the k-lists, giving you O(n) log k time. Let's think step by step. Push the first node of each list into a min heap, keyed by node value. Repeatedly pop the smallest node from the heap, attach it to the merged list, and if there's a next node in that list, push it into the heap. Continue until the heap is empty. Let's dig deeper. Why a heap? It guarantees that at each step, you can efficiently, in O log k, get the smallest remaining node across all lists. Using a dummy node for the result list keeps the code clean and bug-free. Edge cases? Some lists may be empty. All lists empty? Output should be null. Here's the structure. Create a dummy head for the result list and a current pointer. Initialize a min heap and insert the first node of each list if not null. While the heap isn't empty, pop the node with the smallest value. Attach it to the current pointer. If the pop node has a next, push that next node into the heap. Move current forward. Return dummy.next. Let's try to implement it using solution 1. Efficiency overview. The time complexity is big O of n plus m, where n and m are the lengths of the lists, because we traverse each list exactly once. The space complexity is big O of 1 because we only use a few extra pointers and do not allocate new nodes. The concept discussion. We are using an iterative approach with the help of a dummy node. Since we are merging two sorted lists, we can compare the nodes at the current positions of both lists and always pick the smaller one to attach to our new merged list. We use three main pointers, one for list 1, one for list 2, and one to track the tail of the new merged list, which helps us connect the nodes quickly. Here is the function setup. We define our function. var merge two lists equals function with parameters list 1 and list 2. We create a dummy node with next set to null. We initialize a current pointer pointing to the dummy. Then we set pointer p1 to list 1 and pointer p2 to list 2. The dummy node is a standard technique used in linked list operations. It simplifies edge cases by giving us a fixed starting point for the merged list. Current tracks the end of the merged list, and p1 and p2 point to the current nodes we are comparing in the input lists. Next, we enter the main iteration loop, while p1 is not null and p2 is not null. The loop runs as long as both lists have nodes remaining. Inside the loop, we compare p1.val with p2.val. If p1.val is less than or equal to p2.val, we set current.next to p1, then advance p1 to p1.next. Otherwise, we set current.next to p2, then advance p2 to p2.next. After connecting a node, we always advance current to current.next, preparing for the next iteration. Finally, after the loop, we handle the remaining nodes. We set current.next to p1 if p1 is not null. Otherwise, we set it to p2. This ensures that any leftover nodes in the non-empty list are attached directly to the merged list. Finally, we return dummy.next, which is the head of our newly merged list. And that is how this algorithm works. It first sets up a dummy node and pointers, then iteratively compares the heads of the two lists, linking the smaller node to the resulting list. Efficient, simple, and elegant. We start with two sorted linked lists. The first list contains the values 1, 2, and 4. The second list contains the values 1, 3, and 4. Our goal is to merge these two lists into a single sorted list. As we compare nodes from both lists, we always pick the smaller value and move forward. Both lists begin with the value 1, so we add 1 first. Next, we compare 2 and 3, and select 2. Then we select 3, followed by 4 from the first list, and finally 4 from the second list. The merged result is 1, 1, 2, 3, 4, 4. The output matches the expected result, so the test case is accepted. Let's try to implement it using solution 2. Efficiency overview. The time complexity is big O of n plus m, as every node is processed exactly once. The space complexity is big O of n plus m, due to the depth of the recursion stack created during the function calls. The concept discussion. This solution uses recursion, which can be much cleaner than iteration for linked list problems. The fundamental principle is the same. Compare the heads of the two lists. We pick the node with a smaller value and decide that this node will be the head of the merged list. Then, we recursively call the function, linking the next pointer of the chosen node to the result of merging the rest of the lists. This continues until one of the lists becomes empty, which serves as our base case. Here are the base cases. If list 1 is null, we return list 2. If list 2 is null, we return list 1. These are the crucial termination conditions for our recursion. If one of the lists is empty, we have nothing left to merge from that list, so we simply return the non-empty list, which is already sorted and ready to be appended to the current sequence. Next, we handle the case where list 1 value is less than or equal to list 2 value. We set list1.next to the result of recursively merging list1.next with list 2. Then we return list 1. This ensures that list 1 is the head of this merged segment, and the recursive call will handle the remaining nodes. Otherwise, list 2 value is smaller. We set list2.next to the result of recursively merging list 1 with list2.next. Then we return list 2. This ensures that list 2 is the head of this merged segment, and the recursion will handle the remaining nodes. And that is how this algorithm works. It first establishes base cases for empty lists, then recursively compares the current head nodes, always choosing the smaller node as the current head and delegating the merging of the remaining nodes to a subsequent recursive call. Efficient, simple, and elegant. Let's test our function with this input. 2 empty lists, list 1 and list 2. Since both lists are empty, there are no elements to process. Our solution handles this edge case correctly. With no data, the output should also be an empty list. And that's exactly what we get. The program returns an empty list, just as expected. So, our implementation is correct. Even with empty inputs, the function works properly, returning the right result without errors. It's robust and ready for any test case. Breakdown recap. We're given an array of k-sorted linked lists and need to merge them all into one fully sorted linked list. Conceptually, it's about combining multiple sorted sequences into a single unified list. Assess recap. A naive approach would merge the lists one by one using two-list logic, but that's slow. The optimal approach leverages a min-heap, priority queue, to always select the smallest node across all lists. This reduces the complexity significantly and makes it efficient even for many lists. Structure recap. Here's the plan. Create a dummy head for the merged list and a current pointer. Initialize a min-heap and push the first node of each list, if not null. While the heap isn't empty, pop the smallest node, attach it to the merged list, and if that node has a next, push it into the heap. Move the current pointer forward and continue. At the end, return the merged list. Implement recap. We implemented this using a min-heap, storing tuples of node value, node, to ensure proper ordering. Running it on LeetCode, the solution executed cleanly and efficiently merged all lists without errors. Check recap. We verified the logic across all general cases and edge cases. The solution runs in on log k, time with OK space for the heap and produces correct results consistently. Closing insight. The key takeaway? When merging multiple sorted sequences, a min-heap is the most effective tool. It lets you efficiently track and select the smallest current element, keeping the process clean, fast, and scalable for any number of lists.
Wake up. Work. Scroll jobs. Do random LeetCode. Feel behind. Repeat. Break the loop. PatternMastery.com. Breakdown. Assess. Structure. Implement. Check. 5 steps. Way less panic. PatternMastery.com.
To cement your linked list mastery, try these 5 classic follow-ups next. Reverse linked list 2 builds on today's pattern, challenging you to reverse only a section of the list. Palindrome linked list requires checking if a list reads the same forward and backward, which often involves reversing part of it. Merge 2 sorted lists is perfect for practicing pointer updates as you combine 2 lists into one. Let's break down the remove nth node from end of list problem. You're given the head of a singly linked list and an integer n. You need to remove the nth node from the end of the list. As shown in the image, if the list is 1, 2, 3, 4, 5 and n equals 2, the node with value 4 should be deleted. The output should be 1, 2, 3, 5. Let's assess what's tricky here. A brute force way is to count the nodes, then walk to the node just before the one to remove. But that takes 2 passes. Interviewers want a slick, 1-pass solution. The classic trick is to use 2 pointers, fast and slow. Now, let's structure our approach. Create a dummy node pointing to head to handle edge cases easily. Move the fast pointer n steps ahead. Move both fast and slow pointers until fast reaches the end. Skip the nth node from n by setting slow.next equals slow.next.next. Return dummy.next as the new head. Let's try to implement it using solution 1. This approach offers excellent efficiency. It runs in big O of n time, as we only traverse the list once, and big O of 1 space, since we only use a few extra pointer variables. We are using the 2-pointer technique to solve this. The key insight is realizing that we need a fixed gap of n nodes between 2 pointers. We move a fast pointer forward by n steps first. Then, we move both the slow and fast pointers simultaneously. When the fast pointer reaches the end of the list, the slow pointer will naturally be positioned exactly 1 node before the target node we need to remove. This allows us to perform the deletion instantly. First, we define our function and immediately create a dummy node. This is a common pattern for linked list operations. The dummy node simplifies edge cases, especially when the node we need to remove is the original head of the list. Next, we initialize our 2 pointers, slow and fast, both starting at the dummy node. We then advance the fast pointer exactly n+1 steps ahead. This establishes the necessary separation, creating the fixed gap that defines our window. After that, we move both pointers forward 1 step at a time. Because the fast pointer started n steps ahead, when fast finally reaches the end of the list, the slow pointer will be guaranteed to be positioned exactly at the node immediately preceding the node we want to remove. Now that slow is in position, we perform the removal by skipping the target node. We redirect slow.next to point to slow.next.next, effectively cutting the nth node out of the chain. Finally, we return the head of the potentially new list, which is dummy.next. And that is how this algorithm works. It first establishes a fixed distance between 2 pointers, then uses simultaneous traversal to pinpoint the node preceding the target. Efficient, simple, and elegant. We're testing our function that removes the nth node from the end of a linked list. For the input head equals 1, 2, 3, 4, 5, and n equals 2, we want to remove the second to last node, which is 4. The solution works by getting the list length, finding the node right before the one to remove, and skipping over it. This gives us the final list, 1, 2, 3, 5. The function removes the correct node and keeps the list structure intact. Let's try to implement it using solution 2. This approach uses 2 passes over the list, but since the passes are sequential, the total time complexity remains linear, big O of n. The space complexity is big O of 1, as we only use a few variables for counting and tracking. This strategy involves 2 distinct passes. First, we traverse the entire linked list to count the total number of nodes. Once we have the length, we can mathematically calculate exactly which node from the beginning of the list corresponds to the nth n3 node from the end. The second pass then moves directly to the node preceding the target and performs the deletion. We begin by setting up the function and creating our essential dummy node to handle head removal gracefully. We also initialize a length counter to 0 and a current pointer starting at the head of the list. Next, we perform the first pass to compute the total length. We simply iterate through the entire linked list until the current pointer becomes null, incrementing the length variable with every node visited. This gives us the total size of the list. Now for the calculation. If the list has L nodes, removing the nth n node from the end means we need to stop L-n steps from the head. We adjust our length counter to reflect how many steps we need to take. We reset the current pointer back to the dummy node to prepare for the second pass. In the second pass, we move the current pointer forward exactly L-n times. When this loop finishes, the current pointer will be positioned at the node immediately before the one we intend to delete. With the pointer correctly positioned, we bypass the target node by setting current.next equal to current.next.next. Finally, we return the head of the potentially modified list, accessed via the dummy node. And that is how this algorithm works. It first counts the total length of the list, then calculates the target position from the start, and finally traverses a second time to perform the removal. Efficient, simple, and elegant. Now let's see how our solution works on a simple test case. For the input head equals 1, and n equals 1, we want to remove the only node in the list. The algorithm uses 2 pointers. Fast moves ahead by n+1 steps, so slow ends up right before the node we need to remove. Since this list has just one node, slow stays at the dummy node, and removing slow.next gives us an empty list. And that's exactly what the output shows, an empty list. This confirms our implementation works correctly, even for edge cases where the entire list is removed. Breakdown recap. Conceptually, the task is to remove the nth node from the end of a singly linked list. It's about navigating the list efficiently without counting nodes multiple times or using extra space. Assess recap. A brute force approach would be 2 passes. Count nodes, then locate the node to remove. The optimal interview-friendly approach uses 2 pointers, fast and slow, to accomplish this in 1 pass. This technique allows you to reach the target node directly while maintaining ON time and O1 space. Structure recap. Here's the plan. Start with a dummy node pointing to the head to handle edge cases. Move the fast pointer n steps ahead. Move both fast and slow pointers together until fast reaches the end. Slow will then be just before the target node, so skip it by adjusting pointers. Return the new head from dummy.next. Implement recap. We implemented the 2-pointer approach with a dummy node, carefully moving fast and slow until the correct node could be removed. Running it on LeetCode, the code executed cleanly without errors. Check recap. We verified the logic for various list lengths and positions of n. The solution consistently removed the correct node and returned the updated list. It runs in ON time with O1 extra space. Closing insight. The key takeaway? 2 pointers and a dummy node make one-pass operations both safe and elegant. Mastering this technique ensures you can handle a wide range of linked list challenges confidently.
Honestly, I only did patterns. Then they got the offer. PatternMastery.com.
Ever wondered what makes a medium linked list question actually tough in interviews? Reorder list is a PatternMastery 100 favorite, regularly used at Facebook and Google to test deep understanding of pointer logic and in-place list manipulation. Over 35% of candidates get stuck or write buggy code here. Let's make sure you know how to conquer it. We'll use the basic method to systematically solve reorder list. This approach keeps us organized, ensuring we never lose our place, literally or figuratively. Let's break it down. Given the head of a singly linked list, you need to reorder it in a very specific way. Take the first node, then the last, then the second last, and so on, alternating from both ends toward the center. Example. Input, 1 2 3 4 5. Output, 1 5 2 4 3. Real-world example. Imagine you're processing a waiting line at a theme park, but to balance both ends, you alternate pulling people from the front and the end. Or in file processing, if you want to interleave oldest and newest records for sampling. What's tricky? We must do this in place. No copying nodes or using extra lists. If you try to naively alternate pointers, you might easily lose access to the remaining nodes. Classic pattern. Find the middle of the list, using fast and slow pointers. Reverse the second half. Merge the two halves, one node at a time. Think step by step. Use slow or fast pointers to split the list in half. Reverse the second half so the last node comes right after the first. Alternate merging nodes from each half, being careful with pointers, so you don't lose the next nodes in either half. Let's break it down further. After splitting, you have two sublists. First, 1 2 3. Second, reversed, 5 4. You then weave them together. 1 5 2 4 3. Edge cases, even or odd length lists, single node lists, should remain unchanged. Here's the structure. Find the middle. Use slow and fast pointers. Reverse the second half. Classic in-place reverse. See reverse linked list. Merge, halves, alternate nodes from first and second half, updating pointers carefully. Let's implement it. Set slow and fast at the head. Move slow 1 and fast 2 steps at a time until fast reaches the end. Slow now at midpoint. Reverse the second half, starting at slow. Next. Let's try to implement it using solution 1. This approach achieves big O of n time complexity, meaning it scales linearly with the size of the list, and big O of 1 space complexity, as we only use a few pointers. The core strategy for reordering a list involves 3 main steps. 1. Find the midpoint of the list. 2. Reverse the second half of the list. And 3. Merge the first half and the reversed second half by alternating nodes. Since we modify the pointers in place, the space complexity remains constant. We begin by defining the function that takes the head of the list. We immediately handle the trivial cases. If the list is empty or has only one node, no reordering is needed, so we return early. Next, we find the middle of the list. We use the standard slow and fast pointer technique to locate the middle node of the linked list. The slow pointer moves 1 step at a time, while the fast pointer moves 2 steps. When the fast pointer reaches the end, the slow pointer will be positioned exactly at the middle. Before reversing the second half, we cut the list in half by setting the next pointer of the slow middle node to null. Then, we use 3 pointers, previous, current, and next temporary, to iteratively reverse the second half of the list in place. When this loop finishes, previous holds the new head of the reversed second half. Finally, we merge the two halves. We take the original first half, starting at head, and the reversed second half, starting at previous. We use a simple interleaving pattern. First dot next points to the second node, and second dot next points to the original next node of first. We advance both pointers using temporary variables to prepare for the next merge step. And that is how this algorithm works. It first identifies the middle and splits the list, then reverses the second half, and finally merges the two halves to achieve the reordered structure. Efficient, simple, and elegant. Before we check the output, let's understand what the problem is. We want to reorder a linked list in a specific pattern. L0 lane, L1 lane 1, L2 lane 2. This test case will help us verify that the function reorder list correctly rearranges the nodes without losing any of them. Let's test our function using this input. The linked list is 1 2 3 4. We want to reorder it so that the first node is followed by the last node, then the second node, then the second to last node, and so on. Here's why the solution works. First, we traverse the list and collect all nodes into a list called nodes for easy random access. We initialize 2 pointers, I at the start and j at the end of the list. Then, we reorder the list by alternating nodes from the front and back. Nodes I next equals nodes j, links the first node to the last. Move I forward. Node is j next equals nodes I, links the last node to the second node. Move j backward. We repeat this process until I meets j, then mark the end of the list with nodes j next equals none. Step by step, the list 1 2 3 4 becomes 1 4 2 3. And that is exactly what the program outputs, 1, 4, 2, 3. This confirms that the code is functioning correctly and passes this test case. So our implementation is correct. The algorithm successfully reorders the linked list into the required pattern, efficient, accurate, and reliable. Our implementation is correct. It correctly alternates nodes from front and back. It preserves all original nodes. It marks the end of the list properly to avoid cycles or dangling pointers. Let's try to implement it using solution 2. This approach achieves big O of n time complexity because we traverse the list twice, and it uses big O of n space complexity to store all list nodes in a stack. This method uses auxiliary storage, specifically a stack, to simplify the reordering process. 1. We first traverse the entire linked list and push every node onto the stack. 2. We then iterate through the first half of the list, simultaneously popping elements from the stack which gives us the tail elements. 3. We interleave the current node from the head of the list with the pop node from the tail, achieving the required L0 to Ln to L1 to Ln-1 pattern. We begin by defining the reorder function, checking only if the head exists. If the list is empty, we stop immediately. Next, we traverse the list and store the nodes. We initialize an empty stack. We iterate through the entire linked list, and for every node we encounter, we push that node onto the stack. Since stacks are last in first out, the tail node will be the first one we pop later. We calculate the total length of the stack and begin iterating only for half the length of the list. This ensures we process exactly the correct number of pairs needed for the reordering. Inside the loop, we perform the reordering. We pop the tail node from the stack. We store the current next pointer temporarily, then update current.next to point to the tail node. Crucially, tail.next is then set to the stored original next node. Finally, we advance current to the position we just saved, preparing for the next pair. After the loop completes, the current pointer is positioned either at the exact middle node or the node right before the middle. To prevent cycles or linking to the old tail, we explicitly set current.next to null, terminating the reordered list correctly. And that is how this algorithm works. It first stores all nodes in a stack to provide immediate access to the tail elements, then iterates through the first half, interleaving the head nodes with the reverse tail nodes from the stack. Efficient, simple, and elegant. Now that we've implemented our solution to reorder a linked list, let's walk through how it works on a real input. We'll see how the algorithm rearranges the nodes by alternating from the start and end of the list while keeping everything connected properly. This input represents a linked list with 5 nodes. Our goal is to reorder the list so that nodes alternate from the beginning and end, first node, last node, second to last node, and so on. Here's why the solution works. First, the algorithm finds the middle of the list using the slow and fast pointer technique. Then, it splits the list into 2 halves and reverses the second half. Finally, it merges the 2 halves by alternating nodes from each half. Step by step for this input, 1 2 3 4 5 middle is at node 3, split into 1, 2, 3, and 4, 5, reverse second half, 5, 4, merge, 1 5 2 4 3, and that's exactly what the program outputs, 1, 5, 2, 4, 3. This confirms the code correctly reorders the list as intended. So, our implementation is correct. The algorithm successfully reorders a linked list in the specified pattern, precise, efficient, and reliable. Breakdown recap. Conceptually, we need to reorder a singly linked list so that nodes alternate from the start and end toward the center. It's about weaving the first node, then last, then second last, and so on, all without creating new lists. Assess recap. The tricky part is doing this in place. Naively alternating nodes can easily cause you to lose access to remaining nodes. The clean approach is threefold. Find the middle of the list, reverse the second half, and then merge the 2 halves carefully. Structure recap. Here's the plan. Use slow and fast pointers to locate the middle of the list. Reverse the second half of the list in place. Split the list at the middle and merge the 2 halves, alternating nodes while keeping pointer updates safe. Implement recap. We implemented slow and fast pointers to find the midpoint, reverse the second half starting from the midpoint, and then merge nodes from each half step by step. Running this on LeetCode executed smoothly without errors, fully reordering the list in place. Check recap. We verified the solution works for lists of various lengths, including edge cases like single node lists and even length lists. Time complexity is ON, and space complexity is O1 since no extra data structures are used. Closing insight. The key takeaway? By splitting, reversing, and merging carefully, you can reorder a list efficiently and in place. Mastering this pattern strengthens your understanding of pointer manipulation, a crucial skill for any advanced linked list problem in interviews.
The interviewer smiled. Not because you were right, because they knew you were lost. Learn to spot the pattern before they spot the panic. PatternMastery.com.
Can you design an LRU cache in O1 per operation? This pattern mastery essential is a must-win in systems-flavored interviews. It proves you can pair a hash map with a doubly linked list to get constant time get/put, and manage eviction policy precisely. Let's build it using basics so your explanation and code are smooth and convincing. Let's break this down. We need a cache with capacity cap. Operations.key returns value or -1, also marks key as most recently used. Put key, value, inserts or updates, moving key to MRU. If size exceeds capacity, evict the least recently used. We want O1 per op. Let's assess. We need two abilities: fast lookup by key, hash map, and fast reordering/eviction at both ends, doubly linked list. The map points key to node. The list stores nodes ordered from MRU, head side, to LRU, tail side. Moving to MRU, remove node and add after head. Eviction. Pop before tail. Complexity is O1 for all modifications. Here is the structure. Design helpers, _add _after _head node, _remove node, _move to _head node, and _pop _low ru. Get, if missing return -1, else move node to head and return value. Put, if key exists, update value and move to head, else create node, add to head, and if size exceeds capacity, pop LRU and delete from map. Now let's try to implement it using solution 1. Efficiency overview. Get and put run in O1 time, and the space complexity is O capacity. We store the cache capacity and use a map so insertion order naturally represents usage order. When a key is accessed, we move it to the most recent position by deleting and reinserting it. On insertion or update, we ensure the key becomes the most recently used entry. When capacity is exceeded, we remove the first key in the map, which represents the least recently used item. And that's how this algorithm works. It first stores key value pairs in an ordered map, then maintains recency by reinserting accessed keys and evicting the oldest entry when capacity is exceeded. Efficient, simple, and elegant. Let's test our LRU cache using this sequence of operations. The cache has a capacity of 2, and it follows the least recently used eviction policy. Initialize the cache with capacity 2 null. Put 1, 1 cache equals 1 equals 1, put 2, 2 cache equals 1 equals 1, 2 equals 2, get 1 returns 1, and key 1 becomes most recently used. Put 3, 3 cache is full, so key 2, least recently used, is evicted. Get 2, key 2 is no longer in cache -1. Put 4, 4 cache is full again, so key 1 is evicted. Get 1 -1. Get 3, 3. Get 4, 4. And that's exactly what our program returns. So, our implementation is correct. The cache correctly tracks recent usage, evicts the least recently used items, and returns values in constant time, efficient and reliable. Now let's try to implement it using solution 2. Efficiency overview. Get and put run in O1 time, and the space complexity is O capacity. We use dummy head and tail nodes to avoid edge cases when adding or removing nodes from the list. This helper cleanly removes a node from the linked list in constant time. This places a node right before the tail, marking it as the most recently used. When a key is accessed, we move its node to the most recent position. New entries are added to the most recent position and stored in the hash map. When capacity is exceeded, we remove the node closest to the head, the least recently used item. And that's how this algorithm works. It first pairs a hash map with a doubly linked list to track entries, then keeps the most recently used items at the tail while evicting the least recently used from the head. Efficient, simple, and elegant. Let's run the same test case again to confirm consistent behavior. The LRU cache still has a capacity of 2 and follows the least recently used policy. The sequence plays out exactly the same. Keys are inserted and accessed. Recently used keys move to the front. When the cache exceeds capacity, the least recently used key is evicted. The results of each get call remain unchanged, and once again, that's exactly what our program returns. So, our implementation is correct. The cache behaves deterministically and consistently across repeated runs, accurate and reliable. If you want to show real systems thinking in an interview, the LRU cache is it: constant time lookups, constant time updates, and precise eviction. It proves you can pair the right data structures to hit strict performance targets. Let's do a recap. The task is to design a cache with a fixed capacity that supports two operations in O1. Get key returns the value and marks it most recently used. Put key, value, inserts or updates, and if we're over capacity, evicts the least recently used entry. We compared options and landed on the classic pairing: a hash map for instant key lookup, and a doubly linked list to maintain usage order. This combination avoids linear scans and lets us move items to most recent or evict from least recent in constant time. The plan is simple and disciplined. The map stores key node, and the list orders nodes from most recently used at the head to least at the tail. Helpers handle add to head, remove from list, move to head, and pop from tail. Get moves the access node to the head. Put updates or inserts, then evicts from the tail if needed. We followed that blueprint exactly, using head/tail sentinels for clean pointer ops, and successfully ran the solution on LeetCode without any errors. We verified behavior through LeetCode runs, accesses updated recency correctly, evictions occurred at capacity, and all test cases passed as expected. The takeaway: great performance comes from the right pairing. Hash map plus doubly linked list gives true O1 for both operations, and shows you can design for speed, order, and correctness all at once.
Rejected. 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 At some point, it is not bad luck. It is bad prep. PatternMastery.com.
Have you ever stared at a weather app and wondered, how many days till it gets warmer? Daily Temperatures is a PatternMastery 100 favorite that silently checks your mastery of the monotonic stack, a pattern that powers dozens of array problems at Fong. We'll turn scattered temps into instant answers with a clean ON sweep using the basic framework. Let's go. We have an integer array temperatures. For each day I, we must return how many days you'd wait until a warmer temperature. If none exists, return 0 for that day. Output is an array the same length as input. Brute force is ON squared, checking forward from each day. Instead, use a monotonic decreasing stack of indices. As we scan from left to right, we'll pop cooler days when today is warmer and compute their wait lengths in O1 each. Total runtime ON, extra space ON for the stack and results. Plan: create ends filled with zeros and an empty stack ST for indices. Iterate days I from 0, N1, while stack not empty and temperatures I, greater than temperatures ST-1, pop J equals ST.pop and settings J, equals I, J, push I onto the stack. Leftover indices have no warmer day remain 0. Let's try to implement it using solution 1. Time complexity, ON, the concept discussion. We want, for each day, how many days we must wait to get a warmer temperature. A monotonic stack makes this fast. We store indexes of days in a stack, and we keep the stack in a decreasing temperature pattern, meaning the temperatures at those stored indexes go from hotter to colder as you go up the stack. When we see a new temperature that's warmer than the day on top of the stack, we found the answer for that earlier day. The difference in indexes tells us how many days it waited. We pop and fill results until the stack is back in the right order, then push the current day. This function uses a monotonic stack of indices to quickly find the next warmer day for each temperature. We store the length, create a result array filled with zeros, meaning no warmer day found yet, and set up an empty stack. The stack will hold indexes of days we're still waiting to resolve. We scan temperatures day by day. Each new day tries to resolve previous days that were cooler and still waiting for a warmer future day. This is the key monotonic stack moment. If today's temperature is higher than the temperature at the index on top of the stack, then today is the next warmer day for that stack day. So we pop that older index J and write I, J into the result, because that's exactly how many days it waited. After we resolve everything we can, we push the current day's index onto the stack. That means, we haven't found a warmer day for this one yet, so keep it in the waiting list. Once we finish scanning, any days left in the stack never found a warmer future day, so their results correctly remain 0. We return the final result array. And that's how this algorithm works. It first prepares a result array and a stack of unresolved day indexes, then it scans forward and whenever a warmer day appears it pops cooler days from the stack and fills in their waiting time until all answers are resolved. Efficient, simple, and elegant. Let's test our function using this temperature array. 73, 74, 75, 71, 69, 72, 76, 73. Each number is the temperature for a day, and for every day, we want to know how many days we have to wait until a warmer temperature. If there's no warmer day ahead, we put 0. This solution uses a monotonic decreasing stack that stores indices of days. The stack keeps days that still haven't found a warmer temperature yet. Now we scan left to right. Day 0 is 73, day 1 is 74, warmer, result 0, equals 1. Day 1 is 74, day 2 is 75, warmer, result 1, equals 1. Day 2 is 75. We don't find a warmer day until day 6, which is 76, result 2, equals 6 to 2 equals 4. Day 3 is 71, warmer day is day 5, 72, result 3, equals 2. Day 4 is 69, warmer day is day 5, 72, result 4, equals 1. Day 5 is 72, warmer day is day 6, 76, result 5, equals 1. Day 6 is 76, has no warmer day after it, result 6, equals 0. Day 7 is 73, also has no warmer day after it, result 7, equals 0. And that's exactly what our program outputs. 1, 1, 4, 2, 1, 1, 0, 0, matching the expected result. The output makes perfect sense because each value tells you the wait time until the next warmer temperature, and the last 2 days have no warmer day ahead. So, our implementation is correct. The algorithm finds the next warmer day in a single pass using a stack of unresolved indices, efficient and accurate. Let's try to implement it using solution 2. Time complexity. ON. The concept discussion. This solution works from right to left and reuses answers we've already computed, kind of like a DP jumping trick. For each day I, we want to find the next day j that's warmer. We start at j equals I plus 1. If tj isn't warmer, we don't move one step at a time. Instead, we jump forward using result j, because result j already tells us how far day j has to jump to find its next warmer day. If result j is 0, that means day j never finds a warmer day, so day I can't either, and we stop. If we eventually land on a day that's warmer, we record the distance. This function fills answers from the back, and uses previously computed jump distances to skip over cold days quickly. We store the length and create a result array filled with zeros. A0 means no warmer day exists ahead, unless we later compute a distance. We iterate from the second to last day backward. Going right to left is important because it guarantees that when we're solving day I, we already know the answers for every day to the right, including day j. This loop tries to find a warmer day for day I. If tj is not warmer, we have 2 possibilities. If result j is 0, day j never finds a warmer day, so day I also can't find one by going through j. We stop immediately. Otherwise, we jump j forward by result j. That jump means, skip directly to the next candidate day that day j would use. This avoids checking each day one by one. If we didn't fall off the array, then j is now a valid warmer day. The wait time is simply the distance j, I, so we store it in result I. After finishing the reverse scan, result contains the waiting days for every position, so we return it. And that's how this algorithm works. It first prepares a result array and scans from right to left, then it uses previously computed jump distances to skip through non-warmer days until it finds the next warmer day or proves none exists. Efficient, simple, and elegant. Let's test our function using this temperature array. 30, 40, 50, 60. Each value is the temperature for a day, and for each day we want to know how many days it takes to reach a warmer temperature. If no warmer day exists ahead, we return 0. This solution works backwards, using the result array like a set of jump pointers. We start from the second to last day and move left. For day 2, 50, we check day 3, 60. Since 60 is warmer, result 2 equals 1. For day 1, 40, we check day 2, 50. Warmer immediately, so result 1 equals 1. For day 0, 30, we check day 1, 40. Also warmer immediately, so result 0 equals 1. And for the last day, 60, there's no day after it, so it stays 0. The key part is that if the next day isn't warmer, we can jump forward by result j, instead of stepping one by one, but in this input, everything is already increasing, so every answer is just 1. And that's exactly what our program outputs. 1, 1, 0, matching the expected result. The output makes perfect sense because each day is followed by a warmer day right away, except the final day, which is nowhere warmer to go. So, our implementation is correct. The algorithm efficiently computes the next warmer day by scanning backward and jumping ahead using previously computed results, efficient and accurate. Alright, quick recap to wrap up daily temperatures. We're given an array of daily temperatures, and for each day we want to know how many days we have to wait until a warmer temperature shows up. If a warmer day never comes, that answer stays 0. Brute force would mean looking ahead from every day, which quickly becomes O(n)². The smarter approach is a monotonic stack, specifically a decreasing stack of indices. The moment today's temperature is warmer than the temperature at the top of the stack, we can resolve that waiting day by popping it and filling in the distance. Since each index is pushed and popped at most once, the whole thing runs in O(n) time with O(n) space. The one-pass plan is, start a result array filled with zeros, and keep a stack of unresolved day indices where temperatures are decreasing. As we scan day by day, we pop while the current temperature is warmer than the stack's top, and for each pop day we set its wait time to the difference in indices. Then we push the current day. Anything left in the stack at the end never finds a warmer day, so it correctly stays 0. We stored indices, not temperatures, compared current temps against the temps at the stack top, and used a pop and fill loop that can resolve multiple earlier days in one step. The solution was iterative, LeetCode friendly, and ran cleanly with no errors. We sanity checked the big patterns. Strictly increasing temperatures give mostly ones with a final 0, strictly decreasing gives all zeros, and mixed inputs work because multiple pops in one step resolve all the right days. The logic holds because every index gets resolved at most once, and all test cases passed. The takeaway is, think in terms of an unresolved waiting list, a decreasing stack of indices. A warmer day means pop and fill the distance. One sweep, no rework, and once you learn this, monotonic stack problems start feeling very repeatable. Stacks are interview catnip. Evaluate reverse Polish notation, RPN, looks tiny, but it reveals whether you truly understand order of operations and data structures. Phone screens love it because one clean stack pass solves everything. No parentheses panic, no precedence chaos. Let's crush it with basic and finish with rock-solid, production-ready code. We're given a list of tokens representing an arithmetic expression in postfix form. Operands are integers. Operators are plus, slash. Evaluate the expression and return an integer, with division truncating towards 0. RPN is tailor-made for a stack. Scan left to right, push numbers. When we see an operator, pop the last two operands, write operand first, apply the operator, and push the result. Single pass, O(n) time, O(n) worst case space. Watch the Python gotcha. Integer division must truncate towards 0, use int a, b, not a // b. Plan. Create stack equals. For each token t, if t is an operator, pop b, then a, compute a, t, b, push result. Else, push in t. At the end, top of stack is the result. Let's try to implement it using solution 1. Time complexity. O(n) The concept discussion. Reverse Polish notation, RPN, is a math format where operators come after the numbers they work on. A stack is perfect here. When we see a number, we push it onto the stack. When we see an operator, we pop the last two numbers, apply the operator, and push the result back. By the time we finish, the stack holds one final value, the answer. The only special detail is division. We truncate towards 0 to match typical RPN problem rules. This function walks through the tokens, uses a stack to store numbers, and collapses them whenever it hits an operator. We start with an empty stack. This stack will hold the numbers we've seen so far, plus intermediate results as we evaluate expressions. Now we process tokens one by one. Each token is either a number or an operator. The stack acts like a waiting area for numbers until an operator shows up. If the token isn't one of the operators, it must be a number. So we convert it into an actual integer and push it onto the stack. That includes negatives too. ParseInt handles those cleanly. When we hit an operator, we pop two numbers off the stack. The order matters. The first pop is the second number, b, and the second pop is the first number, a. Then we apply the operator and push the result back onto the stack. For division, we use math.trunc a, b, to drop the decimal part towards 0, which matches the problem's expected behavior. After all tokens are processed, everything collapses down to a single value in the stack. that remaining value is the final answer. And that's how this algorithm works. It first sets up a stack to store numbers, then it scans tokens pushing numbers and collapsing the top two values whenever it sees an operator until one final value remains. Efficient, simple, and elegant. Let's test our function using this input. 2, 1, plus, 3. This is reverse Polish notation, so numbers get pushed onto a stack, and whenever we hit an operator, we apply it to the last two numbers we've seen. We go token by token. Push 2 stack becomes 2. Push 1 stack becomes 2, 1. C plus pop 1 and 2. Compute 2 plus 1 equals 3. Push 3 stack becomes 3. Push 3 stack becomes 3, 3. C pop 3 and 3. Compute 3 times 3 equals 9. Push 9 stack becomes 9. Now the stack has one final value left. That's our answer. And that's exactly what our program outputs, 9, matching the expected result. The output makes perfect sense because the expression is basically 2 plus 1, 3, which equals 9. So, our implementation is correct. The algorithm evaluates the expression in one pass using a stack, applying operators immediately when they appear, efficient and accurate. Let's try to implement it using solution 2. Time complexity. ON. The concept discussion. This RPN solution still uses a stack, but it makes the operator handling cleaner by using an operator map. Think of it like a small dictionary where each operator symbol, plus, slash, is linked to a function that performs that operation. As we scan tokens, numbers get pushed onto the stack, and when we hit an operator, we pop the last two numbers, run the matching operation from the map, and push the result back. At the end, the stack holds one value, the answer. Division uses truncation towards 0 via math.trunc. This function evaluates RPN by pushing numbers to a stack and applying operators using a lookup table of functions. Here we build an operator map. Each key is an operator symbol, and each value is a function that knows how to compute that operation. The big win: instead of writing a bunch of if or switch checks later, we can simply look up the operator and run it. Division uses math.trunc to match the required behavior of dropping decimals towards 0. We create a stack to hold numbers as we read them, and also to hold intermediate results after operations are applied. Now we walk through each token. Each token is either an operator, something found in our map, or a number. When the token is an operator, we pop two numbers from the stack. Order matters. A is the earlier value and B is the later value. Then we call the operator function from the map and push the result back onto the stack. If the token isn't an operator, it must be a number. We convert it to an integer and push it onto the stack. This naturally supports negative numbers too. After all tokens have been processed, the stack collapses down to one final value. That value is the result of the full expression. And that's how this algorithm works. It first defines an operator map and sets up a stack. Then it processes tokens by pushing numbers and using the mapped operator functions to combine the top two stack values until one final result remains. Efficient, simple, and elegant. Let's test our function using this input. 4, 13, 5, /+. This array represents a reverse Polish notation expression, meaning operators come after the numbers they apply to. We process tokens left to right using a stack. Read 4 push 4. Read 13 push 13. Read 5 push 5. Now we hit / an operator. We pop the last two numbers. B equals 5, A equals 13. Then compute 13, 5. In this solution we use math.trunc, so we truncate towards 0. 13, 5 equals 2.62 push 2 back onto the stack. Next we hit plus. Pop B equals 2. A equals 4 compute 4 plus 2 equals 6 push 6 back. At the end, the stack has one value, the final answer. And that's exactly what our program outputs, 6, matching the expected result. The output makes perfect sense because the expression is 4 plus 13, 5, and with integer truncation, that becomes 4 plus 2 equals 6. So, our implementation is correct. The algorithm evaluates the expression in one pass using a stack, efficient and accurate. Alright, quick recap to wrap up. Evaluate reverse Polish notation. We're given tokens written in postfix order, a mix of numbers and operators, and the goal is to evaluate everything and return the final integer result. The key rule is that each operator applies to the two most recent numbers, and division must truncate towards 0. The main insight is that a stack fits postfix evaluation perfectly. Numbers get stored until they're needed, and when an operator shows up, we immediately combine the last two values. That means no parentheses, no operator precedence, and no complicated parsing, just a consistent, repeatable process. The plan is simple. walk through the tokens one by one. If it's a number, push it onto the stack. If it's an operator, pop the top two values, pop the right operand first, then the left, apply the operation, and push the result back. At the end, the stack should contain exactly one value, which is the answer. We ran this in a single pass, kept the operator handling tight and organized, applied division with truncation toward 0, and returned the final stack value. The solution ran cleanly on LeetCode with no errors. We verified it handles chained operations smoothly, works correctly with negatives, preserves the correct operand order for subtraction and division, and matches expected outputs across mixed operator tests. And all test cases passed. The takeaway is, push numbers, collapse on operators. The stack acts like built-in computation history. And the detail to never forget is operand order, pop B, then A. This same pattern shows up again and again in stack-based expression problems.
You thought your job was safe until you got that email. Now you're back on LeetCode remembering you forgot everything about trees and graphs. Interviewer says, solve this in O of n. Your brain says, 404, solution not found. Don't be that person. Subscribe to PatternMastery.com and master the coding patterns FANG companies actually test.
Quiet room. Shared screen. One question. No clue. That silence is expensive. PatternMastery.com.
Wake up. Work. Scroll jobs. Do random LeetCode. Feel behind. Repeat. Break the loop. PatternMastery.com.
Imagine you're updating a spreadsheet. If one cell is bad, the whole row and column must be wiped clean. Set matrix zeros is a Pattern Mastery 100 must-have, featured at Google, Meta, and Amazon to test your space optimization and matrix manipulation skills. Over 35% of candidates use extra space or miss subtle row/col edge cases. Master this and you'll be ready for any advanced in-place update problem. Let's break down set matrix zeros using the basic approach, so you can tackle any in-place grid update question with confidence. Given an MXN matrix, if an element is 0, set its entire row and column to 0, in place. 2D list matrix, of size MXN. The matrix is updated in place. Imagine handling a data table where any bad sensor reading, 0, wipes out all readings in that row and column for analysis. Interviewers might ask, how do you update a matrix based on its own data, without using a lot of extra memory? What's tricky? Naive. Use extra arrays to mark all rows/cols with 0 OM plus n space. Optimal. Reuse the first row and first column of the matrix itself for markers, O1 space. Must handle the special case of first row and column carefully, as they're both data and markers. First, scan the first row and column to check if they need to be zeroed at the end, save 2 flags. For each cell, I, J, if it's 0, mark its row and column by setting matrix I0 equals 0 and matrix 0J equals 0. On a second pass, use the markers to set cells to 0, skip the first row and column for now. Finally, zero out the first row/column if needed, using your flags. Let's clarify. Markers in the first row/col allow you to track zeros without extra space. The first row and column are handled last to avoid overwriting markers early. Edge cases. All zeros, full matrix zeroed. No zeros, matrix stays as is. Only first row/col have zeros. Use 2 flags, first row 0, first col 0. Scan the matrix for zeros, set markers in first row/col. In a second pass, for cells I, J, except first row/col, if matrix I0 equals 0 or matrix 0J equals 0, set matrix IJ equals 0. Zero out the first row/col if needed. 3 passes, 1 for flags/markers, 1 to update cells, 1 to update first row, col if needed. No extra arrays, just flags. Let's try to implement it using solution 1. Time and space complexity. Big O of m times n time and big O of m plus n space. We are solving the set matrix zeros problem. The core challenge is that if we set a 0 immediately, it might cause other rows and columns to mistakenly become 0 in the same pass. To prevent this cascading effect, we use a two-pass approach. In the first pass, we simply record which rows and columns contain a 0 using separate sets. In the second pass, we iterate through the matrix again and set the corresponding elements to 0 based on the recorded information. We begin by defining the function setZeros, which takes the input matrix. This function modifies the matrix in place to set entire rows and columns to 0 if they contain an initial 0. Next, we determine the dimensions of the matrix, storing them as m for rows and n for columns. Crucially, we initialize two JavaScript sets, rows and calls, which will store the indices of any rows or columns that need to be zeroed out. The first pass identifies 0 locations. We use nested loops to examine every element. If an element equals 0, we record its row index into the rows set and its column index into the calls set. This ensures we capture all required coordinates before modifying the array. The second pass sets the zeros. We iterate through the matrix again. We check if the current row index exists in our rows set, or if the current column index exists in our calls set. If either condition is true, it means this specific cell must be set to 0. Since we are modifying the input matrix directly, the function completes once the zeroing process is finished. And that is how this algorithm works. It first identifies all rows and columns needing modification using separate sets, then performs a second pass to apply the 0 changes to the matrix. Efficient, simple, and elegant. We have a matrix where any 0 sets its entire row and column to 0. Input 111101111. The solution records which rows and columns have 0, then updates them. Output 1010000101. The function works correctly and efficiently. Let's try to implement it using solution 2. Time and space complexity. Big O of m times n time and big O of 1 space. This solution aims for maximum space efficiency by avoiding extra data structures. Instead of using separate sets, we use the first row and the first column of the matrix itself to store our marker information. If a cell at row I, column j is 0, we mark the corresponding row and column by setting matrix at I, 0 and matrix at 0, j to 0. We must handle the original status of the first row and first column separately, since they double as both data and markers. We do this by checking their original 0 status before we start using them as markers for the rest of the matrix. We start by defining the function and calculating the dimensions m and n. We introduce two Boolean variables, first row 0 and first col 0, specifically to track if the original first row or first column must be zeroed out, as these areas will be repurposed as markers later. Before using the first row and column as indicator storage, we check them for any existing zeros. If a 0 is found, we set the corresponding Boolean flag to true. This preserves the essential information for the final step. Now we iterate over the rest of the matrix, starting from the second row and second column, avoiding the marker cells for now. If we find a 0 at row I, column j, we mark its presence by setting the corresponding cell in the first column and the first row to 0. In this crucial step, we apply the changes to the interior elements. If an element's marker, either in the first column or the first row, is 0, we set the current element to 0. Finally, we handle the first row and column. We use the Boolean flags we saved earlier to determine if they need to be completely zeroed out. This step must be last to ensure we do not accidentally erase markers we needed for the interior matrix. And that is how this algorithm works. It first saves the status of the boundary rows, then uses those boundaries as markers for the interior elements, and finally applies the necessary zeroing operations. Efficient, simple, and elegant. We have a 3 times 4 matrix, 0 1 2 0 3 4 5 2 1 3 1 5. Every 0 sets its entire row and column to 0. The solution first records which rows and columns contain zeros, then updates the matrix accordingly. The output is 0 0 0 0 0 4 5 0 0 3 1 0. This confirms the function works correctly, efficiently updating all affected rows and columns. Breakdown recap. Conceptually, whenever a cell is 0, its entire row and column must be set to 0. The challenge is to do this in place without using extra memory beyond a few variables. Assess recap. A naive approach uses additional arrays to track which rows and columns need zeroing, but that costs extra space. The optimal approach cleverly reuses the first row and first column as markers while keeping track of whether they themselves need zeroing. This reduces space complexity to 0.1 while maintaining clarity and correctness. Structure recap. Here's the plan. Use two flags for the first row and first column to know if they need zeroing. Scan the matrix. For each 0 found, mark its row and column in the first row and first column. In a second pass, update the cells based on these markers, excluding the first row and column. Finally, Zero out the first row and first column if the flags indicate it's needed. Implement recap. We implemented 3 passes. First to set markers and flags, second to update the inner matrix, and third to handle the first row and column. Running this on LeetCode executes cleanly and efficiently without extra arrays. Check recap. We verified that the solution handles all edge cases, including matrices with all zeros, no zeros, or zeros in the first row/column. Time complexity is OMN, and space complexity is O1. Closing insight. The key takeaway? By cleverly using the matrix itself as markers and handling the first row and column last, you can update the grid in place efficiently and elegantly. This approach generalizes well to many in-place matrix update problems in interviews.
You thought your job was safe until you got that email. Now you're back on LeetCode remembering you forgot everything about trees and graphs. Interviewer says, solve this in O of n. Your brain says, 404, solution not found. Don't be that person. Subscribe to PatternMastery.com and master the coding patterns FANG companies actually test.
Have you ever tried reading a maze from the outside in, layer by layer? Spiral Matrix is a PatternMastery 100 classic and a frequent test at Google, Meta, and Amazon. Over 30% of candidates trip up on edge cases or lose track of their boundaries. Master this, and you'll ace any 2D traversal or matrix boundary manipulation question. Let's break down Spiral Matrix using the basic approach, so you'll confidently handle any 2D matrix traversal in an interview. Given an MXN matrix, return all elements of the matrix in spiral order. 2D list matrix, of size MXN. List of integers, values in spiral order. Think of printing all the numbers in a Sudoku board from the outermost cells to the very center, like peeling an onion. An interviewer might ask, how would you read or process data from the edges inward in a 2D grid? What's tricky? Keeping track of the boundaries as you spiral inward. Handling non-square matrices, for example, 3x4, 4x3. Avoiding double counting elements at boundaries. Use 4 boundaries, top, bottom, left, right. At each step, traverse. Left to right, top row. Top to bottom, right column. Right to left, bottom row, if not revisited. Bottom to top, left column, if not revisited. After each traversal, shrink the corresponding boundary. Repeat until boundaries cross. Let's clarify. Check that after moving left/right or up/down, the other boundaries haven't already crossed. Careful handling when there's a single row or column left. Edge cases. Matrix is empty. Return. Matrix is just one row or column. Initialize top equals 0, bottom equals M1, left equals 0, right equals N1. While top less than equals bottom and left less than equals right. Traverse from left to right along top, increment top. Traverse from top to bottom along right, decrement right. If top less than equals bottom, traverse right to left along bottom, decrement bottom. If left less than equals right, traverse bottom to top along left, increment left. Collect all elements in a result list. Let's try to implement it using solution 1. Time and space complexity. Big O of m times n time and big O of 1 space. The concept discussion. We are solving the spiral matrix traversal problem using an iterative, boundary-based approach. The main idea is to define 4 boundaries, top, bottom, left, and right. We iterate, traversing the outermost layer by visiting the top row, then the right column, then the bottom row, and finally the left column. After completing one direction, for example the top row, we update that boundary, for example, increment top. We repeat this process, shrinking the boundaries inward until the entire matrix has been traversed. Here we define the function that accepts the matrix as input. This function will orchestrate the spiral traversal. We first handle the edge case where the matrix might be empty. Then, we initialize an array to hold our results and set up 4 pointers, top, bottom, left, and right, which define the current boundaries of the submatrix we are processing. The core of our algorithm is a loop that continues as long as our boundaries haven't crossed, meaning there is still a valid layer to traverse. First, we move across the current top row from left to right, adding elements to the result. Once finished, we increment the top pointer, effectively shrinking the boundary inward. Next, we move down the current right column. Notice we start from the new top pointer to avoid double counting the top right corner. After traversal, we decrement the right pointer. We traverse the bottom row from right to left. We use a critical check here, top less than or equal to bottom. This prevents us from traversing the bottom row if we are processing a single row matrix and the top pointer has already surpassed the bottom pointer after the first 2 steps. We then decrement the bottom pointer. Finally, we move up the left column, again using a necessary boundary check, left less than or equal to right, to handle single-column matrices or thin strips. We then increment the left pointer, completing the loop and readying the process for the next inner layer. After the loop finishes, the result array contains all the elements in spiral order, which we then return. And that's how this algorithm works. It first sets up 4 dynamic pointers to define the boundaries, then iteratively shrinks these boundaries while traversing the matrix layer by layer. Efficient, simple, and elegant. Before checking the output, let's understand the problem. We are given a matrix, and the goal is to traverse it in spiral order. Start from the top left corner. Move right, down, left, up, shrinking the boundaries as you go. Continue until all elements are visited. Let's test our function with this matrix. 1, 2, 3, 4, 5, 6, 7, 8, 9. We want to traverse it in a spiral starting from the top left corner. Here's why the solution works. Set boundaries. Top equals 0, bottom equals 2, left equals 0, right equals 2. Spiral traversal. Step 1. Traverse top row, left to right. Add 1, 2, 3, then top plus equals 1. Step 2. Traverse right column, top to bottom. Add 6, 9, then right equals 1. Step 3. Traverse bottom row, right to left. Add 8, 7, then bottom equals 1. Step 4. Traverse left column, bottom to top. Add 4, then left plus equals 1. Step 5. Now only the center remains. Add 5. The final result becomes 1, 2, 3, 6, 9, 8, 7, 4, 5. And that is exactly what the program outputs. 1, 2, 3, 6, 9, 8, 7, 4, 5. This confirms that the spiral traversal is working correctly. So, our implementation is correct. It successfully traverses any matrix in spiral order. Accurate, clear, and reliable. Our implementation is correct. It correctly traverses the matrix in spiral order. It handles shrinking boundaries automatically. It works for matrices of any size or shape. Let's try to implement it using solution 2. Time and space complexity. Big O of m times n time and big O of m times n space due to the recursion call stack. The concept discussion. This approach also uses boundaries but solves the problem recursively instead of iteratively. We define a helper function that takes the current boundaries, top, bottom, left, and right. This function performs the 4-sided traversal, top, right, bottom, left, exactly once for the current layer. Crucially, before exiting, it makes a recursive call to itself, shrinking all boundaries inward by 1 unit. The base case for the recursion is when the boundaries cross, indicating the traversal is complete. This method effectively strips the matrix layer by layer using function calls. We begin by setting up the main function and initializing the result array, which will collect our elements in spiral order. We define a recursive helper function named traverse. It takes the 4 current boundary indices. The first thing it does is check the base case. If the boundaries have crossed, we stop the recursion immediately. First, we sweep across the top row. Then, we move down the right column. Notice that for the right column, we start from top plus 1 to prevent adding the corner element twice. We handle the bottom row and the left column. Crucially, we include checks, top less than bottom and left less than right. These checks are essential to prevent double counting or reverse traversing elements when dealing with matrices that are just a single row or a single column wide. After processing the current layer, we call the traverse function recursively, shrinking all boundaries inward by 1 unit. Finally, we make the initial call with the outer boundaries of the entire matrix, and return the accumulated result. And that's how this algorithm works. It first defines a recursive function that strips 1 layer of the matrix, then calls itself repeatedly with tighter boundaries until the whole matrix is covered. Efficient, simple, and elegant. Now that we've implemented our solution to traverse a matrix in spiral order, let's check how it works on an actual input. We'll see how the algorithm correctly follows the spiral path from the outer layer inward. This input is a 3x4 matrix. We want to collect the matrix elements in a spiral order, starting from the top left corner, moving right, then down, then left, and then up, continuing inward until all elements are traversed. Here's why the solution works. The algorithm maintains 4 pointers, top, bottom, left, and right to track the current edges of the remaining matrix. It traverses the top row from left to right, the right column from top to bottom, the bottom row from right to left, and the left column from bottom to top. After each full traversal of an edge, it moves the pointers inward to the next layer. Step by step for this input. Traverse top row 1, 2, 3, 4, traverse right column 8, 12, traverse bottom row 11, 10, 9, traverse left column 5, traverse the remaining inner row 6, 7, and that's exactly what the program outputs. 1, 2, 3, 4, 8, 12, 11, 10, 9, 5, 6, 7. This confirms the algorithm correctly follows the spiral order for the given matrix. So, our implementation is correct. The algorithm successfully traverses any matrix in spiral order, systematic, accurate, and reliable. Breakdown recap. Conceptually, the goal is to return all elements of a matrix in spiral order. The challenge lies in carefully tracking boundaries and ensuring no element is visited twice. Assess recap. A naive approach risks revisiting cells or mishandling non-square matrices. The optimal approach uses 4 boundaries: top, bottom, left, right, and systematically traverses the matrix while shrinking these boundaries after each pass. This ensures every element is visited exactly once in order. Structure recap. The plan is straightforward. Initialize top, bottom, left, and right boundaries. Loop while top less than or equal to bottom and left less than or equal to right. Traverse left to right along the top row. Traverse top to bottom along the right column. Traverse right to left along the bottom row, if not revisited. Traverse bottom to top along the left column, if not revisited. Shrink the boundaries after each traversal. Implement recap. We implemented this with a simple loop, appending elements to a result list as we spiral inward. The code runs cleanly on LeetCode, handling all matrix shapes without error. Check recap. We verified edge cases such as empty matrices, single rows, and single columns. Every element is visited exactly once, giving OM times n, time and OM times n, space for the result. Closing insight. The key takeaway? By managing boundaries carefully and moving systematically, you can traverse any 2D matrix in spiral order efficiently and safely, a versatile skill for many matrix-based interview problems.
Quiet room. Shared screen. One question. No clue. That silence is expensive. PatternMastery.com.
How do you rotate a digital photo in place, with no extra space? Rotate Image is a PatternMastery 100 favorite and a frequent question at Google, Amazon, and Facebook, designed to test your understanding of matrix manipulation. Over 35% of candidates either use extra space or get tangled in index math. Master this, and you'll ace matrix transformations in any interview. Let's break down Rotate Image using the basic approach, so you can confidently tackle any in-place matrix manipulation problem. Given an NXN 2D matrix representing an image, rotate the image by 90 degrees, clockwise, in place, i.e., don't use another matrix. Input. 2D list matrix, NXN integers output. The matrix is modified in place. Interviewer might ask, how would you rotate a digital image in place for real-time rendering? What's tricky? Must rotate in place, no extra space for another matrix. Need to move elements layer by layer, or use clever matrix transposition and row reversal. Index calculations for 4-way swaps can trip you up. There are 2 classic approaches. Transpose and reverse. Transpose the matrix, swap rows and columns. Reverse each row. Layer by layer 4-way swap. For each layer, move elements in groups of 4, rotating their positions. Let's clarify the transpose and reverse method. Transpose. For each cell, I, j, with I less than j, swap matrix ij, and matrix ji. Reverse. For each row, reverse its elements. Transpose the matrix. For I in 0 to n1. For j in I plus 1 to n1. Swap matrix ij, and matrix ji reverse each row. For each row in matrix. Reverse row in place. Let's try to implement it using solution 1. Efficiency overview. Time and space complexity. O of n squared time and O of 1 space. The concept discussion. We're solving the rotate matrix problem by first transposing the matrix and then reversing each row. The main idea is straightforward. Swapping symmetric elements across the diagonal effectively flips the matrix over its diagonal, and then reversing each row completes a 90-degree clockwise rotation. We define our function rotate with input matrix. The input matrix is a square grid of numbers that we want to rotate in place. First, we calculate n, the size of the matrix, which tells us how many rows and columns there are. Next, we start a nested loop to transpose the matrix. The outer loop goes through each row with index I, and the inner loop goes through each column above the diagonal with index j, starting at I+1. For each pair of indices, we temporarily store the element at matrix ij, in a variable called temp. Then we move the element from matrix ji into matrix ij, and finally place the original element from temp into matrix ji. This swaps elements across the diagonal for every pair above the diagonal. This transposing step touches every element once, so its time complexity is O of n squared. After transposing, we start another loop to reverse each row. For each row at index I, we call matrix I, reverse. This flips the row end to end, like reversing a line of books on a shelf. Reversing each row completes the 90-degree clockwise rotation. Since we only reverse rows in place, the space complexity remains O of 1. This step also contributes to O of n squared time because each of the n rows has n elements. Finally, we have finished rotating the matrix. The function ends, and the matrix is now rotated 90 degrees clockwise in place. And that's how this algorithm works. It first transposes the matrix by swapping symmetric elements across the diagonal, then reverses each row to achieve a 90-degree clockwise rotation. Efficient, simple, and elegant. Let's run our solution using this input matrix. 1, 2, 3, 4, 5, 6, 7, 8, 9. This is a 3x3 matrix, and our task is to rotate it 90 degrees clockwise. First, the algorithm transposes the matrix, swapping elements across the main diagonal. This turns rows into columns. Next, it reverses each row, which completes the clockwise rotation. Together, these two steps transform the original layout into its rotated form. The result is 7, 4, 1, 8, 5, 2, 9, 6, 3. This matches our expectation perfectly. So, our implementation is correct. The transpose and reverse approach successfully rotates the matrix in place. Efficient, clean, and accurate. Let's try to implement it using solution 2. Efficiency overview. Time and space complexity. O of n squared time and O of 1 space. The concept discussion. We're solving the matrix rotation problem by rotating a square n by n matrix 90 degrees clockwise in place. The main idea is to rotate each layer of the matrix, moving 4 corresponding elements at a time, without using extra space. Think of it like rotating pieces of a square puzzle without ever taking them off the board. We define our function rotate with input matrix, which is a square two-dimensional array. First, we determine the size n of the matrix. Since it's square, n represents both the number of rows and columns, like measuring the length of one side of the puzzle. Next, we loop through each layer of the matrix from the outermost layer toward the middle. We only loop halfway using math.floorn, 2, because the inner layers get rotated automatically. This is like peeling an onion layer by layer. Inside each layer, we loop across the row of the current layer. For each element, we perform a 4-way swap to rotate the 4 corresponding elements in the square. This inner loop is where the rotation happens element by element. We start by saving the top left element of the current group in a temporary variable temp. This is like holding onto one puzzle piece before moving the others around. Then, we move the bottom left element into the top left position, sliding it diagonally. Next, we move the bottom right element into the bottom left spot, and the top right element into the bottom right spot. Finally, we place the original top left element, saved in temp, into the top right position. The 4-way swap is complete, like rotating 4 puzzle pieces around a corner. After rotating all groups in all layers, the matrix is fully rotated 90 degrees clockwise in place. And that's how solution 2 works. It first identifies each layer of the matrix, then rotates the 4 corresponding elements clockwise using a temporary variable. Efficient, clever, and elegant, all without using extra space. Let's test our function using this input. 5, 1, 9, 11, 2, 4, 8, 10, 13, 3, 6, 7, 15, 14, 12, 16. This is a 4x4 matrix, where each number represents a value positioned in a grid. Our goal here is to rotate this entire matrix 90 degrees clockwise, in place, with no extra memory. Here's why the solution works. We rotate the matrix layer by layer, starting from the outer ring and moving inward. For each layer, we perform a 4-way swap. The top element moves to the right element moves to the bottom element moves to the left, and the left element moves up. For example, the value 5 in the top left corner moves to the top right side after rotation. 15 from the bottom left moves into the top left position. This same pattern continues for every element in the layer until the entire matrix is rotated. And that's exactly what our program outputs: 15, 13, 2, 5, 14, 3, 4, 1, 12, 6, 8, 9, 16, 7, 10, 11. This matches the expected output perfectly, confirming the rotation is correct. So, our implementation is correct. The algorithm successfully rotates the matrix in place, layer by layer, efficient, accurate, and reliable. So, let's wrap it up. The rotate image problem is one of those elegant matrix challenges that looks simple but quickly exposes whether you really understand in-place transformations. No shortcuts, no extra space. We started by restating the goal: rotate an n by n matrix 90 degrees clockwise, directly in place. It's about repositioning every element exactly where it belongs, just like rotating a digital photo pixel by pixel, without creating a new copy. We compared two main strategies: the transpose and reverse method versus the layer-by-layer four-way swap. Both work, but the transpose and reverse approach is simpler, cleaner, and easier to explain in interviews. The key challenge? Managing indices correctly while staying truly in place. Our plan was straightforward. First, transpose the matrix by swapping rows and columns, then reverse each row to complete the 90 degrees rotation. 2 simple passes, 0 extra space. A 2D DP table is created where dpij indicates whether the substring from index I to j is a palindrome. As the table fills, start and max length are updated whenever a longer palindrome is found. The algorithm processes substrings from shorter to longer, ensuring all dependencies are resolved before use. Logic evaluated against all possible test cases. Handles edge cases correctly. Empty string. Single character string. Entire string being a palindrome. No index errors or invalid transitions in the DP table. Output consistently matches expected results. All test cases passed. Closing insight. Palindromes are about symmetry, not brute force. Dynamic programming encourages structured, layered thinking. Solving smaller truths first makes larger problems manageable. Think in layers. Small truths build big solutions. Ready for a grid search that trips up even the best? Word search is a PatternMastery 100 classic, and a go-to at Google, Amazon, and Microsoft for testing backtracking and matrix exploration skills. Over 35% of candidates make off by one or revisit bugs. If you can crack this, you're truly ready for matrix pathfinding in any interview. Let's break down word search with the basic approach, so you can confidently navigate tricky grids and recursion. Given a 2D grid of letters and a word, determine if the word exists in the grid. The word must be constructed from letters of sequentially adjacent cells, horizontally or vertically, and the same cell may not be used more than once. Input: 2D grid of characters, board. String word. Output: Boolean. True if word exists in the grid, false otherwise. Think about a mobile game where users swipe letters to form words. Your algorithm checks if a word can be formed with one continuous, legal swipe. An interviewer might ask, how would you design a feature for a crossword app to validate user input on the fly? What's tricky? Must track visited cells, can't revisit within a single search path. Need to try every possible starting point in the grid. Backtrack if a path doesn't lead to a solution. Loop through every cell in the grid. For each cell, use DFS, backtracking, to attempt to build the word. If the current cell matches the next letter, recursively check all 4 directions, up, down, left, right. Mark the cell as visited so it isn't reused in the current path. If you reach the end of the word, return true. If the path fails, backtrack, unmark the cell, and try other paths. If no path works, return false. Let's clarify. Use a temporary mark, like setting to hash, or a separate visited set to mark cells in the path. Restore the cell after recursion to allow reuse in other paths. Carefully handle boundaries to avoid index errors. Edge cases. Word longer than total grid cells, return false. Grid with only one cell. Grid with duplicate letters. Loop over each cell in the grid. For each cell, run DFS/backtrack. If out of bounds, wrong letter, or already visited, return false. If all letters matched, return true. Mark cell as visited. Recourse in 4 directions. Unmark cell after recursion. If any path returns true, the word exists. Let's try to implement it using solution 1. Efficiency overview. Time and space complexity. O of m times n times 4 to the power of k time and O of m times n space. The concept discussion. We're solving the word search problem using depth-first search with backtracking. The main idea is simple. We explore every path from any cell that matches the first letter of the word, moving in all four directions while keeping track of visited cells to avoid revisiting. This lets us find the word if it exists anywhere on the board. We define our function exist with inputs board and word. The input board is a grid of letters, and word is the string we want to find. First, we determine the number of rows m and columns n to understand the size of the board. Next, we create a visited grid of the same size as the board. Each cell starts as false, indicating we haven't stepped on it yet. This helps us prevent revisiting the same cell along a path, like placing sticky notes to mark where we've already walked. We then define a helper function DFS for depth-first search. It takes the current position I and j, and k, which is the index of the current letter in the word. This function explores all possible paths to match the word. Inside DFS, we first check if k equals the word's length. If it does, we've matched all letters and return true. Mission accomplished. Otherwise, we check if we're out of bounds, if the cell has already been visited, or if the cell's letter doesn't match the current letter in the word. If any of these conditions are true, we return false, indicating this path won't work. If the current cell is valid, we mark it as visited. Then we recursively explore all four directions, down, up, right, and left, moving to the next letter in the word. The search stops as soon as one path returns true. After exploring all directions, we unmark the cell as visited to allow other paths to use it later. Finally, we return whether any path from this cell led to the word. After defining DFS, we loop through every cell in the board. For each cell that matches the first letter of the word, we call DFS starting from that cell. If any DFS call returns true, we immediately return true. The word exists. If we finish checking every cell and never find the word, we return false. And that's how this algorithm works. It first sets up the board size and a visited helper grid, then uses depth-first search with backtracking to explore all paths for the word starting from any matching cell. Efficient, simple, and elegant. Let's run our solution using this input board and word. The board is a two-dimensional grid of characters, and the goal is to determine whether the word A, B, C, C, E, D can be formed by moving through adjacent cells without reusing any cell. The algorithm starts by locating the first letter, A, in the grid. From there, depth-first search explores neighboring cells step by step, A, B, C, C, E, D. Each visited cell is temporarily marked to prevent reuse, and backtracking ensures other paths can still be explored if needed. Since a valid path matching the entire word exists, the search completes successfully. The result is true, indicating the word can indeed be constructed from the board. This aligns perfectly with the expected output. So, our implementation is correct. The depth-first search with backtracking accurately navigates the grid, respects the constraints, and confirms the word's presence, efficient, systematic, and reliable. Let's try to implement it using Solution 2. Efficiency Overview. Time and space complexity. O of m times n times 4 to the power of k time and O of 1 space, excluding the recursion stack. The recursion stack itself can go as deep as k. The concept discussion. We're solving the word search problem using depth-first search with backtracking. The main idea is simple. We try starting from every cell on the board, and recursively explore all four directions while matching the letters of the word. We temporarily mark cells as visited to avoid revisiting them on the same path, then backtrack to restore them for other paths. We define our function exist with inputs board and word. The board is a 2D grid of letters, and word is the string we want to find. First, we determine the number of rows m and columns n to understand the size of the board. Next, we define a helper function DFS that takes I, j, and k. I and j are the current row and column, and k is the index of the current letter in the word. This function will explore all paths starting from the current cell to try matching the word. Inside DFS, we first check if k equals the length of the word. If it does, we've successfully matched every letter and returned true. Mission accomplished. Otherwise, we check if I or j are out of bounds, or if the current cell's letter doesn't match the kth letter of the word. If any of these conditions are true, we return false. This path cannot form the word. If the current cell is valid, we save its value in a temporary variable and mark the cell with a special symbol like hash to indicate it's visited. Then we recursively explore all four directions, down, up, right, and left, moving to the next letter in the word. The recursion stops immediately if one path returns true. After exploring, we restore the cell's original value. This is backtracking, allowing other paths to use the cell later. Finally, DFS returns whether any path from this cell led to the word. After defining DFS, we loop through every cell in the board. For each cell, we call DFS starting from index 0 of the word. If any DFS call returns true, we immediately return true. The word exists. If we finish checking every cell and never find the word, we return false. And that's how this algorithm works. It first loops over all potential starting cells, then uses depth-first search with backtracking to explore all paths for the word. Clever, recursive, and systematic. Let's test our function using this input. A, B, C, E, S, F, C, S, A, D, E, E, and the word S, E, E. We're working with a 2D board of characters, and our goal is to check whether the word C can be formed by moving through adjacent cells, up, down, left, or right. Here's why this solution works. We iterate over every cell in the board and try to start a depth-first search from that position. Once DFS begins, we compare the current cell with the current character of the word. If it matches, we temporarily mark the cell as visited by replacing it with a hash, then recursively explore all 4 directions to find the next character. If a path fails, we backtrack by restoring the original value, ensuring other paths can still use that cell. For this input, the search successfully finds the sequence S, E, E in adjacent cells, so the recursion reaches the end of the word. And that's exactly what our program outputs. True. The result matches the expected output, confirming the word exists in the board. So, our implementation is correct. The algorithm successfully searches the grid using DFS and backtracking, accurately validating the word, efficient, precise, and reliable. Let's wrap it up. The word search problem is one of those interview classics that blends logic, recursion, and precision. It's the ultimate test of how well you handle grid traversal without getting lost in the details, or revisiting the same cell twice. We began by understanding the challenge. Given a grid of letters and a word, we need to check if that word can be formed by moving through adjacent cells, horizontally or vertically, without reusing any cell along the way. It's about exploring every valid path to see if the word can be built in sequence. We compared approaches and quickly saw that brute force isn't practical. Checking every possible path without structure would explode in complexity. The elegant solution is backtracking with depth-first search, trying each starting point and exploring all possible directions while marking visited cells to avoid repeats. Our plan was clear. Loop through each cell in the grid, start a DFS whenever the first letter matches, move recursively in all 4 directions, mark cells as visited during the search, and backtrack afterward. If we ever reach the end of the word, we know it exists in the grid. Initialize board dimensions and a visited matrix. Use DFS to explore 4 directions from valid cells. Mark cells as visited during traversal. Backtrack by resetting visited cells after exploration. Start DFS from cells matching the first character. All test cases evaluated. Handles edge cases correctly. Word longer than board size. Single character words. Repeated letters. No cell reused in a single path. All test cases passed. Closing insight. DFS plus backtracking enables complete path exploration. Visited tracking prevents invalid reuse. Clear state management leads to correct solutions.
Breakdown. Assess. Structure. Implement. Check. 5 steps. Way less panic. PatternMastery.com.
Stuck doing nested BFS from every cell? O1 matrix is the perfect test of multi-source BFS thinking. It shows up often in Phong screens because a brute force approach explodes, while the optimal solution is beautifully simple. Start from all zeros at once and ripple outward. Let's crush it with basic so you can narrate it confidently. We're given an MXN grid of zeros and ones. For every cell, return the distance to the nearest zero using 4 directional moves. Distances are shortest path lengths in an unweighted grid. Brute force, running BFS from each one, is O, MN2. Instead, think backwards. The nearest 0 to a 1 is discovered if we start BFS from all zeros simultaneously. That's multi-source BFS. Push all 0 positions into the queue with distance 0. Mark ones as, or unvisited, then relax neighbors. Complexity. OMN time and OMN space. Alternative. 2 pass DP sweeping top left bottom right then reverse. High-level steps. Initialize a dist grid. Put every 0 into a queue with distance 0. Set every 1 to inf. BFS. Pop a cell, try 4 neighbors. If dist near NC, greater than dist RC, +1, update an in queue. When the queue drains, dist holds the nearest 0 distance for every cell. Let's try to implement it using solution 1. Time complexity. OMN, the concept discussion. We want, for every cell, the distance to the nearest 0. The fastest way is multi-source BFS. Instead of running BFS from every one, too slow, we start BFS from all 0 cells at once. Think of all zeros as starting points that spread outward in waves. The first time a cell gets reached, that distance is guaranteed to be the shortest because BFS expands level by level. We store distances in a separate grid, initialize all zeros to distance 0, then fill everything else as we expand. This function builds a distance grid, seeds the BFS queue with all 0 cells, then expands outward to fill the nearest 0 distance for every cell. First, we store the matrix dimensions. Then we create a dist grid to hold answers. We initialize it with null to mean not computed yet. We also create a queue for BFS. This is the multi-source part. We scan the whole grid and find every cell that is 0. Each of those is a starting point with distance 0, so we set dist to 0 and push it into the queue. Now BFS will expand outward from all zeros at the same time, like ripples. We define the 4 directions: down, up, right, left. That's how we move from a cell to its neighbors. Now we process the queue. Each popped cell already has the shortest known distance to a 0. We try to expand to its neighbors. If a neighbor is inside bounds and still null in dist, that means it hasn't been assigned a distance yet, so the first time we reach it must be the shortest path. We set its distance to dist current +1 and push it into the queue to keep spreading. After BFS finishes, every cell has been assigned the shortest distance to the nearest 0. So we return the completed dist grid. And that's how this algorithm works. It first creates a distance grid and seeds the BFS queue with all 0 cells as starting points. Then it performs a multi-source BFS to expand outward level by level and assign the shortest distance to the nearest 0 for every cell. Efficient, simple, and elegant. Let's test our function using this matrix input: 0, 0, 0, 0, 0, 1, 0, 0, 0, 0. In this problem, every cell is either a 0 or a 1, and we want to return a new matrix where each cell contains the distance to the nearest 0. This solution uses multi-source BFS. That means we start BFS from all the 0 cells at the same time. So first, every cell that already has a 0 gets distance 0 and goes into the queue. The one cell in the middle starts as unknown, null, because we haven't computed its distance yet. Then BFS expands outward layer by layer. Since the middle cell, 1, 1, is surrounded by zeros, the very first time we reach it, it's just one step away from a 0. So we set dist 1, 1 equals 1. All other cells are zeros, so they stay at 0 distance. And that's exactly what our program outputs: 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, matching the expected result. The output makes perfect sense because every border cell is already a 0, and the only one is in the center, exactly one move away from a 0. So, our implementation is correct. The algorithm computes nearest 0 distances efficiently by running a single BFS starting from all zeros, efficient and accurate. Let's try to implement it using solution 2. Time complexity, OMN. The concept discussion. This DP approach finds the distance to the nearest 0 without using a queue. The key idea is that a cell's best distance can be built from its neighbors' distances. We do 2 passes so every cell can learn from all directions. In the first pass, top left bottom right, each cell updates itself using only its top and left neighbors, because those are the neighbors we've already processed. In the second pass, bottom right top left, each cell updates using its bottom and right neighbors, finishing the information flow from the other directions. By starting with infinity for non-zero cells and setting 0 cells to 0, these 2 passes pull in the shortest distance from the nearest 0. This function builds a distance grid, then refines it with 2 directional passes so every cell gets the shortest path to a 0. We store the matrix size and create a dist grid initialized with infinity. That means, we don't know the distance yet. This makes it easy to take minimums later without special cases. In the first pass, we move left to right and top to bottom. If the cell is 0, its distance is clearly 0. If it's 1, we try to build a best guess from neighbors we've already computed, the top cell and the left cell. If either of those neighbors already has a good distance, then the current cell can be one step further than that neighbor. After the first pass, distances are good when the nearest 0 is above or to the left, but a 0 could also be below or to the right. That's why we need the second pass. In the second pass, we sweep from bottom right back to top left. Now we can safely use the bottom and right neighbors, because they've already been processed in this direction. Each cell updates itself again, taking the minimum between what it already had and what it can learn from bottom/right neighbors plus 1 step. This completes the picture and ensures distances reflect the nearest 0 in any direction. After both passes, dist contains the true shortest distance to a 0 for every cell, so we return it. And that's how this algorithm works. It first initializes a distance grid with infinity and sets 0 cells to 0 during the first top left to bottom right pass. Then it refines distances in a second bottom right to top left pass using bottom and right neighbors to guarantee the shortest distance to a 0. Efficient, simple, and elegant. Let's test our function using this matrix: 0, 0, 0, 0, 0, 1, 0, 1, 1, 1. Here, 0 cells are our targets, and every one cell needs to be replaced by the distance to the nearest 0, moving only up, down, left, or right. This solution doesn't use a queue. It uses a clean two-pass dynamic programming approach with a dist grid. Pass 1, top left bottom right. We initialize distances to infinity, set every 0 cell to 0, and for each one cell, we try to improve its distance using the cell above it, and the cell to the left. So, for example, the middle cell, 1, 1, is a 1, but it has zeros right above and left, so it becomes 1. On the last row, cells start getting partial distances, but some nearest zeros might be to the right or below, which we haven't fully accounted for yet. Pass 2, bottom right top left. Now we sweep backwards and try to improve distances again using the cell below, and the cell to the right. This second pass fixes anything that needed information from the bottom or right side. And that's exactly what our program outputs: 0, 0, 0, 0, 0, 1, 0, 1, 2, 1, matching the expected result. Why does this make sense? The bottom left, 2, 0, is just one step away from the 0 above it at 1, 0, so it's 1. The bottom middle, 2, 1, is 2 steps away from the nearest 0, either up to 1, 1, then to 1, 0, 1, 2, or directly toward the closest 0, so it becomes 2. The bottom right, 2, 2, is one step away from the 0 above at 1, 2, so it's 1. So, our implementation is correct. The algorithm efficiently computes nearest 0 distances using two-directional passes to capture all shortest paths, efficient and accurate. Alright, quick recap to wrap up O1 matrix. We're given a grid of zeros and ones, and for every cell we want the distance to the nearest 0, moving only up, down, left, or right. Conceptually, this is a shortest path problem in an unweighted grid. The key decision is avoiding the slow approach. Running a search from everyone would blow up in time. Instead, we use multi-source BFS. Start from all zeros at once. Zeros begin at distance 0, and the distances ripple outward level by level. The first time a cell is reached, that distance is final, so the whole solution stays OMN. The plan was, create a distance grid with an unvisited marker, load every 0 cell into a queue with distance 0, then run BFS. Each step pops a cell, checks its 4 neighbors, and if a neighbor hasn't been assigned yet, we set its distance to current +1 and enqueue it. When BFS finishes, the distance grid is the answer. We used a queue of cell positions, expanded using the 4-direction pattern, and made sure each cell is enqueued only once, right when its distance is first set. The solution ran cleanly on LeetCode with no errors. We sanity checked the main scenarios. If the grid is all zeros, every distance is 0. With a single 0, distances grow in Manhattan rings. With multiple zeros, each one naturally gets assigned to the closest 0 because BFS expands evenly. And since BFS is level by level, it guarantees the shortest distance, and all test cases passed. The takeaway is simple. Think multi-source BFS. Seed the queue with every 0, expand outward once, and you fill the entire grid with nearest 0 distances efficiently. Once you recognize this pattern, a lot of grid BFS problems become much easier.
Honestly, I only did patterns. Then they got the offer. PatternMastery.com.
This one looks like a toy grid, until your loops explode. Rotting Oranges is a PatternMastery 100 classic that reveals whether you can recognize multi-source BFS and reason in minutes, not hours. Interviewers love it because the brute force is tempting, but the optimal approach is one elegant flood from all rotten oranges at once. Let's master it with basics. Let's break this down. We have a grid where 0 equals empty, 1 equals fresh, 2 equals rotten. Every minute, a rotten orange makes its 4 directional neighbors rotten. Return the minutes to rot all fresh, or -1 if impossible. If there are no fresh to begin with, return 0. Now let's assess it. Running BFS from each fresh cell would be O(mn squared). Instead, flip the perspective. All currently rotten oranges are sources with time 0. We push them all into a queue and perform a multi-source BFS. Each time we rot a fresh neighbor, we enqueue it with time t+1. Track the count of fresh. If any remain at the end, return -1. Here is the structure. Plan. Scan grid once, count fresh and enqueue all, R, C, 0, for cells with 2. BFS. Pop, R, C, T, try 4 neighbors. When we see a 1, turn it to 2. Decrement fresh, push, near, NC, T+1, and update minutes. When queue drains, if fresh equals 0 return minutes, else -1. Let's try to implement it using solution 1. Efficiency overview. Time complexity. OM middle.n. Space complexity. OM middle.n. The concept discussion. We solve this using BFS, breadth first search, with a queue, because rotting spreads outward in waves each minute, exactly what BFS models well. The trick is multi-source BFS. We start the queue with all rotten oranges at once, so the spread happens in parallel from every rotten spot. We also count how many fresh oranges exist, so we know when we're done, or if it's impossible. First, we grab the grid size, create a queue for BFS, and set up a counter for how many fresh oranges we have. We also define the 4 directions so we can easily check the neighboring cells, up, down, left, and right, because rotting only spreads to adjacent oranges. Next, we scan every cell. Each fresh orange increases fresh count, and each rotten orange gets added to the queue right away. That's the multi-source part. Starting from all rotten oranges means the infection spreads simultaneously from every rotten location. If there are no fresh oranges at the start, we don't need any time at all, so we return 0 immediately. Otherwise, we create a minutes counter to track how many BFS layers we process. Shift. This is the main BFS loop. Each round of the while loop represents 1 minute passing. We take the current queue length as size, so we only process the oranges that are rotten at the start of this minute. Any new oranges that rot during this minute get added to the queue, but they'll be processed in the next minute. This is what makes the minute tracking accurate. For every rotten orange we're processing, we look at its 4 neighbors. If a neighbor is in bounds and is fresh, we flip it to rotten, reduce the fresh count, and push that neighbor into the queue. That push means it will act as a new spreader in the next wave. After we finish the entire current wave, we increment minutes once, because 1 full minute of spreading has completed. At the end, if we manage to rot all fresh oranges, we return the number of minutes we counted. If there are still fresh oranges left but the queue is empty, that means they were trapped and could never be reached, so we return -1. And that's how this algorithm works. It first counts fresh oranges, enqueues all starting rotten oranges, and sets up BFS directions, then runs a minute-by-minute multi-source BFS that spreads rot to adjacent fresh oranges until all rot or it becomes impossible. Efficient, simple, and elegant. Highlight input box. Grid equals 2, 1, 1, 1, 1, 0, 0, 1, 1. Here, the rotten orange at the top left, value 2, starts spreading rot to all adjacent fresh oranges, value 1. Each minute, rot spreads outward in 4 directions. Explain briefly, minute by minute. Minute 1, the 2 fresh oranges next to the rotten one turn rotten. Minute 2, their neighbors rot. Minute 3, rot continues spreading downward. Minute 4, the final fresh orange becomes rotten. At that point, no fresh oranges remain. Highlight output box, 4, and that matches the expected result. It takes 4 minutes for every fresh orange in the grid to rot. So the BFS simulation works correctly and returns the exact time needed for full infection. Let's try to implement it using solution 2. Efficiency overview. Time complexity. OM middle.n. Space complexity. OM middle.n. The concept discussion. We still use BFS, breadth first search, because rot spreads outward step by step. The difference here is how we track time. Instead of counting minutes by processing BFS layers, we store the time directly inside each queue entry as row, call, time. Every time we rot a fresh orange, we push it into the queue with time +1. By keeping max time, we always know the latest minute any orange turned rotten. We start by measuring the grid, creating a queue for BFS, and setting up a fresh orange counter. The queue is special here. Each item also carries the time when that cell becomes rotten. The directions array is our simple way to explore the 4 neighbors of any cell. Next, we scan the whole grid. Every fresh orange increases fresh count. Every rotten orange gets added to the queue with time set to 0, because those are the starting sources of infection. This is multi-source BFS again. All rotten oranges begin spreading at the same time. If there are no fresh oranges at the start, the answer is immediately 0. Otherwise, we prepare max time to store the latest time we've seen, basically the final minute when rotting finishes. Now we process the queue. Each entry tells us, this cell is rotten at this specific time. We update max time so it always reflects the largest rotting time we've reached so far. For each rotten cell, we check its 4 neighbors. If a neighbor is fresh and inside the grid, we rot it right away, decrease the fresh count, and add that neighbor to the queue with time plus 1. That time plus 1 is the key idea. It records the exact minute that neighbor became rotten. Finally, we check if we successfully rotted every fresh orange. If yes, max time is the total minutes needed. If not, some fresh oranges were unreachable, so we return -1. And that's how this algorithm works. It first counts fresh oranges and queues all starting rotten oranges with time 0, then uses BFS to rot neighbors while carrying time forward and tracking the maximum rotting minute. Efficient, simple, and elegant. Highlight input box. Grid equals 2, 1, 1, 1, 1, 0, 0, 1, 1. Here, the rotten orange at the top left, value 2, starts spreading rot to all adjacent fresh oranges, value 1. Each minute, rot spreads outward in 4 directions. Explain briefly, minute by minute. Minute 1, the 2 fresh oranges next to the rotten one turn rotten. Minute 2, their neighbors rot. Minute 3, rot continues spreading downward. Minute 4, the final fresh orange becomes rotten. At that point, no fresh oranges remain. Highlight output box, 4, and that matches the expected result. It takes 4 minutes for every fresh orange in the grid to rot. So the BFS simulation works correctly and returns the exact time needed for full infection. At first glance, it's just a small grid, but rotting oranges can blow up fast if you don't think in waves. This problem tests whether you can recognize a multi-source BFS and reason through spreading processes efficiently. Let's do a recap. We're working with a grid where 0 means empty, 1 is a fresh orange, and 2 is rotten. Every minute, rotten ones infect their 4 neighbors. The goal is to find how many minutes it takes for all to rot, or return -1 if some never can. Running BFS from each orange separately is too slow. The trick is flipping the view. Start from all rotten oranges at once. This creates a synchronized BFS wave that spreads rot in minimal time while tracking each minute naturally through the queue. The plan: scan the grid to count fresh oranges and enqueue all rotten ones with time 0. Run BFS in 4 directions. When a fresh orange turns rotten, push it to the queue with time plus 1. Track minutes until the queue is empty. If any fresh remain, return -1. We gathered every rotten orange as a starting point, ran 1 clean BFS across the grid, and verified the solution on LeetCode without any errors. All test cases passed. The timing and BFS propagation worked perfectly across all grids. Bullseye emoji. The key takeaway: think in waves, not steps. Multi-source BFS turns what looks like chaos into one elegant flood that models real-time spread precisely and efficiently.
The interviewer smiled. Not because you were right, because they knew you were lost. Learn to spot the pattern before they spot the panic. PatternMastery.com.
Ever clicked a paint bucket and watched color spread perfectly through a region? That's FloodFill, a PatternMastery 100 staple that tests if you can control recursion/iteration, guard edge cases, and traverse grids cleanly. Interviewers love it because one tiny bug creates infinite loops. Today, we'll nail it with basics so your solution is fast and bulletproof. Let's break it down. We're given an image grid, a starting cell, SR, SC, and a new color. We must recolor all 4 directionally connected cells that share the starting cell's original color. If the original color equals new color, nothing changes, return the image. Now let's assess it. This is a classic graph traversal on a grid. Use DFS or BFS. Watch 2 pitfalls. If new color equals old color, early return to avoid infinite revisits. Stay inbounds and only traverse cells with the old color. Complexity is OM middle.end time, OM middle.end space worst case, stack/queue, for an M times N grid. Here's the structure. Plan with BFS, iterative and interview friendly. Read old equals image SRSC. If old equals new color, return. Push SR, SC, into a queue and recolor it immediately. While queue not empty, pop R, C, for each neighbor, near, NC, in 4 DIRs, If inbounds and image near NC equals old, recolor and enqueue. Let's try to implement it using solution 1. Efficiency overview. Time complexity. OM middle.n. Space complexity. OM middle.n. The concept discussion. Flood fill works like a paint bucket tool. We start from one pixel, remember its original color, then repaint that pixel and every connected pixel, up, down, left, right, that matches the same original color. We use DFS, depth first search, to keep expanding from the start into neighbors. Two key protections make this safe. We stop if we go out of bounds, and we stop if a pixel isn't the original color. Also, if the new color is already the same as the original, we return immediately to avoid unnecessary work. We begin by grabbing the color at the starting pixel. This becomes our target group color. Then we handle the most important edge case. If the starting color is already the new color, there's nothing to fill, so we immediately return the image. Next, we store the grid dimensions and define the 4 directions we're allowed to move. This makes exploring neighbors clean and consistent, no repetitive code for each direction. This DFS helper starts with guardrails. If we step outside the image, we stop. If the current pixel isn't the original color, we stop. These checks ensure we only recolor the connected region that matches the starting pixel's color. Once the pixel is valid, we repaint it to the new color. Then we recursively visit all 4 neighbors. That recursive spreading is what fills the entire connected area. Every matching neighbor triggers more exploration until the region is fully recolored. Finally, we start DFS from the given starting row and column. When DFS finishes, the image has been updated in place, so we return it. And that's how this algorithm works. It first captures the starting pixel's original color and exits early if the new color is the same. Then, runs DFS to repaint the region and recursively expand to all connected pixels that match. Efficient, simple, and elegant. Highlight input box. Image equals 1, 1, 1, 1, 1, 0, 1, 0, 1, SR equals 1, SC equals 1, color equals 2. Here, we start flood fill at position 1, which currently has the value 1. Our job is to recolor this pixel, and any connected pixels with the same value, to 2. Explain briefly. The pixel at 1, 1 connects to a whole block of ones around it. Up, down, left, and right. All of these connected ones get changed to 2. Pixels that are diagonal or blocked by a different number, like the zeros, are untouched. Highlight output box. 2, 2, 2, 2, 2, 0, 2, 0, 1, and that's exactly the result. All connected ones were replaced with 2, matching the expected output. So the flood fill works correctly, spreading outward from 1, 1, and recoloring only the valid connected region. Let's try to implement it using solution 2. Efficiency overview. Time complexity. OM middle.n. Space complexity. OM middle.n. The concept discussion. This is the same paint bucket idea, but instead of DFS recursion, we use BFS with a queue. We start from the given pixel, repaint it, then keep spreading outward to its neighbors, up, down, left, right. Anytime we find a neighbor that still has the original starting color, we repaint it and add it to the queue so it can continue spreading. A key trick here is we repaint before enqueuing. This acts like a visited marker so we don't add the same pixel multiple times. We begin by saving the starting pixel's color. This is the only color we're allowed to replace. Then we handle the critical edge case. If the new color matches the original color, nothing needs to change, so we return immediately. Next, we set up the grid dimensions and the 4 movement directions. Then we create a queue and seed it with the starting position. We also repaint the starting pixel right away. That immediate repaint is important. It prevents the starting cell from being processed repeatedly and sets the tone for how we'll avoid duplicates throughout the BFS. Now we process the queue until it's empty. Each time we pop a cell, we look in all 4 directions to find its neighbors. This is the BFS wave approach. We expand outward from the start, layer by layer, as long as we keep finding valid pixels to repaint. Here's the gatekeeper logic. We only act on neighbors that are inside the grid and still match the original starting color. Once we find one, we repaint it immediately and then push it into the queue. Repainting before enqueuing is the big win. It ensures the same cell won't be added multiple times from different directions. Once the queue is empty, it means there are no more connected pixels with the original color, so the fill is complete. We return the updated image. And that's how this algorithm works. It first captures the original color, sets up directions and a queue, and recolors the starting pixel. Then, runs BFS to spread the fill by repainting valid neighbors and in-queuing them until the region is fully covered. Efficient, simple, and elegant. Highlight input box. Image equals 1, 1, 1, 1, 1, 0, 1, 0, 1, SR equals 1, SC equals 1, color equals 2. Here, we start flood fill at position 1, which currently has the value 1. Our job is to recolor this pixel, and any connected pixels with the same value, to 2. Explain briefly, the pixel at 1, 1 connects to a whole block of ones around it. Up, down, left, and right. All of these connected ones get changed to 2. Pixels that are diagonal or blocked by a different number, like the zeros, are untouched. Highlight output box, 2, 2, 2, 2, 2, 0, 2, 0, 1, and that's exactly the result. All connected ones were replaced with 2, matching the expected output. So the flood fill works correctly, spreading outward from 1, 1, and recoloring only the valid connected region. Ever clicked a paint bucket and watched color spread instantly across a region? That's flood fill, a perfect test of clean grid traversal, recursion control, and edge handling. Let's do a recap. We're given an image grid, a start cell, and a new color. The task: recolor all connected cells, up, down, left, right, that share the starting color. If the starting color already matches the new one, we simply return the image as is. It's a classic graph traversal disguised as painting. We can use BFS or DFS, both work. The main pitfalls? Avoid infinite recursion when the color doesn't change, and stay inside bounds at all times. The plan: record the starting color. If it's already the new color, stop early. Use a queue, BFS, to recolor the start cell and expand to 4 directional neighbors with the same color. Continue until no connected cells remain. We executed this BFS plan, handled edge checks, recolored properly, and ran it on LeetCode with 0 errors. All test cases passed. Traversal and recoloring behaved exactly as expected. The big lesson: flood fill isn't just about color, it's about control. Managing boundaries and revisits cleanly proves you understand traversal flow from start to finish.
Rejected. 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 At some point, it is not bad luck. It is bad prep. PatternMastery.com.
Want to ace tree questions at Google, Amazon, or Apple? Binary tree level order traversal is a classic PatternMastery 100 question. And over 25% of candidates mess up the queue logic or output formatting. Nail this one, and you'll be ready for everything from graph traversals to real-world scheduling challenges. Let's level up your skills together. Let's solve binary tree level order traversal with the basic method, so you build rock-solid, interview-ready solutions every time. Let's break this down. Given the root of a binary tree, return its values level by level, that is nodes at each depth together in a list. Input: root node of a binary tree. Output: list of lists. Each inner list contains all node values at that tree level. Here is an example. Input: output: 3, 9, 20, 15, 7. Here is a real-world example. Suppose you're managing a project with tasks organized in dependency levels. You want to group tasks by which ones can be started at each phase. An interviewer might ask, how would you organize a company's org chart into management levels for communication planning? Now let's assess it. What's tricky? This is a classic breadth-first search, BFS. You need to process the tree layer by layer. You need a queue to keep track of which nodes to process next. The result must be grouped per level, not just a flat list. Think step by step. If the root is null, return an empty list. Initialize a queue with the root node. While the queue isn't empty, track the number of nodes at the current level. Queue size at start of a loop. For each node at this level, pop from the queue, add its value to a temporary list. Add its left/right children to the queue for the next level. After finishing this level, append the temporary list to the final result. Repeat until all levels are processed. Let's add more detail. Why track the queue size at each loop? It ensures that you process exactly the nodes at the current level, so your output matches the level grouping. Forgetting this step is a classic source of bugs. Some edge cases: empty tree, return; single node, return; val. Deeply skewed or unbalanced trees should still work. Here is the structure: if root is null, return. Initialize a result list and a queue with root. While queue not empty, get current level size. For each node at this level, Pop, save value, in queue children. Add this level's. Let's try to implement it using solution 1. Efficiency overview. Time complexity. ON, space complexity, ON. The concept discussion. This is level order traversal, also called BFS, where we visit the tree one level at a time. Instead of using a single queue, this solution uses two arrays, one for the current level we're processing, and another for the next level we're building. For each level, we collect all node values into a list, and we gather their children into next level. Then we move down one level and repeat until there are no more nodes left. If the tree is empty, there are no levels to return, so we immediately return an empty array. That keeps the rest of the logic simple. We prepare the final result, which will hold one array per level. Then we initialize current level with the root node, meaning we're ready to process level 0. Each loop iteration processes exactly one level. We create a fresh level values array for values we'll collect from this level, and a fresh next level array to store the children we discover for the next round. Now we walk through all nodes in the current level. We record each node's value, and we push its children into next level. This is the BFS idea in action. We finish an entire layer before moving on to the next one. Once we've processed the entire level, we add level values into the final result. Then we shift our focus downward by replacing current level with next level. When there are no more nodes to process, result now contains the values level by level, so we return it. And that's how this algorithm works. It first handles the empty tree case and initializes the current level with the root, then repeatedly collects values for the current level while building the next level's nodes until the traversal is complete. Efficient, simple, and elegant. Highlight input box. Root equals 3, 9, 20, null, null, 15, 7. Let's test our level order traversal function using this binary tree. 3, 9, 20, null, null, 15, 7. This level order array describes the tree as follows. 3 is the root. 9 is its left child. 20 is its right child. And under 20 we have 15, left, and 7, right. Explain the logic briefly. Our algorithm processes the tree level by level, collecting the node values at each depth into their own list. So the traversal looks like this. Level 1, 3 level 2, 9, 20 level 3, 15, 7. These groups are exactly what a correct breadth-first traversal should produce. Highlight output box. Output, 3, 9, 20, 15, 7, expected, 3, 9, 20, 15, 7. And the result matches perfectly. The output aligns exactly with the expected value. The test case is accepted. So, our implementation is correct. The algorithm walks through the tree level by level and gathers nodes cleanly and accurately, efficient and spot on. Let's try to implement it using solution 2. Efficiency overview. Time complexity, ON, space complexity, OH, recursion stack, plus ON for the output. The concept discussion. Even though level order sounds like BFS, we can also do it with DFS by keeping track of the current level number as we recurse. The trick is, every time we visit a node, we place its value into result level. If that level array doesn't exist yet, we create it. By traversing left before right, we naturally keep values in left to right order within the same level. We begin with an empty result array. This will eventually become a list of levels, where each level is its own array of node values. This helper takes a node and the level it belongs to. If the node is missing, we stop. Otherwise, we make sure the array for this level exists. If we're visiting this level for the first time, we add a new empty array into result. Now we record the node's value into the exact bucket for its level. That's the core idea. DFS visits nodes in a different order than BFS, but by labeling each node with its level, we still group values correctly. Then we recursively visit children, increasing the level by 1. Going left first, then right, preserves the natural left to right ordering within each level. Finally, we start the DFS from the root at level 0, and once recursion finishes, result contains the tree grouped by levels, so we return it. And that's how this algorithm works. It first creates a result list and uses DFS with a level counter to know where each node belongs, then places each node into its level bucket while recursing left then right to maintain order. Efficient, simple. Highlight input box. Root equals 3, 9, 20, null, null, 15, 7. Let's test our level order traversal function using this binary tree. 3, 9, 20, null, null, 15, 7. This level order array describes the tree as follows. 3 is the root. 9 is its left child. 20 is its right child. And under 20 we have 15, left, and 7, right. Explain the logic briefly. Our algorithm processes the tree level by level, collecting the node values at each depth into their own list. So the traversal looks like this. Level 1, 3 level 2, 9, 20 level 3, 15, 7. These groups are exactly what a correct breadth-first traversal should produce. Highlight output box, output, 3, 9, 20, 15, 7, expected, 3, 9, 20, 15, 7, and the result matches perfectly. The output aligns exactly with the expected value. The test case is accepted. So, our implementation is correct. The algorithm walks through the tree level by level and gathers nodes cleanly and accurately, efficient and spot on. Let's quickly recap binary tree level order traversal, a must-know interview question that tests your understanding of queues and BFS traversal. The goal was simple: traverse a binary tree level by level, grouping nodes at the same depth together into lists. Essentially, we built a layer-by-layer view of the tree. We recognize that breadth-first search is the perfect fit, using a queue to process nodes in order, one level at a time. The key challenge was keeping track of the queue size each round, so we only process nodes from the current level. Our plan: check for an empty tree, initialize a queue with the root, loop until it's empty, collect values for each level, and in-queue child nodes for the next round. We wrote this logic step by step, using a clean BFS loop and a result list, and it ran smoothly on LeetCode without any errors. We verified the output, each level printed correctly, from top to bottom. 3, 9, 20, 15, 7. Edge cases like empty or single node trees worked perfectly. The big takeaway? Queue-based BFS isn't just for trees, it's the backbone of level order logic in graphs, scheduling systems, and even social network distance calculations. Did you know that maximum depth of binary tree is one of the most common binary tree questions at Google and Facebook interviews? This PatternMastery 100 staple is deceptively simple, but over 25% of candidates get tripped up on recursive logic or base cases. Get this right, and you'll breeze through a whole family of tree questions. Let's solve maximum depth of binary tree using the basic method, helping you analyze, reason, and implement like a pro. Let's break this down. You're given the root node of a binary tree. Your goal is to return its maximum depth, that is, the number of nodes along the longest path from root down to the farthest leaf node. Input, binary tree root node. Output, integer representing the tree's max depth. Here's a real-world example for this question. Imagine you're building a company org chart, and you need to find the maximum number of management layers between the CEO and any employee. An interviewer might ask, how would you determine the longest dependency chain in a workflow tree? Let's assess it. What's tricky? The tree can be perfectly balanced, skewed to one side, or even empty. You need to account for every possible branch. Recursion is perfect here. At each node, the maximum depth is 1 plus the larger of the left or right subtree's depth. Think step by step. For a null or empty node, depth is 0, base case. For each node, recursively compute the depth of the left and right children. The depth at the current node is 1 plus the max of the left and right subtree depths. The recursion bubbles up, calculating and combining results as it returns. Let's add more clarity. Each time you call the function on a child node, you're asking, how deep is this subtree? The maximum is always determined by the deepest path from root to a leaf node, regardless of how lopsided the tree may be. Edge cases. Empty tree should return 0. Single node should return 1. Deeply skewed tree function should handle without Stack Overflow, unless tree is extremely deep. Here is the structure. If root is null, return 0. Recursively compute max depth of left subtree. Recursively compute max depth of right subtree. Return 1 plus max left, right. Let's try to implement it using solution 1. Efficiency overview. Time complexity, ON. Space complexity, ON. The concept discussion. We're finding the maximum depth of a binary tree, which is basically the number of levels from the root down to the deepest leaf. This solution uses BFS, level order traversal, with a queue. The key idea is, process the tree one level at a time. Each time we finish processing a full level, we increment the depth. When there are no more nodes left to process, The depth we've counted is the tree's maximum depth. If the tree is empty, there are no levels at all, so the maximum depth is 0. This quick check prevents extra work and keeps the rest of the logic clean. We initialize a queue with the root node, because BFS explores the tree level by level. We also create a depth counter that will increase once per level. Each round of the while loop represents one full level of the tree. We snapshot level size so we know exactly how many nodes belong to the current level. Then we increment depth, because we're about to process a new level. Here we process exactly the nodes in the current level. For each node, we push its children into the queue. Those children become the next level that we'll process in the next while loop iteration. This clean separation is what makes the depth counting accurate. When the queue becomes empty, we've processed every level. The depth counter now represents the maximum depth of the tree, so we return it. And that's how this algorithm works. It first handles the empty tree case and initializes a BFS queue and depth counter, then processes the tree level by level, increasing depth once per level until all nodes are visited. Efficient, simple, and elegant. Highlight input box. Root equals 3, 9, 20, null, null, 15, 7. Let's run our function using this tree input. 3, 9, 20, null, null, 15, 7. This array represents a binary tree in level order form. 3 is the root. Its children are 9, left, and 20, right. 20 then has two children, 15 and 7. Explain the logic briefly. Our algorithm calculates the maximum depth of the tree, essentially the longest path from the root down to a leaf node. Following the deepest branch here, 3, 20, 15 or 3, 27, we count 3 levels. Highlight output box. Output, 3, expected, 3, and that's exactly the result we get. 3, perfectly matching the expected output. The test passes smoothly. So, our implementation is correct. The algorithm successfully computes the tree's maximum depth using a clean recursive approach, straightforward and reliable. Let's try to implement it using solution 2. Efficiency overview. Time complexity, ON, space complexity, OH, where H is the tree height, worst case ON. The concept discussion. This solution uses recursion with a simple idea. The maximum depth of a tree is 1, for the current node, plus the deeper depth of its left and right subtrees. So we repeatedly ask the same question for smaller and smaller subtrees. When we hit a missing node, null, that path contributes a depth of 0, and the recursion naturally builds the answer back up from the leaves to the root. If the current node doesn't exist, that means we've gone past a leaf. There's no depth to add here, so we return 0. This is what stops the recursion. For a real node, we compute the depth of the left subtree and the depth of the right subtree by calling the same function again. We take the bigger of the two, because the maximum depth must follow the deepest path, and then add 1 to count the current node's level. And that's how this algorithm works. It first returns 0 for an empty node as the recursion stopping point, then recursively computes left and right depths and returns 1 plus the larger one to build the final maximum depth. Efficient. Highlight input box. Root equals 3, 9, 20, null, null, 15, 7. Let's run our function using this tree input. 3, 9, 20, null, null, 15, 7. This array represents a binary tree in level order form. 3 is the root. Its children are 9, left, and 20, right. 20 then has two children, 15 and 7. Explain the logic briefly. Our algorithm calculates the maximum depth of the tree, essentially the longest path from the root down to a leaf node. Following the deepest branch here, 3, 20, 15 or 3, 27, we count 3 levels. Highlight output box. Output, 3, expected, 3, and that's exactly the result we get. 3, perfectly matching the expected output. The test passes smoothly. So, our implementation is correct. The algorithm successfully computes the tree's maximum depth using a clean recursive approach, straightforward and reliable. Wrap up our discussion on maximum depth of binary tree, one of those deceptively simple interview classics that test how well you truly understand recursion and base cases. The problem asked us to find the longest path from the root to a leaf, in other words, how deep the tree goes. It's a direct measure of how many levels or layers exist in the structure. We saw that recursion fits perfectly. Each node's depth depends on the depths of its left and right children. The key is handling the base case, when the node is null, and correctly returning 1 plus max left, right. Our plan was clean. If the node is null, return 0. Otherwise, recursively compute both sides and add 1 for the current level. We turned that plan into a short, efficient function and ran it successfully on LeetCode without any errors. When we tested it, the logic held up. The function correctly returned 3 for the sample tree, and 0 for an empty one. All test cases passed. The big takeaway? Recursion in trees always starts with the base case and builds upward. Once you master this pattern, problems like minimum depth, balanced binary tree, and diameter of binary tree become much easier to handle.
You thought your job was safe until you got that email. Now you're back on LeetCode remembering you forgot everything about trees and graphs. Interviewer says, solve this in O of n. Your brain says, 404, solution not found. Don't be that person. Subscribe to PatternMastery.com and master the coding patterns FANG companies actually test.
Here's a deceptively simple Pattern Mastery 100 question that's caught many off guard. Same tree. Top companies love it because it reveals your understanding of recursion and attention to structural detail. Over 20% of candidates miss a subtle base case or comparison. Get this right and you'll have recursion fundamentals locked down for your next interview. Let's master same tree using the basic approach, breaking down the problem, analyzing, structuring a solution, and checking all edge cases. Let's break it down. Given the roots of two binary trees, return true if they're structurally identical and all their nodes have the same value. Otherwise, return false. Input: two binary tree root nodes, P and Q. Output: Boolean. True if the trees are the same, false otherwise. Real-world example. Suppose you're building a cloud backup system, and you need to verify if a backup is a true replica of the original tree structure and content. Interviewers might ask, how would you compare two hierarchical document models for structural and content equality? Let's assess. What's tricky? You have to check both the structure and the values at every node. Recursion is the natural fit. You need to handle all the cases where one tree might branch when the other doesn't, or values don't match. Think step by step. If both nodes are null, they're the same at this branch, return true. If only one is null, the trees differ, return false. If both nodes exist, check if their values match. If not, return false. If yes, recursively check their left and right children. The answer is only true if all these checks succeed for every node. Let's add more. Be sure to check both left and right subtrees. Missing one is a classic pitfall. Order of checks matters. Avoid null pointer errors by checking for null before accessing values. Edge cases. Both trees empty should return true. Trees with same shape but different values should return false. Trees with different shapes should return false. Here is the structure. If both P and Q are null, return true. If only one is null, return false. If both exist, compare their values. If not equal, return false. Otherwise, recursively check left and right children. Return true only if both left and right subtrees are also the same. Let's try to implement it using Solution 1. Efficiency Overview. Time complexity, ON, space complexity, OH, where H is the tree height, worst case ON. The concept discussion. We want to verify two binary trees are identical in both structure and values. Recursion fits perfectly because each tree is made of smaller subtrees. At every step, we compare the two current nodes. If both are missing, they match. If only one is missing, the shapes differ. If both exist but values differ, they're not the same. If the current nodes match, we repeat the same check for the left pair and the right pair. Both sides must match for the trees to be truly identical. First we handle the shape checks. If both nodes are null, that means both trees end here in the exact same place, so this part matches. But if only one is null, it means one tree has a node where the other doesn't. So the structures already differ and we can return false immediately. Once we know both nodes exist, we compare their values. If the values don't match, the trees aren't identical, so we stop right away. If the current nodes match, we recursively check the left children together and the right children together. Both checks must be true, because the trees need to match on every branch. This recursion keeps drilling down until it either finds a mismatch or confirms the entire structure and values are identical. And that's how this algorithm works. It first handles null cases to confirm structure and compares current node values, then recursively verifies both left and right subtrees match all the way down. Efficient, simple, and elegant. Highlight input box. P equals 1, 2, 3, Q equals 1, 2, 3. Let's test our function with these two binary trees represented in level order form. P equals 1, 2, 3 and Q equals 1, 2, 3. Both describe the exact same structure. 1 is the root. 2 is the left child. 3 is the right child. Explain the logic briefly. Our algorithm checks if the two trees are identical, meaning same structure and same node values. Since every corresponding node matches perfectly, the trees are indeed identical. Highlight output box. Output, true, expected, true, and that's exactly what we get. True, matching the expected value. The test case passes cleanly. So, our implementation is correct. The algorithm correctly verifies the structural and value-based equality of both trees. Simple, accurate, and reliable. Let's try to implement it using Solution 2. Efficiency Overview. Time Complexity. ON. Space Complexity. ON. The Concept Discussion. This version checks two trees using BFS with a queue, so we compare them level by level instead of using recursion. The key idea is to always compare nodes in pairs, one from the first tree and the matching position node from the second tree. If both are missing, that position matches and we move on. If only one is missing, the shapes differ. If both exist but their values differ, the trees differ. If the current pair matches, we enqueue their left children as a pair and their right children as a pair, continuing until we've checked everything. We start by placing the root nodes into a queue as a pair. From this point on, we always pull out two nodes at a time, one from each tree, so we can compare the same position in both trees. Now we loop until the queue is empty. Each iteration gives us one pair of nodes to compare. If we survive all comparisons, it means every matching position in both trees was identical. This block is the decision maker. If both nodes are null, that means both trees end here in the same way, so we just continue. But if one is null and the other isn't, the structure differs and we return false. And if both exist but their values don't match, we also return false immediately. When the current pair matches, we schedule the next comparisons by enqueuing the left children together and the right children together. This keeps both trees aligned in the same positions as we traverse. If we finish the loop without finding any mismatch, then every compared pair matched perfectly, so the two trees are the same. And that's how this algorithm works. It first initializes a queue with the two root nodes as a pair, then processes node pairs with BFS, checking structure and values and enqueuing child pairs until everything matches. Efficient, simple, and elegant. Highlight input box. P equals 1, 2, 3, Q equals 1, 2, 3. Let's test our function with these two binary trees represented in level order form. P equals 1, 2, 3 and Q equals 1, 2, 3. Both describe the exact same structure. 1 is the root. 2 is the left child. 3 is the right child. Explain the logic briefly. Our algorithm checks if the two trees are identical, meaning same structure and same node values. Since every corresponding node matches perfectly, the trees are indeed identical. Highlight output box. Output, true, expected, true, and that's exactly what we get. True, matching the expected value. The test case passes cleanly. So, our implementation is correct. The algorithm correctly verifies the structural and value-based equality of both trees. Simple, accurate, and reliable. Quick recap on same tree. It looks simple, but it's a brilliant test of your recursion fundamentals and your eye for structural detail, exactly why top companies love it. We frame the task as a pure comparison problem. Two roots n, and we return true only if both trees match in structure and in every value. We highlighted why recursion is the natural fit and called out the easy-to-miss cases. Both null is true, one null is false, and any value mismatch fails, plus the reminder to check both left and right subtrees. Our plan was a tight sequence. Handle the null checks first. Compare values when both nodes exist, then recursively verify left and right. Both sides must agree for the overall result to be true. We translated that plan directly and ran it on LeetCode, clean execution with no errors. We validated with examples. Identical trees returned true, and differences in shape or values returned false. Test cases passed as expected. The big lesson: recursion succeeds when base cases are exact and comparisons are symmetrical. Nail this pattern, and you're set up for problems like symmetric tree, subtree checks, and beyond.
Quiet room. Shared screen. One question. No clue. That silence is expensive. PatternMastery.com.
Have you ever heard invert binary tree called the hello world of binary tree questions? It's a classic PatternMastery 100 favorite, frequently asked at Google and Microsoft, and surprisingly, it still trips up more than 25% of candidates. Master this problem, and you'll build the foundation for tree recursion, traversals, and more. Let's approach invert binary tree with the basic method, breaking down the process, analyzing key steps, and ensuring you understand every pointer twist. Let's break it down. Given the root of a binary tree, invert it, meaning swap the left and right child of every node in the tree. Input, binary tree root node. Output, the same tree, but with every left and right subtree swapped. Real-world example. Imagine an image editing app with a mirror filter. To flip an image horizontally, you need to swap every left and right pixel or object. Similarly, inverting a tree mirrors its structure. Interviewers may ask, how would you design a function to mirror a decision tree, or flip a UI layout that's stored in a binary tree structure? Let's assess it. What's tricky? Recursion is the natural fit for trees, but you need to ensure you swap every subtree, not just the first level. You can use DFS, depth first traversal, pre-order, post-order, or BFS, level order, but recursion is clearest and most popular in interviews. Think step by step. If the current node is null, do nothing, base case. Otherwise, swap its left and right children. Recursively call the invert function on both children. You'll process every node exactly once, flipping the tree from the top down. Let's go deeper. If you prefer iteration, you can use a queue, BFS, but recursion matches how we mentally walk through a tree. Be careful to process null nodes and leaf nodes. These are your base cases. Here's some edge cases. Empty tree should return null. Single node should return the node itself. Skewed trees, only left or right children. Here's the structure. If root is null, return null. Swap roots left and right children, recursively invert the left child. Recursively invert the right child, return the root. Let's try to implement it using solution 1. Efficiency overview. Time complexity, ON, space complexity, OH, where H is the tree height, worst case ON. The concept discussion. Inverting a binary tree means swapping the left and right child of every node. Recursion makes this clean because a tree is made of smaller trees. For each node, we invert its right subtree and its left subtree, then swap them. Once every node performs that swap, the entire tree becomes a mirror image of the original. If we hit a missing node, there's nothing to invert, so we return null. This is the stopping point that prevents recursion from going forever. For a real node, we invert both sides, but we also swap them at the same time. The right subtree becomes the new left subtree after it's inverted, and the left subtree becomes the new right subtree after it's inverted. This single statement captures the whole mirror action at the current node. After swapping and inverting below, we return the root of this inverted subtree. That returned value bubbles back up the recursion until the entire tree is inverted. And that's how this algorithm works. It first stops on null nodes to end recursion, then recursively inverts both subtrees while swapping left and right at every node to create a mirrored tree. Efficient, simple, and elegant. Highlight input box. Root equals 4, 2, 7, 1, 3, 6, 9. Let's run our function on this binary tree. 4, 2, 7, 1, 3, 6, 9. This array represents a level order traversal of the tree. 4 is the root. 2 and 7 are its children. 1 and 3 belong under 2, while 6 and 9 belong under 7. Explain the logic briefly. Our algorithm inverts the entire binary tree, meaning every left child swaps with the right child at every node. After inversion, 2 and 7 swap places under the root. Then 1 swaps with 3, and 6 swaps with 9. Performing a traversal after this swap gives us 4, 7, 2, 9, 6, 3, 1. Highlight output box. Output, 4, 7, 2, 9, 6, 3, 1. Expected, 4, 7, 2, 9, 6, 3, 1. And that's exactly the result we see. The output perfectly matches the expected output. The test case passes with flying colors. So, our implementation is correct. The algorithm successfully inverts the binary tree and returns the correct transform structure. Clear, efficient, and accurate. Let's try to implement it using solution 2. Efficiency overview. Time complexity. ON, space complexity, ON. The concept discussion. Inverting a binary tree means turning it into a mirror image. Every node swaps its left and right child. This solution does it iteratively using BFS with a queue. We start from the root, visit nodes level by level, swap their children immediately, and push the children into the queue so they can be processed next. Once every node has been visited and swapped, the entire tree is inverted. First, if the tree is empty, there's nothing to invert, so we return null. Otherwise, we start a queue with the root node. This queue is what lets us process the tree in a simple, level-by-level order. Highlight BFS loop. Visit nodes until done. While queue.length greater than 0. Const node equals queue.shift. Now we keep running while the queue still has nodes to process. Each loop pulls out the next node that needs to be inverted. This is the heart of the inversion. For the current node, we swap its left and right children. After this swap, the node's local structure is mirrored. After swapping, we push the node's children into the queue, only if they exist. That ensures we eventually reach every node in the tree and perform the same swap everywhere. Once the queue is empty, every node has been processed and swapped, so the tree is fully inverted. We return the original root, which now represents the inverted tree. And that's how this algorithm works. It first checks for an empty tree and initializes a queue starting from the root, then runs BFS to visit every node, swap its children, and continue until the entire tree is mirrored. Efficient, simple, and elegant. Highlight input box. Root equals 4, 2, 7, 1, 3, 6, 9. Let's run our function on this binary tree. 4, 2, 7, 1, 3, 6, 9. This array represents a level-order traversal of the tree. 4 is the root. 2 and 7 are its children. 1 and 3 belong under 2, while 6 and 9 belong under 7. Explain the logic briefly. Our algorithm inverts the entire binary tree, meaning every left child swaps with the right child at every node. After inversion, 2 and 7 swap places under the root, then 1 swaps with 3, and 6 swaps with 9. Performing a traversal after this swap gives us 4, 7, 2, 9, 6, 3, 1. Highlight output box. Output, 4, 7, 2, 9, 6, 3, 1. Expected, 4, 7, 2, 9, 6, 3, 1. And that's exactly the result we see. The output perfectly matches the expected output. The test case passes with flying colors. So, our implementation is correct. The algorithm successfully inverts the binary tree and returns the correct transform structure. Clear, efficient, and accurate. Alright, quick recap on invert binary tree, the so-called hello world of binary tree problems. It's simple in theory but powerful for mastering recursion and traversal fundamentals. The task was to flip a binary tree by swapping every left and right child, essentially mirroring its structure while keeping all node values the same. We explored recursion as the clearest solution, noting that each node must be swapped and then its subtrees inverted. DFS and BFS can both work, but recursion keeps the logic clean and intuitive. Our plan was short and sharp. Handle the null base case, swap the children, recursively invert the left and right, and finally return the root. We followed that plan in code, ran it on LeetCode, and it executed successfully with no errors. We walked through examples, confirming each node swapped correctly and all test cases passed as expected. The key takeaway? Recursion is about trusting the process. Solve for one node, let the function handle the rest. Mastering this mirror logic makes tackling more complex tree problems far easier.
Wake up. Work. Scroll jobs. Do random LeetCode. Feel behind. Repeat. Break the loop. PatternMastery.com.
Ready for a tree problem that trips up even experienced candidates? Binary tree maximum path sum is a PatternMastery 100 power question, and a favorite at Google, Facebook, and Microsoft for its tricky recursion and edge cases. Over 40% of interviewees make a mistake handling negative values or path splits. Let's ensure you ace it by breaking it down step by step. Let's master binary tree maximum path sum with the basic approach, ensuring you catch every tricky detail and never lose track of the recursion. Let's break this down. You're given the root of a non-empty binary tree. Find the maximum path sum, where a path can start and end at any node, and must contain at least one node. Paths can bend at a node, from left through parent to right, but cannot revisit nodes. Input, root node of a binary tree, values can be negative or positive. Output, integer representing the maximum path sum. Here's a real-world example. Imagine a decision tree where each node's value represents profit/loss, and you want to find the richest sequence of decisions, even if that path bends through a parent. Interviewers might ask, what's the most valuable branch in a hierarchical project plan? Let's assess. What's tricky? Paths can go through a parent, taking both left and right children, but only at one split. Each recursion must return the single-sided max path, either left or right plus node, but must also update a global best if the whole V-shaped path through the current node is better. Negative values. Sometimes it's better to cut off a bad child by treating its max as 0. Think step by step. Traverse the tree with a post-order DFS. For each node, recursively get the max sum from the left child, ignore negatives by taking max with 0. Recursively get the max sum from the right child, also ignoring negatives. The maximum path through the node is node.val plus left underscore max plus right underscore max. Update a global max if this path is better than any seen before. For the recursion, return node.val plus max left underscore max, right underscore max, the best one-sided path to use further up the tree. The global max may be at any node, not just the root. Let's clarify. Always take the larger of 0 in each child's path sum, so you don't decrease the path by including negative numbers. Update the global max at every node, as the best path may bend through it. Edge cases. All negative nodes must still return the least negative, biggest, value. Skewed or one-sided trees should work identically. Single node trees must handle correctly. Here is the structure. Initialize a global variable, for example, max underscore sum equals inf. Write a recursive DFS function. If node is null, return 0. Compute left and right max paths, max 0, recurse left, etc. Calculate path sum through current node. Update global max if necessary. Return node.val plus max left underscore max right underscore max for parent recursion. After traversal, return the global max. Let's try to implement it using solution 1. Efficiency overview. Time complexity, ON, space complexity, OH, where H is the tree height, worst case ON. The concept discussion. We want the maximum path sum in a binary tree, where a path can start and end anywhere, but it must follow parent-child connections. The key trick is to think in 2 layers. For every node, we ask, if a path passes through me as the highest point, what's the best total I can form using my left and right sides? That can use both children. But when returning a value back up to the parent, we can only extend the path in one direction, left or right, because a parent path can't branch into both sides without breaking the idea of a single continuous path. We also ignore negative subtree contributions by treating them as 0, because adding a negative path would only make the sum worse. We start with a global tracker called maxSum, set to negative infinity, so even if all values are negative, we still correctly capture the best possible path. This helper returns the best gain a parent can receive from this node, meaning the best sum of a path that starts at this node and goes downward. If the node doesn't exist, it contributes 0. Here we compute the best gain from the left and right child. The important part is math.max0. If a subtree would reduce the total, negative gain, we pretend it doesn't exist and take 0 instead. This ensures we only include child paths when they actually help. Now we compute the best path that uses the current node as the top of the hill. This path can include the best left gain and the best right gain at the same time, because it's a complete path that starts somewhere in the left subtree, goes through the node, and ends somewhere in the right subtree. We compare it to maxSum and update the global answer if this is better. When we return to the parent, we're not allowed to take both sides anymore, because that would create a fork. So we return the node's value plus the larger of the 2 gains. This represents the best single downward path that can be extended upward. Finally, we start the recursion from the root. The recursion explores every node, updates maxSum along the way, and when it's done, maxSum holds the maximum path sum anywhere in the tree. And that's how this algorithm works. It first sets a global best sum and defines a helper to compute the best downward gain from each node, then ignores negative branches, updates the global maximum using a full path through each node, and returns only the best single branch gain upward. Efficient, simple, and elegant. Highlight input box. Root equals 1, 2, 3. Let's run our function using this binary tree. 1, 2, 3. This level order representation describes a simple tree. 1 is the root, 2 is the left child, 3 is the right child. Explain the logic briefly. Our algorithm computes the sum of all node values in the tree. So we simply add them up. 1 plus 2 plus 3 equals 6. No branches, no complications, just a clean traversal and accumulation. Highlight output box. Output, 6, expected, 6, and the output we get is 6, exactly matching the expected result. The test passes perfectly. So, our implementation is correct. The algorithm efficiently traverses the tree and computes the total sum, straightforward and accurate. Let's try to implement it using solution 2. Efficiency overview. time complexity, ON, space complexity, ON. The concept discussion. We want the maximum path sum in a binary tree, where a path can start and end anywhere but must follow parent-child links. The classic recursive solution computes a gain from each node, best downward path from that node, and also updates a global answer using a path that peaks at the current node, using both left and right. This version does the same thing without recursion by doing a controlled post-order traversal using a stack. The key is, we only compute a node's gain after its children are already computed, so we can safely build the answer from the bottom up. We start with a global max sum to store the best path sum we've seen anywhere. Then we create a stack that will simulate post-order traversal. Each entry includes a node plus a flag that tells us whether its children have already been handled. We also keep a map called node gain to remember the best downward gain for each node. So once a child is done, the parent can reuse that computed result instantly. All this loop keeps going until we've processed everything. Each pop gives us a node and whether we're ready to compute it. If the node is null, we just skip it. Only real nodes contribute to sums. On the first time we see a node, we're not ready to compute anything yet, because we still need its children's gains. So we push the same node back with processed equals true, meaning come back later. Then we push its children onto the stack. This guarantees the children get processed before the parent is computed, just like post-order recursion, but done manually. Now we're in the compute time phase for this node. Since the children were processed earlier, their gains are already in the map. We fetch those gains, and clamp them with math.max0, so negative branches are treated as 0, because adding a negative path would only make a good path worse. Here we compute the best path that uses this node as the highest point. That path is allowed to take both left and right gains at the same time, forming a full left node right path. We compare it with max sum and update the global best if this one is larger. Finally, we store the node's gain for its parent. A parent path can't fork into both sides, so we only keep the better one of left or right and add the current node's value. Saving this into node gain is what allows the parent to compute its result later. Once the stack is empty, we've computed everything bottom up, and max sum holds the best path sum anywhere in the tree, so we return it. And that's how this algorithm works. It first sets up a global maximum, a stack that simulates post-order traversal, and a map to store downward gains, then processes nodes after their children, clamps negative gains, updates the global best using a 2-branch peak path, and stores a single branch gain for parent extension. Efficient, simple, and elegant. Highlight input box. Root equals 1, 2, 3. Let's run our function using this binary tree. 1, 2, 3. This level order representation describes a simple tree. 1 is the root, 2 is the left child, 3 is the right child. Explain the logic briefly. Our algorithm computes the sum of all node values in the tree. So we simply add them up. 1 plus 2 plus 3 equals 6. No branches, no complications, just a clean traversal and accumulation. Highlight output box. Output, 6, expected, 6, and the output we get is 6, exactly matching the expected result. The test passes perfectly. So, our implementation is correct. The algorithm efficiently traverses the tree and computes the total sum, straightforward and accurate. Quick wrap-up on binary tree maximum path sum, a classic that exposes gaps in recursion, handling negatives, and path splits. We define the goal as finding the highest sum path anywhere in the tree. A path can start and end at any node, may bend through a parent once, and must include at least one node. We highlighted the 2 key ideas. 1, each recursion returns a single-sided best path to its parent, and 2, at every node we also consider a V-shaped path using both children to potentially update a global best. Handling negatives by zeroing them out prevents bad branches from dragging down the sum. Our plan: post-order DFS. For each node, compute the best gain from left and right, never below 0. Consider the full bend through sum at the node to update a global maximum, and return the node's value plus the larger single-sided gain to the parent. We followed that plan end-to-end and ran it on LeetCode without errors. In tests, the approach captured both straight and bending paths correctly, handled all negative trees by choosing the least negative node, and passed the edge cases. The takeaway: separate the value you return upward, single side, from the value you use to update the global best, possible split. Master that distinction and the hardest tree DP style problems get much easier.
Breakdown. Assess. Structure. Implement? Check. 5 steps. Way less panic. PatternMastery.com.
Honestly, I only did patterns. Then they got the offer. PatternMastery.com.
Want to master a problem that appears in system design and algorithm interviews at Google and Meta? Serialize and deserialize binary tree is a Pattern Mastery 100 favorite, testing recursion, edge cases, and even real-world network reliability. Over 40% of candidates get tripped up by nulls or mismatched node orders. Get this right, and you'll unlock the secrets behind saving and restoring complex data structures. Let's tackle serialize and deserialize binary tree using the basic method, a systematic approach that ensures your code is both correct and robust. Let's break this down. Given the root of a binary tree, design an algorithm to serialize, convert into a string, and deserialize, rebuild from string, the tree so that it can be perfectly reconstructed later. Input: root node of a binary tree. Output: serialize root returns a string. Deserialize data reconstructs the tree from that string. Here is a real-world example. Think of saving a user's game progress, or syncing a complex org chart between servers. You need to turn the tree into a format you can store or transmit, then reliably rebuild it on the other side. An interviewer might ask, how would you persist a configuration tree for backup and recovery? Now let's assess. What's tricky? You must record the structure, not just the values. Null nodes matter. Skipping them loses information. Order matters. Children must appear in the right place. Recursive traversal, pre-order or level order, is common. Think step by step. For serialization, traverse the tree, usually pre-order. For each node, record its value. For null children, record a sentinel value, like hash or null. Join values into a string, commas, spaces, etc. For deserialization, split the string into a list. Use recursion to rebuild the tree, reading values in the same order. When you encounter the sentinel, return null for that child. Let's clarify. Why record nulls? Without them, you can't tell if a node had a missing left or right child. Matching the order, pre-order for both serialize and deserialize, keeps logic clear. Edge cases. Empty tree should serialize as an empty string or sentinel. Tree with only left/right children, must handle all arrangements. Here is the structure. Serialize. Use a recursive helper to pre-order traverse. Append values to a result list. For null, append sentinel. Join the result list into a string. Deserialize. Split the string into a queue/list. Use a recursive helper that pops values. If sentinel, return null. Else, build node. Recurse for. Let's try to implement it using solution 1. Efficiency overview. Time complexity. ON. Space complexity. ON. The concept discussion. We're converting a binary tree into a string so it can be stored or sent somewhere, then rebuilding the same tree back from that string. The key idea is pre-order traversal. Node, left, right. While converting, we also write null for missing children so the structure doesn't get lost. While rebuilding, we read the values in the same order and use recursion to reconstruct the exact shape. Here we're turning the tree into a single text string. If a node doesn't exist, we record it as the word null. Otherwise, we record the current node's value first, then we serialize the left subtree, then the right subtree. This current, left, right order is what lets us rebuild the tree later, and writing null is what protects the tree shape from being lost. Now we're going the other direction. String back into a tree. First we split the string by commas so we get an easy-to-read list of pieces, like a queue of values. We also keep an index pointer so we always know which piece we're currently reading, and we move it forward as we rebuild nodes. This helper function is the heart of rebuilding. If the next token is null, that means there is no node here. So we return null and move the pointer forward. That's how we recreate missing children in the exact same spots as before. If the token is a real number, we create a new tree node from it. Then, because the data was stored in node, left, right order, we recursively build the left child next, and then the right child. By following the same order used during serialization, we reconstruct the same structure reliably. Finally, we kick off the rebuild from the start of the token list and return the root node that comes back. That root represents the entire reconstructed tree. And that's how this algorithm works. It first splits the tree into a pre-order string with null placeholders, then reads the tokens in order and recursively rebuilds each node and its children. Efficient, simple, and elegant. Highlight input box. Root equals 1, 2, 3, null, null, 4, 5. Let's test our function on this binary tree. 1, 2, 3, null, null, 4, 5. This level order representation describes the structure like this. 1 is the root. 2 is the left child. 3 is the right child. And under 3, we have 4, left, and 5, right. The two null values simply indicate that node 2 has no children. Explain the logic briefly. Our algorithm serializes, or processes, the tree in the required order and builds the output array representing the same structure. Since the tree already matches the expected layout, and there are no inversions, transformations, or deletions happening, the output should look exactly like the input. Highlight output box. Output: 1, 2, 3, null, null, 4, 5 expected. 1, 2, 3, null, null, 4, 5. And that's exactly what we see. The output matches the expected result perfectly, so the test case is accepted. So, our implementation is correct. The algorithm successfully processes and returns the tree structure exactly as intended, consistent, accurate, and reliable. Let's try to implement it using solution 2. Efficiency overview. Time complexity, ON, space complexity, ON. The concept discussion. This version uses BFS, level order traversal, meaning we scan the tree level by level using a queue. While converting the tree into a string, we also write null whenever a child is missing so we don't lose the shape. Then we trim off extra null values at the end to match the compact format often used on platforms like LeetCode. For rebuilding, we read the tokens from left to right and use another queue to reconnect children in the same level order pattern. First, we handle the simple case. If the tree is empty, we just return the text null. Otherwise, we prepare for level order traversal by placing the root into a queue. We also create an array called result that will collect everything we want to output, node values and null markers, so we can turn it into a final string later. Now we repeatedly pull items from the queue. If we pull out a real node, we record its value and then push its left and right children into the queue, even if those children are missing. If we pull out a missing child, we record the word null. This is important because the null entries preserve the exact shape of the tree, not just the values. After BFS finishes, we may have extra null values at the end that don't add any useful structure info. Those are just missing nodes beyond the last real value. So we pop them off to make the output more compact. Finally, we join everything with commas to produce a single string. To rebuild the tree, we again handle the empty case first. If the data is null or empty, the tree is empty. Otherwise, we split the string into tokens. The first token becomes the root node. Then we put that root into a queue, because we'll rebuild the tree level by level. The pointer tracks which token we should read next. Here's the rebuilding loop. We take the next parent node from the queue, then read the next token for its left child and the following token for its right child. If a token is not null, we create a real node and connect it. And whenever we create a real child node, we push it into the queue, because it will later become a parent for the next level. Step by step, this reconstructs the full tree in the same level order shape used during serialization. And that's how this algorithm works. It first sets up a BFS queue and records values plus null placeholders, then trims trailing nulls, then rebuilds the tree level by reading tokens in order and attaching left and right children with a queue. Efficient, simple, and elegant. Highlight input box. Root equals 1, 2, 3, null, null, 4, 5. Let's test our function on this binary tree. 1, 2, 3, null, null, 4, 5. This level order representation describes the structure like this. 1 is the root. 2 is the left child. 3 is the right child. And under 3, we have 4, left, and 5, right. The two null values simply indicate that node 2 has no children. Explain the logic briefly. Our algorithm serializes, or processes, the tree in the required order and builds the output array representing the same structure. Since the tree already matches the expected layout, and there are no inversions, transformations, or deletions happening, the output should look exactly like the input. Highlight output box. Output: 1, 2, 3, null, null, 4, 5 expected. 1, 2, 3, null, null, 4, 5. And that's exactly what we see. The output matches the expected result perfectly, so the test case is accepted. So, our implementation is correct. The algorithm successfully processes and returns the tree structure exactly as intended, consistent, accurate, and reliable. Quick recap of serialize and deserialize binary tree. This problem is the bridge between interview algorithms and real-world persistence. Save a tree as text, then rebuild it exactly, nulls and all. We needed two operations: turn a tree into a string, serialize, and reconstruct the identical tree from that string, deserialize. The core requirement was preserving both values and structure, which means null nodes had to be explicitly recorded. We called out the common traps: forgetting nulls, mixing traversal orders, or losing child positions. A consistent traversal, like preorder, plus a sentinel for nulls prevents ambiguity and guarantees a perfect round trip. Our plan, during serialization, perform a preorder walk and append either the node's value or a sentinel, for example hash, to the output sequence. During deserialization, read the sequence in the same order, creating nodes for values and returning null at sentinels, recursing left, then right. We followed that plan end-to-end and ran the solution on LeetCode, clean execution, no errors. In tests, strings like 1, 2, hash, 3, 4, hash, 5, hash reconstructed the exact original tree, and edge cases, like an empty tree, were handled correctly. All test cases passed. The takeaway: structure must be encoded, not inferred. Pair a fixed traversal order with explicit null markers, and you'll reliably serialize complex trees in interviews and production systems alike.
The interviewer smiled. Not because you were right, because they knew you were lost. Learn to spot the pattern before they spot the panic. PatternMastery.com.
Want to prove you really understand recursion and tree structure? Subtree of another tree is a PatternMastery 100 favorite, and a classic test at Google and Amazon for algorithmic reasoning and code reuse. Over 30% of candidates miss a subtle check or edge case. If you can solve this confidently, you'll show you can handle complex recursive comparisons and tree pattern matching. Let's crack subtree of another tree using the basic method, so you always stay systematic and interview-proof. Now let's break this down. You're given two binary trees, root and subroot. Determine if subroot is a subtree of root. In other words, if there's a node in root where the tree rooted at that node is identical to subroot. Input: two binary tree root nodes, root and subroot. Output: Boolean: true if subroot is a subtree of root, false otherwise. Here is real-world example. Imagine you're managing file systems or XML or HTML documents as trees, and you need to check if a particular snippet, subtree, exists within a larger structure, without flattening them. An interviewer might ask, how would you check if a certain configuration or code block is present within a larger config tree? Now let's assess it. What's tricky? You need to traverse the main tree, root, and, at each node, check if the subtree starting there is identical to subroot. Reuse same tree logic for equality check. Recursion is your friend, but you must remember to check at every possible starting node. Let's think step by step. If root is null, there's no tree to match, return false. At each node, check: is the tree starting here the same as subroot? Use a helper function: is same tree. If not, recursively check both left and right subtrees of root. The answer is true if any check succeeds. Let's go deeper. Is same tree recursively compares node values and structure, so it's a perfect subroutine. You have to check every node in root, not just where the values match at the top. Here are some edge cases. Both trees empty, should return true. Subroot is larger than root, should return false. Subroot not present anywhere in root, should return false. Here is the structure. If root is null, return false. If is same tree root, subroot, returns true, return true. Recursively check subtree of left and subtree of right. Return true if any check passes. Now let's try to implement it using solution 1. Efficiency overview. The time complexity is OM times n, and the space complexity is OM plus n, where m is the number of nodes in root, and n is the number of nodes in subroot. This helper checks whether two trees are structurally identical and have the same values. Both nodes must match, and their left and right subtrees must also match. If we reach a null node in the main tree, there's nothing left to compare, so we return false. At each node of the main tree, we check whether the subtree starting here matches subroot. If it does, we've found our answer. If the current node doesn't match, we recursively search the left and right subtrees. Finding a match in either side is enough. If none of the nodes in the main tree produce a match, the function eventually returns false. And that's how this algorithm works. It first traverses the main tree using DFS, then repeatedly compares subtrees to the target tree until a match is found or all nodes are exhausted. Efficient, simple, and elegant. Let's test our function using this input. We're checking whether subroot exists as an exact subtree inside root. We traverse the main tree and compare each node with the root of subroot. When we reach the node with value 4 in the main tree, its structure and values match subroot. Both the left child 1 and the right child 2 match exactly. Since both the structure and node values align perfectly, subroot is indeed a subtree of root. And that's exactly what our program returns, true. So, our implementation is correct. The algorithm accurately compares subtrees and detects exact matches, efficient and precise. Now let's try to implement it using solution 2. Efficiency overview. The average time complexity is OM plus n, and the space complexity is OM plus n, where m is the number of nodes in root, and n is the number of nodes in subroot. This helper converts a tree into a string using preorder traversal. Each node value is prefixed with a marker, and null children are explicitly recorded as x. This guarantees a unique representation of the tree structure. Without recording null nodes, different tree shapes could serialize to the same string. The X marker prevents structural ambiguity and avoids false positives. Once both trees are serialized, we simply check whether the smaller tree string appears inside the larger one. If it does, subroot exists as a subtree of root. If the serialized subroot string is found inside the serialized root string, we return true. Otherwise, the result is false. And that's how this algorithm works. It first serializes both trees using preorder traversal with null markers, then checks whether the serialized subtree appears as a substring of the serialized main tree. Efficient, simple, and elegant. Let's test our function using this input. We're checking whether subroot appears as an exact subtree inside root. We traverse the main tree and compare each possible subtree with subroot. We find a node with value 4, which looks like a potential match at first. However, its subtree structure is different. The node 2 has an extra child 0 in the main tree. Since subtree matching requires both values and structure to be identical, this difference causes the comparison to fail. And that's exactly what our program returns, false. So, our implementation is correct. The algorithm properly detects structural mismatches and avoids false positives, accurate and reliable. So, that's subtree of another tree, a deceptively simple question that really tests how well you understand recursion and structural comparison in binary trees. Let's do a recap. At its core, this problem asks, can we find a smaller tree, subroot, perfectly nested somewhere inside a larger tree, root? Conceptually, it's like checking if a certain pattern or section exists within a much bigger hierarchy, without flattening or simplifying anything. We explored how the challenge isn't just comparing values, it's about comparing entire structures. We reuse the logic from the same tree problem, but the key twist is that we must perform that comparison at every node of the main tree until we find a match. The plan was straightforward. If the main root is null, return false. Otherwise, check if the subtree starting at this node matches subroot using the helper function. If not, move down to the left and right subtrees and repeat the process. It's a clean, recursive structure that ensures every possible subtree gets checked. We put that logic into code, recursively traversing the main tree, using the helper to verify structural and value equality, and ensuring no node was skipped. Finally, we ran the solution through LeetCode. It handled all the test cases, true when subroot existed, false when it didn't, and accurate even on edge cases like empty trees. Everything executed without errors. The key takeaway? Recursion shines when the problem mirrors itself at smaller levels. By breaking the comparison into smaller identical checks, you prove not just coding skill, but deep understanding of how trees think. Can you rebuild a tree from just its travel diaries? Construct binary tree from preorder and in-order traversal is a PatternMastery 100 cornerstone, regularly asked at Amazon, Apple, and Google to test your deep understanding of recursion and tree building. Over 35% of candidates miss subtle index bugs or don't manage recursion boundaries right. Let's break it down so you don't. We'll use the basic method to solve construct binary tree from preorder and in-order traversal, giving you a powerful template for any tree reconstruction problem. Let's break this down. Given two arrays representing the preorder and in-order traversals of a binary tree, with no duplicates, reconstruct the original binary tree. Input: preorder. Nodes visited as root, left, right. In order. Node is visited as left, root, right. Output: root of the reconstructed binary tree. Here is a real-world example. Imagine restoring a company's org chart from two different reports, one listing employees as visited in order of management, preorder, the other listing them by their department or hierarchy, in order. Interviewers might ask, how would you reconstruct a configuration or parse tree if you only had two traversals? Let's assess. What's tricky? You must know how preorder and inorder traversals uniquely determine a tree. The first value in preorder is always the root. In an order, everything to the left of the root is the left subtree. Everything to the right is the right subtree. Think step by step. Use a pointer or index to track the current root in preorder. Use a hash map to quickly find root positions in an order, to split left and right. Recursively, pick root from preorder. Find its index in an order. Recursively build the left subtree, from an order left split. Recursively build the right subtree, from an order right split. Advance the preorder pointer at each recursive call. Let's clarify. Always slice the in-order array to define subtrees. Preorder's root pointer moves forward every time you build a new node. Base case, if there's nothing left to build, left index greater than right, return null. Edge cases, empty lists, should return null. Single node builds a leaf. Deeply skewed trees, for example, all left or all right children. Here is the structure. Build a hash map of value index for an order for O1 lookups. Create a recursive function with left/right boundaries for an order. At each call, use the current preorder index for the root value. Increment preorder index for the next call. Recursively build left subtree, in order left split. Recursively build right subtree, in order right split. Return the constructed node. Now let's try to implement it using solution 1. Efficiency overview. The time complexity is O(n), and the space complexity is O(n), where n is the number of nodes. We create a map from node value to its index in the in-order traversal. This lets us instantly locate the root in the in-order array instead of searching linearly. This recursive function builds a subtree using index boundaries instead of slicing arrays. The parameters define the current preorder and in-order ranges. When the current range is invalid, it means there are no nodes left to build, so we return null. The first element of the preorder range is always the root of the current subtree. We create a new tree node using this value. We find the root's position in the in-order array. Everything to the left belongs to the left subtree, and its size tells us how to split preorder. We recursively build the left and right subtrees using the calculated index ranges. Once both subtrees are built, we return the root of the current subtree. And that's how this algorithm works. It first identifies roots using preorder traversal, then uses in-order traversal to split left and right subtrees, recursively rebuilding the entire binary tree in linear time. Efficient, simple, and elegant. Let's test our function using this input. We're reconstructing a binary tree using its preorder and in-order traversal sequences. In preorder traversal, the first element is always the root. So we start with 3 as the root of the tree. In the in-order traversal, everything to the left of 3 belongs to the left subtree, and everything to the right belongs to the right subtree. Left subtree in order, 9. Right subtree in order, 15, 20, 7. We repeat the same process recursively. The left subtree root is 9. The right subtree root is 20, with children 15 and 7. And that's exactly what our program produces. So, our implementation is correct. The algorithm correctly reconstructs the tree by leveraging the properties of preorder and in-order traversals, accurate and efficient. Now let's try to implement it using solution 2. Efficiency overview. The time complexity is O(n), and the space complexity is O(n), where n is the number of nodes. We start by creating the root from the first preorder value. The stack tracks the path of nodes whose right child is not yet assigned. In-order index tells us how far we've progressed in the in-order traversal. We iterate through preorder and create nodes in the exact order they appear. Each node must be attached either as a left or right child. If the top of the stack hasn't appeared in order yet, we're still building its left subtree. So the new node becomes a left child. When the stack top matches the in-order value, it means the left subtree is complete. We pop nodes until we find where the right child should go. The new node becomes the right child of the last pop node. After processing all preorder values, the tree is fully constructed, and we return the root. And that's how this algorithm works. It first builds nodes in preorder order, then uses a stack and in-order traversal to decide exactly when to attach left versus right children, reconstructing the tree iteratively in linear time. Efficient, simple, and elegant. Let's test our function using this input. Here, both traversals contain a single value, which represents a tree with just one node. In preorder traversal, the first and only value -1 is the root. Since the in-order traversal also contains only -1, there are no left or right subtrees to construct. The recursion stops immediately, and the tree consists of just this one node. And that's exactly what our program returns. So, our implementation is correct. The algorithm cleanly handles the simplest case and correctly reconstructs a single node binary tree. Rebuilding a tree from its travel diaries sounds tricky, but with pre-order and in-order you've got a perfect roadmap. This is a classic interview favorite because it exposes whether you truly understand recursion, boundaries, and tree structure. Let's do a recap. We're given two traversals of the same binary tree: pre-order, root, left, right, and in-order, left, root, right. The goal is to reconstruct the original tree. Think of it like restoring an org chart from two reports, one in visit order, one in hierarchical order. We leaned on two core truths. The first item in pre-order is always the root, and in in-order, everything left of that root is the left subtree and everything right is the right subtree. The main pitfalls? Mismanaging indices and not respecting subtree boundaries as recursion unfolds. Our plan: create a fast lookup from value to its position in the in-order list. Use a moving position in pre-order to pick the next root. Then, with left/right bounds in the in-order range, recursively build the left subtree from the left side of the split and the right subtree from the right side. Stop when the current in-order window is empty. We followed that blueprint, advancing the pre-order position each time we formed a new node and using the in-order boundaries to keep each recursive call in its lane. No extra slicing work, just clean boundary management. We ran the solution on LeetCode. It constructed the sample tree correctly, handled empty input as null, built a single node tree for the one-element case, and coped with skewed trees. All tests passed without errors and the logic behaved exactly as expected. The big lesson: tree reconstruction is all about disciplined boundaries. Anchor each step on pre-order's next root, let in-order define the left/right regions, and let recursion do the assembly. Get the indices right, and the entire tree falls perfectly into place.
Rejected. 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 At some point, it is not bad luck. It is bad prep. PatternMastery.com.
Think you know your trees? Validate Binary Search Tree is a PatternMastery 100 essential and a classic filter in Google, Amazon, and Microsoft interviews. Nearly 1 in 3 candidates get tripped up by subtle edge cases or misuse of recursion. Master this, and you'll be ready for any problem that tests understanding of tree invariants and value constraints. Let's use the basic approach to tackle Validate Binary Search Tree so you'll never miss a hidden bug or boundary case. Let's break it down. Given the root of a binary tree, determine if it's a valid binary search tree, BST. For every node, all values in its left subtree must be less than the node's value, and all values in its right subtree must be greater than the node's value. Input: root node of a binary tree. Output: Boolean. True if the tree is a valid BST, otherwise false. Here is a real-world example. Suppose you're maintaining a database index tree. If the tree violates BST rules, searches become incorrect or inefficient. An interviewer might ask, how would you validate a config tree to ensure proper ordering for efficient range queries? Let's assess. What's tricky? A common mistake is to just compare each node with its immediate children, but BST rules require every value in the left subtree to be less than the current node, and every value in the right subtree to be greater, all the way down. Think step by step. Use recursion with value boundaries. Each time you descend left, update the upper bound, current node's value. Each time you descend right, update the lower bound. If any node violates these constraints, the tree isn't a BST. Let's go deeper. Start with the full possible value range. Example: from -infinity to +infinity. At every node, if the value isn't strictly within min, max, return false. Recursively validate left and right subtrees, passing updated bounds. Edge cases: duplicate values are not allowed in a BST, must be strictly less/greater. An empty tree is a valid BST. Subtle violations deep in the tree. Example is a right child of a left subtree is greater than root, must be caught. Here is the structure. Write a helper function with node, min, and max parameters. If node is null, return true. If node's value not in min, max, return false. Recursively validate left subtree, max equals node's value. Recursively validate right subtree, min equals node's value. Return true only if both subtrees are valid. Now let's try to implement it using solution 1. Efficiency overview. The time complexity is O(n), and the space complexity is O(n), where n is the number of nodes in the tree. We initialize a stack to simulate recursion. Preval stores the value of the previously visited node during in-order traversal. We start traversal from the root. This loop continues as long as there are nodes left to process, either in the stack or via the current pointer. We keep moving left, pushing nodes onto the stack, until we reach the leftmost node. When we visit a node, we compare its value with the previously visited value. If it's not strictly greater, The BST property is broken. We update prev_val and then move to the right subtree to continue the in-order traversal. If all nodes are visited in strictly increasing order, the tree is a valid BST. And that's how this algorithm works. It performs an in-order traversal using a stack, checking that each node's value is greater than the last to confirm the binary search tree property. Efficient, simple, and elegant. Let's test our function using this input. We need to verify whether the given binary tree satisfies the binary search tree, BST, property. For a valid BST, all values in the left subtree must be less than the current node. All values in the right subtree must be greater than the current node. In this tree, the root is 2. Its left child is 1, which is less than 2. Its right child is 3, which is greater than 2. All nodes satisfy the BST constraints. And that's exactly what our program returns, true. So, our implementation is correct. The algorithm properly enforces BST rules and validates the tree accurately. Now let's try to implement it using solution 2. Efficiency overview. The time complexity is O(n), and the space complexity is O(n), where n is the number of nodes in the tree. This helper function validates a subtree by ensuring every node value stays within a permitted range. A null node is valid by definition, so we return true and continue. Each node must be strictly greater than low and strictly less than high. If this condition fails, the BST property is violated immediately. We recursively validate the left subtree with an updated upper bound, the right subtree with an updated lower bound. We start with the widest possible bounds, allowing the root to take any value. And that's how this algorithm works. It first enforces global value bounds at every node, then recursively tightens those bounds as it traverses left and right subtrees to guarantee the binary search tree property. Efficient, simple, and elegant. Let's test our function using this input. We're checking whether this tree satisfies the binary search tree rules. The BST property requires that all values in the left subtree of a node are smaller than the node. All values in the right subtree are larger than the node. Here, the root is 5. The right child is 4, which is already less than 5, violating the BST rule. Even though 3 is less than 4 and 6 is greater than 4, the entire right subtree must contain values greater than 5, which is not the case. And that's exactly what our program returns, false. So, our implementation is correct. The algorithm correctly detects violations that occur deeper in the tree, not just at direct child nodes, accurate and reliable. So, how do you really know if a tree is behaving like a proper binary search tree? Validate binary search tree is the perfect check of whether you understand how recursion and constraints flow through a tree's structure. Let's do a recap. The problem asks us to confirm if a given binary tree follows BST rules, meaning every node's left subtree has smaller values, and every right subtree has larger values. Conceptually, it's about keeping the entire structure ordered, not just comparing neighbors. We discussed how many people slip by only checking parent-child pairs. The trick is realizing that each subtree inherits boundaries from its ancestors. As we move down, we must update those value limits, shrinking the valid range for each recursive call. Our logic was simple but powerful. Start with a wide range, say from negative to positive infinity. For each node, verify it fits within that range. Then, move left with an updated upper bound and move right with an updated lower bound. The recursion ends cleanly when all nodes fit their limits. We coded this recursive check, starting from the root and passing updated boundaries as we traversed. The function neatly returned true or false depending on whether every node respected its constraints. Running the solution on LeetCode confirmed it works perfectly. Valid BSTs passed as true, invalid ones returned false, and tricky edge cases, like deep violations or empty trees, were all handled correctly without errors. The key takeaway: a valid BST isn't about direct neighbors, it's about inherited rules. Mastering that recursive boundary mindset ensures you won't miss hidden violations buried deep in the tree.
This is not another random playlist. It is a roadmap. Patterns, structure, repetition. The stuff that actually sticks. PatternMastery.com.
Did you know KTH smallest element in a BST is a PatternMastery 100 essential and a go-to question at Google, Facebook, and Amazon to test your mastery of binary search tree properties and tree traversal? Over 30% of candidates stumble on this, either by missing the in-order pattern or handling K incorrectly. Nail this problem, and you'll be ready for everything from ranking queries to real-time analytics. Let's use the basic framework to tackle Keith's smallest element in a BST step by step, so you'll be confident and clear in every interview. Let's break it down. Given the root of a binary search tree, BST, and an integer k, find the Keith's smallest value. 1 indexed, in the tree. Input, root node of a BST, integer k. Output, integer value of the kth smallest element. Here is a real-world example. Imagine managing a leaderboard where you need to find the kth top performer. Or, in a scheduling app, finding the kth earliest event among time slots stored in a BST. An interviewer might ask, how would you efficiently find the median or percentile rank in a huge, dynamically changing dataset? Let's assess. What's tricky? A BST's in-order traversal, left root right, produces sorted values. The challenge is to traverse efficiently and stop exactly at the kth value. Think step by step. Perform an in-order traversal of the BST. Use a counter to keep track of how many nodes you've visited. Once the counter reaches k, record the node's value and stop. Be careful, do not keep traversing after finding the kth node. Let's clarify. You can do this recursively or iteratively, using a stack. If the tree is very large and k is small, the traversal short-circuits early. Edge cases. K is 1, smallest, k is tree size, largest. Here is the structure. Initialize a counter, starting at 0, and a variable to store the result. Traverse the tree in order, left root right. At each node, increment the counter. If counter equals k, record the node's value and return immediately. Return the result. Now let's try to implement it using solution 1. Efficiency overview. The time complexity is O(n), and the space complexity is O(n), where n is the number of nodes in the tree. We use a stack to simulate recursion for in-order traversal. Count tracks how many nodes we've visited so far. This loop keeps running as long as there are nodes left to process. We always go as far left as possible first, because in-order traversal visits left children before the current node. When we pop from the stack, we're visiting the next smallest value in the BST. We increment the visit counter. As soon as we visited the kth node, we return its value immediately. There's no need to traverse the rest of the tree. After visiting a node, we move to its right subtree to continue the in-order traversal. And that's how this algorithm works. It performs an in-order traversal of the BST, counting nodes in ascending order, and returns the value of the kth visited node. Efficient, simple, and elegant. Let's test our function using this input. We're asked to find the first smallest element in a binary search tree. In a BST, an in-order traversal visits nodes in sorted, ascending, order. Performing in-order traversal on this tree gives 1, 2, 3, 4. The first smallest element in this ordered sequence is 1. And that's exactly what our program returns. So, our implementation is correct. By leveraging the in-order property of BSTs, the algorithm efficiently finds the kth smallest element. Now let's try to implement it using solution 2. Efficiency overview. The time complexity is O(n) plus k log n, and the space complexity is O(n). This class implements a standard min heap from scratch. The smallest value is always kept at the top, allowing efficient removal. We create an empty heap that will store all values from the tree. We traverse the entire tree using DFS. Every node value is inserted into the heap, regardless of position. We remove the smallest element k 1 times. The next value popped is the kth smallest element. The final pop gives us exactly the kth smallest value stored in the tree. And that's how this algorithm works. It first gathers all node values using a full tree traversal, stores them in a minute heap, then repeatedly removes the smallest elements until the kth1 is reached. Efficient, simple, and elegant. Let's test our function using this input. We need to find the third smallest element in a binary search tree. In-order traversal of a BST produces values in ascending order. For this tree, the in-order sequence is 1, 2, 3, 4, 5, 6. The third smallest element in this list is 3. And that's exactly what our program returns. So, our implementation is correct. The algorithm correctly uses the BST's ordering property to locate the kth smallest element efficiently. Finding the kth smallest element in a BST is one of those problems that looks simple, until you realize how much it reveals about your grasp of tree structure and traversal. This one tests whether you truly understand how BST ordering naturally connects to in-order traversal. Let's do a recap. Conceptually, the problem is about ranking within a tree. We're given a BST and a number k, and we need the kth smallest value. Because a BST's in-order traversal visits nodes in sorted order, our goal becomes, traverse in order, and stop at the kth step. The key insight here is that you don't need to sort anything manually. The BST structure does that for you. The challenge is controlling traversal flow and counting visits correctly. Whether you choose recursion or a stack-based approach, stopping at exactly the right moment is what keeps the solution efficient. We built the plan like this. Start an in-order traversal, move left first, Visit the node, then move right. Keep a running counter of visited nodes. When the counter equals k, capture that value and stop traversing. That's the entire sorted order distilled into one clean recursive flow. We implemented that logic using either recursion or an iterative stack. Each node visit increased the count, and when the count matched k, we returned the node's value immediately. No unnecessary traversal or extra data structures were needed. Testing on LeetCode confirmed the method's precision. For k equals 3, the traversal sequence 1, 2, 3, 4, 5, 6 correctly returned 3. Edge cases, like k equals 1 or k equals number of nodes, also worked flawlessly, proving the counter logic and traversal control were solid. The big takeaway? The in-order traversal is your built-in sorted list for BSTs. By combining it with precise counting, you can extract ranked elements directly from structure. No sorting, no arrays, just pure logic.
LeetCode says medium. Your nervous system says boss fight. That is your sign you need pattern training. PatternMastery.com.
Ever wondered what makes tree interviews both tricky and fun? Lowest common ancestor of a binary search tree is a PatternMastery 100 favorite, routinely used by Google, Facebook, and Amazon to test how well you exploit BST properties. More than 30% of candidates overcomplicate it or miss the power of BST traversal. Let's make sure you're not one of them. Let's solve lowest common ancestor of a BST using the basic framework, a stepwise guide that ensures you never miss an optimization or edge case. Now let's break this down. You're given the root of a binary search tree, BST, and two nodes, P and Q. Your task? Find their lowest common ancestor, LCA, the deepest node in the tree that has both P and Q as descendants. Input, root node of a BST, and two node references P and Q. Output, the node representing their lowest common ancestor. Here is a real-world example. Imagine managing folder permissions in a company's shared drive. To find the closest shared folder for two users' files, you need the LCA. Or, in a genealogy tree, to find the nearest shared ancestor between two people. Let's assess it. What's tricky? With a normal binary tree, you'd need to search both subtrees recursively. But in a BST, every node's left children are smaller, and right children are larger, so you can leverage value comparisons to avoid unnecessary work. Now let's think step by step. Start at the root. If both P and Q are less than root, both nodes are in the left subtree, go left. If both P and Q are greater than root, both nodes are in the right subtree, go right. Otherwise, root is between P and Q, or equals one of them, that's the split point, and the LCA. Let's clarify. You don't need to visit every node. BST ordering lets you home in on the ancestor in OH time, where H is tree height. Edge cases. One node is ancestor of the other. Nodes are on different sides of root. Root is LCA. Here is the structure. Start at root. While root is not null, if both P and Q are less than root, go left. If both are greater than root, go right. Else, root is the LCA, return it. If root becomes null, shouldn't happen for valid input, return null. Now let's try to implement it using solution 1. Efficiency overview. The time complexity is OH, and the space complexity is O1, where H is the height of the BST. We start from the root and move downward, using a single pointer to traverse the tree. If both target nodes are smaller than the current node, their lowest common ancestor must lie in the left subtree. If both target nodes are larger than the current node, their lowest common ancestor must lie in the right subtree. When one node is on the left and the other is on the right, or one of them equals the current node, we found the split point. That node is the lowest common ancestor. This line is a safety fallback. In a valid BST with valid inputs, the LCA will always be found before this. And that's how this algorithm works. It walks down the BST using value comparisons, narrowing the search space at each step until it finds the node where the paths to both targets diverge. Efficient, simple, and elegant. Let's test our function using this input. We're asked to find the lowest common ancestor, LCA, of two nodes in a binary search tree. In a BST. If both P and Q are less than the current node, we move left. If both are greater than the current node, we move right. Otherwise, the current node is where the paths split. That node is the LCA. In this case, P equals 2 is in the left subtree. Q equals 8 is in the right subtree. So their paths diverge at the root node 6. And that's exactly what our program returns. So, our implementation is correct. The algorithm efficiently uses BST properties to locate the lowest common ancestor, accurate and optimal. Now let's try to implement it using solution 2. Efficiency overview. The time complexity is OH, and the space complexity is OH, where H is the height of the BST. This helper walks down the BST from the root to the target node, recording every node encountered along the way. Thanks to BST ordering, the path is uniquely determined. We compute two root to node paths, one for P and one for Q. We walk through both paths simultaneously. As long as the nodes match, we update the LCA. The first mismatch means the paths have diverged. The last shared node before divergence is returned as the lowest common ancestor. And that's how this algorithm works. It first records the paths from the root to each target node, then scans those paths to find the last common node where the paths overlap. Efficient, simple, and elegant. Check number 2. Let's test our function using this input. We're finding the lowest common ancestor, LCA, of two nodes in a binary search tree. In a BST, if both values are smaller than the current node, we move left. If both are larger, we move right. Otherwise, the current node is the point where the paths meet or split. Here, one node is 2. The root itself, the other node 1, lies in the left subtree. Since the root node 2 is an ancestor of itself and also of node 1, it is the lowest common ancestor. And that's exactly what our program returns. So, our implementation is correct. The algorithm correctly handles cases where one node is an ancestor of the other, efficient and reliable. If BST questions ever felt abstract, this one makes them click. The lowest common ancestor of a BST shows how a tiny ordering rule can guide you straight to the answer without searching everything. Let's do a recap. We're given a BST plus two nodes, P and Q. The goal is to return the lowest common ancestor, the deepest node that has both P and Q in its subtree. In plain terms, the closest shared parent in a value-ordered tree. The key advantage is the BST property. Left subtree values are smaller, right subtree values are larger. Instead of exploring both sides like a general tree, we compare P and Q against the current node's value to decide which single direction to go, or to stop at the exact split point. Start at root and loop, or recurse, with 3 simple checks. If P and Q are both smaller than the current node, go left. If both are larger, go right. Otherwise, you've hit the split, or matched one of the nodes, and that current node is the LCA. We followed that plan directly, using straightforward comparisons at each step. No extra data structures, no exhaustive search, just clean movement left or right until the split point appears. We ran it on LeetCode and verified the logic. When P and Q sit on opposite sides, the root at the split is returned. When one is an ancestor of the other, that ancestor is the answer. Edge cases like the root being one of the targets and tiny trees behaved exactly as expected, and everything executed without errors. The takeaway, in a BST, order is a compass. Let value comparisons guide your traversal, and the LCA reveals itself in OH time. No backtracking, no fuss.
You thought your job was safe until you got that email. Now you're back on LeetCode remembering you forgot everything about trees and graphs. Interviewer says, solve this in O of n. Your brain says, 404, solution not found. Don't be that person. Subscribe to PatternMastery.com and master the coding patterns FANG companies actually test.
Breakdown. Assess. Structure. Implement. Check. 5 steps. Way less panic. PatternMastery.com.
Ever wonder how Google and Apple autocomplete searches so quickly? Implement try, prefix tree, is a PatternMastery 100 staple, and a favorite at top tech interviews for testing your ability to design efficient string data structures. Over 30% of candidates struggle to code correct insert, search, and prefix logic under pressure. Master the try, and you'll ace not just interviews, but also real-world search systems. Let's break down implement try, prefix tree, with the basic framework, a powerful way to design and implement complex structures in interviews. You're asked to build a data structure that supports 3 operations. Insert, word, adds a word to the try. Search, word, returns true if the word is in the try. Starts with prefix, returns true if there's any word in the try that starts with the given prefix, input/output. Insert and query words/prefixes, all lowercase English letters. Try supports OL time per operation, where L is the length of the word/prefix. Picture a search engine's autocomplete, or a phone book lookup that instantly finds all contacts by prefix. Interviewers might ask, how would you optimize prefix queries in a massive dictionary or suggest words in a typing app? What's tricky? You need efficient insert/search/prefix checks, all in OL time. The structure must handle a dynamic set of words with overlapping prefixes. Avoid confusion between a node being a prefix and being the end of a valid word. Think step by step. Represent the trie as a tree where each node is a letter, and paths from the root to nodes spell words/prefixes. Each node contains a mapping from characters to child nodes, usually a fixed-size array for 26 letters, or a hash map. A Boolean flag indicating if a word ends at this node is _end. For insert, word. Start at the root for each character, create or move to the child node. After the last character, mark is _end true. For search, word. Walk down the tree per character. After the last, return true if is _end is set. For starts with, prefix. Same as search, but return true as long as you reach the last prefix character. Let's clarify. Insert and search both use the same traversal logic. Only difference, search checks is _end. Starts with doesn't. Try saves huge space on repeated prefixes compared to storing all possible words. Edge cases. Empty string insert/search. Prefixes that are full words versus partial prefixes. Define a trie node class. Children, mapping for 26 letters, array or dictionary is _end. Boolean for word end. Trie class. Root node, empty methods. Insert, search, starts with. For each operation, loop character by character, branching through the tree. Now let's try to implement it using solution 1. Efficiency overview. The time complexity is OM per operation, and the space complexity is O total characters, where M is the length of the input word or prefix. Each trie node stores a map of child characters to nodes, a flag indicating whether this node ends a valid word. The trie starts with a single root node that represents an empty prefix. We walk character by character. Create nodes when needed. Move deeper into the tree. Mark the final node to signal a complete word. To confirm a word exists, we must be able to follow every character. The final node must be marked as a word ending. For prefixes, we only care that the path exists. We don't need the final node to mark a complete word. And that's how this algorithm works. It first builds a character by character tree structure, then efficiently supports word insertion, exact searches, and prefix checks by walking shared paths. Efficient, simple, and elegant. Let's test our trie implementation using this sequence of operations. A trie, prefix tree, stores words character by character and allows fast word lookup and prefix checks. The trie is initialized null. We insert apple into the trie. Searching for apple returns true, since the full word exists. Searching for app returns false, because app is only a prefix so far, not a complete word. Checking starts with app returns true, because apple starts with app. We then insert app as its own word. Searching for app now returns true, since it was explicitly inserted. And that's exactly what our program returns. So, our implementation is correct. The trie correctly distinguishes between full words and prefixes while supporting efficient insert, search, and prefix queries. Solution 2. Approach. An array with a fixed size of 26 characters. Time complexity, OM per operation. Space complexity, O total characters. Each node keeps an array of 26 slots, one for each lowercase letter. This allows constant time access to child nodes without hashing. The trie begins with a root node representing an empty prefix. Each character is converted into an array index by subtracting the ASCII value of the letter A. That maps A to index 0, B to index 1, and so on. We create child nodes as needed and move down the trie character by character. At the end, we mark the node as a completed word. If any character path is missing, the word does not exist. The final node must also be marked as a word ending. For prefixes, we only verify that the path exists. The word does not need to end here. And that's how this algorithm works. It builds a prefix tree using fixed size arrays for fast character access, enabling efficient word insertion, exact lookup, and prefix queries with predictable performance. Efficient, simple, and elegant. Let's test our trie implementation using this input. A trie, prefix tree, stores words character by character and supports fast searches and prefix checks. The trie is initialized null. We insert the word apple. Searching for apple returns true because the word exists. Searching for app returns false since it's only a prefix at this point. Checking starts with app, returns true, because apple begins with app. We then insert app as a complete word. Searching for app now returns true. And that's exactly what our program returns. So, our implementation is correct. The trie accurately handles inserts, full word searches, and prefix checks, reliable and efficient. Autocomplete isn't magic, it's structure. Implement trie, prefix tree, turns fast prefix lookups into a simple, repeatable pattern. Nail this, and you're designing the backbone of search suggestions and instant lookups. Let's do a recap. We built a data structure that supports 3 core operations. Insert a word, check if a full word exists, and check if any word starts with a given prefix. Each operation works in OL time, where L is the length of the input word or prefix. The main challenges were keeping operations efficient, sharing overlapping prefixes to save space, and clearly distinguishing between this path exists and this path is a complete word. That last point, marking word ends, is where many implementations go wrong. Conceptually, the trie is a rooted tree where each edge represents a character. Every node stores a set of outgoing character links to children, a Boolean flag indicating whether a complete word ends at that node. Insert, search, and starts with all walk the same path character by character. The only difference is whether we require that end of word flag at the finish. We followed that plan precisely, traversed from the root, created nodes as needed on insert, checked for missing links during queries, and relied on the end of word flag to distinguish full matches from mere prefixes. We ran the solution on LeetCode, no errors. Our tests confirmed the behavior. After inserting apple, a full word search for apple returned true, app returned false until we inserted it, and starts with app, correctly returned true the whole time. Edge cases like empty strings and missing prefixes behaved as expected and passed the LeetCode checks. The big takeaway: the trie turns repeated work into shared structure. By separating path exists from word ends here, you get fast, reliable prefix queries, exactly what high-performance search features need.
Wake up. Work. Scroll jobs. Do random LeetCode. Feel behind. Repeat. Break the loop. PatternMastery.com.
What happens when you need Google-level search plus support for wildcards? Design, add, and search words data structure is a PatternMastery 100 favorite and a must-know at top tech interviews, blending trie design with recursive search logic. Over 35% of candidates fumble the wildcard or get stuck on recursion. Let's make sure you're ready to shine. Let's break down design, add, and search words data structure using the basic approach, step by step, to cover all the nuances of both trie operations and pattern matching. Build a data structure that supports add word. Adds a word into the data structure. Search word. Returns true if the word exists. Where. Can represent any letter. Wildcard. Input/output. Supports any lowercase word. Search may include. As a wildcard. Needs to handle both standard word lookups and pattern matches efficiently. Imagine a code search tool that must find variables or function names with partial information, like foo.bar matching foobar and foobar. An interviewer might ask, how would you design a dictionary with fast wildcard search for autocomplete or spell checking? What's tricky? Standard trie can handle prefix search, but now you need to support period wildcards, which can match any character at a position. Recursive, DFS, search is required. When you hit period, you must explore all child nodes at that level. Must distinguish between matching a word's full length, is _end, and just matching a prefix. Think step by step. Use a trie node class, children, letter node, and is _end Boolean. Add word. Same as regular trie insert, follow/create nodes for each letter, set is _end at the end. Search, word. Walk down the trie for each character. If current char is not period, follow the child node as usual. If current char is period, recursively try all children at this node. At the end of the word, return true only if the is_end is set. Use recursion to handle branching at period efficiently. Let's clarify. The wildcard search will branch out at each period, but prunes quickly if a child doesn't exist. The structure is the same as a standard trie, but search must explore all possible matching paths when wildcards are present. Edge cases. Multiple wildcards, for example. A. E. Empty string, should only match if empty word was added. Search for word longer than any added, should return false trie node. Children. Dictionary for each letter is _end. Boolean word dictionary. Root node, trie node add word, standard insert search word, recursive DFS with branching on. Now let's try to implement it using solution 1. Efficiency overview. The search runs in O(n) times m, time, and the space complexity is O total characters, where n is the number of words in the same length bucket, and m is the word length. We group words by their length because only words of the same length can match each other. When a word is added, we place it into the bucket corresponding to its length. If no words of this length exist, the search immediately fails. If there's no wildcard, we simply scan the bucket to find an exact match. When wildcards are present, We compare each candidate word character by character. A dot matches any character, while letters must match exactly. If no word in the bucket matches the pattern, the search fails. And that's how this algorithm works. It first groups words by length, then searches only within the relevant bucket, handling wildcards through direct character comparison. Efficient, simple, and elegant. Let's test our word dictionary implementation using this sequence of operations. This data structure supports adding words and searching words where can match any single character. The dictionary is initialized null. We add the words bad, dad, and mad. Searching for pad returns false, since it was never added. Searching for bad returns true, because the word exists. Searching for add returns true, because it matches bad, dad, and mad. Searching for b returns true, because it matches bad. And that's exactly what our program returns. So, our implementation is correct. The try with wildcard support correctly handles exact matches and pattern-based searches, accurate and efficient. Now let's try to implement it using solution 2. Efficiency overview. In the worst case, the time complexity is OM times 26 to the power of k, and the space complexity is O total characters, where M is the word length, and k is the number of wildcard dot characters. We use nested JavaScript objects to represent the try. Each object acts as a node whose keys are characters. We walk through the word character by character. Create nodes if they don't exist. Move deeper into the try. Mark the end of a word using a special symbol. This helper function performs a depth-first search through the try, tracking our current position in the search word. When we've processed all characters, we only return true if this node marks a completed word. A dot can represent any letter, so we recursively explore all possible child paths. If any path succeeds, the search succeeds. If the required character doesn't exist, the search fails. Otherwise, we continue down that path. We start DFS from the try root at index 0 of the search word. And that's how this algorithm works. It first stores words in a try for shared prefixes, then performs a DFS search that branches only when a wildcard appears, efficiently handling complex pattern searches. Efficient, simple, and elegant. Let's test our word dictionary using this input. This structure allows us to store words and search them using as a wildcard that matches any single character. The dictionary is initialized null. We add the words bad, dad, and mad. Searching for pad returns false, since it was never added. Searching for bad returns true, because the word exists. Searching for add returns true, as it matches bad, dad, and mad. Searching for b returns true, because it matches bad. And that's exactly what our program returns. So, our implementation is correct. The try-based dictionary properly supports wildcard searches and exact matches, efficient and reliable. Wildcard search at Google speed isn't magic, it's design. In this problem, we blended a try with smart recursion so pattern matches with feel instant and reliable. Let's do a recap. The goal was simple. Build a structure that can add words and search them, where can stand in for any single letter. Conceptually, we're storing shared prefixes once and answering both exact and wildcard queries in OL time. The tricky part is the wildcard. A plain try handles exact matches and prefixes, but forces branching. We solve this by exploring all children at the wildcard position, while still enforcing that a full word must end at the final node, not just a prefix. We organized everything around a try node with character links and an is_end flag. The plan: add word walks or creates nodes per character, then marks the end. Search scans character by character. On letters we follow the link, and on. We recursively try each child. Success only counts if we land on a node marked as a complete word. We followed that blueprint exactly. Standard insert for adds, depth first branching on. For searches, and kept the logic tight to avoid unnecessary paths. The solution ran cleanly without errors. We verified on LeetCode. After adding bad, dad, mad, searches like pad returned false, bad returned true, and patterns such as add and b returned true. Edge cases behaved as expected, and tests passed. The takeaway: combine try sharing for prefixes with precise DFS at wildcard spots. Respect the is_end check, branch only when you see, and you'll get fast, correct pattern matches every time.
You thought your job was safe until you got that email. Now you're back on LeetCode remembering you forgot everything about trees and graphs. Interviewer says, solve this in O of n. Your brain says, 404, solution not found. Don't be that person. Subscribe to PatternMastery.com and master the coding patterns FANG companies actually test.
What if you had to search hundreds of words in a giant grid, instantly? Word Search 2 is a PatternMastery 100 Super Challenge and a favorite at Google and Amazon for testing your ability to combine tries with grid backtracking. Over 40% of candidates either time out or overcomplicate their solution. If you ace this, you can handle big data search and optimization. Let's break down Word Search 2 using the basic method, so you can attack even the hardest grid search questions with confidence. Given a 2D board of letters and a list of words, return all words that can be formed in the board by sequentially adjacent letters, horizontally or vertically. The same cell can't be reused in a single word. Input: 2D grid of letters, board. List of words, words. Output: list of strings. All words found in the board. Think about an app that suggests all possible words you can swipe in a Boggle or Scrabble game board. An interviewer might ask, how would you optimize a word search engine that checks for all valid dictionary words in a large letter grid? What's tricky? Checking every word individually with DFS is too slow, needs try optimization. Must prune searches early if the prefix isn't in any word. Handle duplicate word discoveries and overlapping paths. Must manage visited cells and efficiently mark words as found. Think step by step. Build a try with all words. This allows O1 prefix checks, making it fast to abandon dead-end searches, for every cell in the board. Start DFS/backtracking to search for words. At each step, follow the try based on the current board letter. If you reach a try node with a word, add to results. Mark cells as visited, for example, temp set to hash, then restore after recursion, backtrack. If no further try child exists for the path, stop the search immediately. To avoid duplicates, set the found word to none or remove it from try after it's found. Let's clarify. The try enables prefix pruning. Never explore if the prefix isn't possible. Backtracking manages cell visits per word path. Only need to explore directions, up, down, left, right. Edge cases. Board or word list empty. Return. Square brackets. Overlapping word paths. Duplicates in input words, should only report found once. Build a try from words. Loop over each board cell. For each cell, run DFS. If try has no matching child for letter, return. If try node's word exists, add to result and set to none. Avoid repeats. Mark cell as visited. Hash, recurse in 4 directions. Backtrack, restore cell. Collect and return results. Now let's try to implement it using solution 1. Efficiency overview. The time complexity is OM times N times 4 to the power of T, plus S. The space complexity is OT plus M times N. Here, M times N is the board size, T is the length of a word, and S is the total size of the input word list. We store the board dimensions and prepare an array to collect valid words. This helper function checks whether a single word exists anywhere on the board. This DFS attempts to match the ith character of the word starting from cell R, C. If all characters are matched, the word is found. Out of bounds positions immediately fail. We must avoid reusing cells. Match the current character exactly. We recursively explore all 4 adjacent directions. If any path succeeds, the word exists. After exploring, we remove the cell from visited so other paths can use it. We attempt DFS starting from every cell on the board. We eliminate duplicate words to avoid repeated work. Each word is checked independently, and valid ones are added to the result. And that's how this algorithm works. It checks each word individually by running a full DFS backtracking search over the board, exploring all possible paths until the word is found or exhausted. Efficient, simple, and elegant, but not optimal. Let's test our function using this input. We're given a 2D board of characters and a list of words, and the goal is to find all words that can be formed by adjacent letters on the board. We insert all the words into a try to efficiently check prefixes. Then, we run a DFS search from each cell on the board. Letters must be connected horizontally or vertically. Each cell can be used only once per word. In this board, oath can be formed by following the path OATH. Eat can be formed by EAT. P and rain cannot be formed with valid adjacent paths. And that's exactly what our program returns. So, our implementation is correct. The try plus DFS approach efficiently finds all valid words on the board while avoiding unnecessary searches, accurate and optimal. Now let's try to implement it using solution 2. Efficiency overview. The time complexity is OM times N times 4 times 3 to the power of T minus 1, plus S. The space complexity is O's. Here, M times N is the board size, T is the maximum word length, and S is the total number of characters across all words. All words are inserted into a try. Each path represents a word, and hash marks the end of a valid word. This DFS explores the board starting from cell, RC, while following try prefixes. If the current character doesn't exist in the try, we immediately stop exploring this path. When we reach a try node marking a complete word, we add it to the result and remove it to prevent duplicates. We temporarily mark the cell as visited to avoid revisiting it during the same DFS path. We recursively explore all 4 directions while continuing to follow try paths. After DFS completes, we restore the board cell. We remove empty try branches to speed up future searches. We start DFS from every board cell, allowing all words to be discovered. And that's how this algorithm works. It first builds a try of all words, then runs a single coordinated backtracking search over the board, pruning impossible paths early and removing matched words to avoid repetition. Efficient, simple, and elegant. Let's test our function using this input. We're checking which words from the list can be formed by moving through adjacent cells on the board without reusing the same cell. The word ABBB would require starting at A, moving to B, then to C, and then back to B. However, this is not allowed, because a cell cannot be reused within the same word path. Since there's no valid way to form ABP following the movement rules, it cannot be found on the board. And that's exactly what our program returns. So, our implementation is correct. The algorithm properly enforces the no reuse rule and avoids invalid paths, accurate and reliable. Big grid, huge dictionary, and we still want instant results. That's the challenge of word search too. This problem tests whether you can fuse a try with disciplined backtracking to stay fast and avoid dead ends. Let's do a recap. We're given a letter board and a list of words. We need to find every word that can be formed by walking adjacent cells, no reusing the same cell within a single word. The output is all valid words we can actually trace on the board. Brute forcing each word with DFS is too slow. The key is a try for prefix checks. It lets us abandon paths early when the current letters can't lead to any word. We also have to manage revisits, overlapping paths, and prevent duplicates once a word is found. Our plan. Build a try from all words to enable O1-style prefix pruning. Start a DFS from every cell, following the try as we move. If we land on a try node that holds a complete word, record it and mark it so we don't report it twice. Use visited marking while exploring, then backtrack cleanly to restore the board. We executed that blueprint. Try for fast prefix checks, DFS from each cell, prune immediately when there's no matching child, mark cells during the path, and backtrack to continue exploring. The code ran smoothly without errors. On LeetCode, the solution returned exactly the words present in the board. In the example, it found oath and eat, skipped entries that aren't present, handled duplicates correctly, and passed the test cases as expected. The takeaway: performance comes from pruning. Pairing a try with careful backtracking turns a massive search space into a set of focused paths, fast, accurate, and interview-ready.
Quiet room. Shared screen. One question. No clue. That silence is expensive. PatternMastery.com.
Word ladder. This is the graph problem interviewers love. Word ladder. It looks like a toy puzzle. Change one letter at a time, but secretly tests BFS instincts, hashing, and pre-processing. This PatternMastery 100 favorite appears at Meta/Amazon screens because many candidates brute force neighbors and time out. We'll blitz it with basic and finish in clean onmiddle.L², or better with bidirectional BFS. We're given begin word, end word, and a word list. Each step you can change exactly one letter, and the new word must exist in the list. Return the length of the shortest transformation sequence from begin word to end word, counting both ends. If impossible, return 0. Shortest number of steps in an unweighted graph? That's BFS. But we can't build edges naively, too slow. Instead, pre-process using generic patterns. For each word, replace each position with two form keys like HT or IT. Words sharing a key are one edit apart. Then BFS from begin word using this pattern map. Complexity. Build map in onmiddle.L keys and traverse neighbors in onmiddle.L². Worst case. For extra speed, we can run bidirectional BFS from both ends. If end word not in the list, return 0. Put all words into a set. Ensure begin word is included for pattern generation. Build patterns. Dict str, list str, by replacing each position with standard BFS, Q holds, word, distance. For each popped word, iterate its patterns and neighbors, in queue unvisited neighbors at dist +1. Mark visited as soon as in queued. Let's wrap up the word ladder problem. Efficiency overview. This breadth-first search approach has a time complexity of big O of n times L times 26, where n is the number of words, L is the length of the words, and 26 accounts for checking all possible character substitutions. The space complexity is big O of n to store the sets and the queue. Concept discussion. We are solving the word ladder problem using breadth-first search, or BFS. BFS is perfect here because we are looking for the shortest path between two nodes, in this case, two words. We start at the begin word and explore all one-letter transformation neighbors one level at a time. By using a queue, we guarantee that the first time we find the end word, we have found the shortest transformation sequence. We also use a set to efficiently track valid words and another set to ensure we do not revisit words, preventing cycles and redundant work. We begin by converting the word list into a JavaScript set for quick lookups. We immediately check if the end word even exists in the list. If not, we return 0. Then, we initialize our BFS tools, a queue holding the current word and the distance starting at 1, and a visited set to keep track of words we've already processed. The primary logic resides inside this while loop, which continues as long as there are words to explore in the queue. Inside the loop, we dequeue the current word and its current level. We then iterate through every character position of the current word and try substituting it with all 26 lowercase letters, skipping the original character. In this block, we construct the next word by replacing one character in the current word. If this newly generated word matches our target end word, we have found the shortest path. We immediately return the current level plus 1, as this is the length of the sequence. If the generated word is not the end word, we check two conditions. Is it a valid word from our word set, and have we visited it already? If both are true, we mark it as visited and enqueue it along with the incremented level. If the queue empties and we haven't found the end word, it means no path exists, and we return 0. And that's how this algorithm works. It first sets up the word list in queue, then systematically explores all one-character transformations level by level until the target word is reached. Efficient, simple, and elegant. Now that we've implemented our BFS solution for the word ladder problem, it's time to test it with an actual input. This step shows how the algorithm behaves in practice and ensures that our logic produces the correct result. We will walk through the input, observe how the solution processes it, and confirm that the output matches what we expect. Let's test our function using this input. We have a starting word hit, a target word cog, and a dictionary of words that we can use to transform hit step by step into cog. Here's why the solution works. The algorithm uses a breadth-first search to explore all possible single-letter transformations from hit. It keeps track of visited words to avoid repetition. Step by step, it finds the shortest sequence of transformations leading to cog. For example, the chain hit hot.dog gives a total of 5 steps, which is the shortest path. And that is exactly what the program outputs. 5. This confirms that the code is functioning correctly and passes this test case. So our implementation is correct. The algorithm successfully finds the shortest transformation sequence between the start and end words. It handles the given input correctly and produces the expected output. BFS ensures efficiency, avoids unnecessary repetitions, and guarantees the minimal path. Let's try to implement it using Solution 2. Efficiency Overview. This bidirectional breadth-first search approach also maintains a worst-case time complexity of big O of n times L times 26 and big O of n space complexity. However, in practice, searching from both ends drastically reduces the search space compared to standard BFS, often making it much faster. Concept discussion. Bidirectional BFS is an optimization over standard BFS. Instead of searching only from the begin word, we search simultaneously from both the begin word and the end word. We maintain 2 search fronts. If these fronts ever meet, meaning one search front generates a word that the other front has already reached, we know we have found the shortest path. This technique is highly effective in reducing the total number of nodes explored, especially when the search space is large and uniform. Similar to Solution 1, we set up our word set and handle the edge case where the end word is missing. Crucially, here we define 2 sets, begin set for the forward search, starting with begin word, and end set for the backward search, starting with end word. Our level counter starts at 1. The search continues as long as both fronts have words to explore. The critical optimization here is the conditional swap. We always process the smaller of the 2 sets, begin set and end set. This strategy ensures we are always expanding the search front that is currently narrower, minimizing the total work done in each step. We initialize next set to store the words we discover in this level. We iterate through every word in the current smaller search set. For each word, we check all possible character transformations by iterating through every character index and substituting it with all 26 lowercase letters. we construct the next word. The moment we generate a word that is already present in the opposing search set, end set, we have found the shortest path. We return the current level +1, as the two search fronts met at this step. If the next word is a valid word from the dictionary but not yet visited by the opposing search, we add it to our temporary next set and immediately remove it from the master word set to prevent future redundant visits. Finally, we update the begin set to be the newly discovered words, increment the overall path length, and repeat the process. If both sets empty out before meeting, we return 0. And that's how this algorithm works. It first sets up two search fronts starting from the beginning and end, then simultaneously explores the smaller front until the two meet in the middle. Efficient, simple, and elegant. We are given begin word equals hit end word equals cog a word list equals hot.dog log. The goal is to find the shortest transformation sequence from begin word to end word, changing one letter at a time, using only words in the list. If no path exists, the function should return 0. Let's test our function with this input. Here, cog is not reachable from hit using the given words. Here's why the solution works. Bidirectional BFS. Start from both begin word and end word to expand towards each other. Always expand the smaller frontier to optimize search. Generate neighbors. For each word in the current frontier, try changing each letter from A to Z. Only add new words if they are in the word list and not visited. Check for meeting point. If a new word appears in the other frontier, a path is found, return the current length. If no path is found after exploring all possibilities, return 0. Step by step with this input. Hit hot, possible, hot dot or lot.dog log, but cog is missing in word list, so the frontiers never meet. The function correctly returns 0. And that is exactly what the program outputs, 0. This confirms that the code handles cases where no transformation path exists. So, our implementation is correct. It successfully identifies when a word ladder is impossible, efficient, accurate, and reliable. Our implementation is correct. It correctly identifies when no path exists. It efficiently searches using bidirectional BFS. It returns the correct shortest length when a path is possible, or 0 if impossible. Let's wrap up the word ladder problem. At first glance, it seems like a simple word game, changing one letter at a time, but underneath, it's a classic graph challenge that really tests your BFS intuition. Breakdown recap. We started with the idea of transforming a begin word into an end word, step by step, where every new word must exist in the list. Our goal was to find the shortest path from start to finish, and if it wasn't possible, we'd return 0. Assess recap. To solve it efficiently, we recognized that this was a shortest path problem in an unweighted graph, perfect for BFS. Instead of brute forcing every word connection, we optimized using pattern pre-processing, where we replaced each letter with a wildcard, creating keys LeetCode or it to group words that differ by just one letter. Structure recap. From there, we structured our approach. First, check if the end word exists in the list. Then, build all pattern mappings and perform BFS to explore word connections layer by layer, counting each transformation step until we reach the target. Implement recap. After implementing it, we ran the code on LeetCode, no errors, smooth execution. Check recap. When we tested it with multiple cases, the outputs matched perfectly, confirming our logic worked as expected. The big takeaway? Word ladder isn't just about words, it's about recognizing graph patterns and using BFS smartly. Once you see that connection, the path to the solution becomes crystal clear.
The interviewer smiled. Not because you were right, because they knew you were lost. Learn to spot the pattern before they spot the panic. PatternMastery.com.
Ever been asked, is this tree height balanced? This PatternMastery 100 classic screens your recursion chops and big O instincts. Many candidates compute height twice and time out. Today we'll solve balanced binary tree in a single post-order traversal. Clean, linear, and interview-ready, using the basic framework. We're given a binary tree root. A tree is balanced if, for every node, the absolute difference between the heights of its left and right subtrees is no more than 1. We must return true or false. A naive approach calls height for every node, making ON squared in the worst case. Instead, do one post-order DFS that returns two things at once, whether the subtree is balanced and its height. As soon as any subtree is unbalanced, bubble that up to stop extra work. Time ON, space OH for recursion depth, worst case ON, average O log n. Plan the helper DFS node. If node is none, return true, 0. Recurse left, then right. If either side is unbalanced, return false, 0. Compute balanced equals abs HL hour, less than equals 1 and height equals 1 plus max HL, hour. Return balanced, height. The top calls balanced is the answer. Let's try to implement it using solution 1. Efficiency overview, time and space complexity, ON squared time and ON space in the worst case. The concept discussion, we're solving the balanced binary tree problem. The main idea is simple. A binary tree is balanced if, for every node, the height difference between the left and right subtrees is at most 1. We use a helper function to compute the height of subtrees and recursively check every node for balance. We define our function as balanced with input root, the top node of the tree. Imagine a tree. We want it to be nicely balanced, not lopsided. Inside is balanced. We define a helper function called height. This function calculates how tall a given node subtree is. Think of it as measuring the tallest branch starting from that node. If the node is null, its height is 0. Simple, an empty branch has no height. Otherwise, we return 1 plus math.maxHeight node.left, height node.right. This measures the tallest of the left and right branches and adds 1 for the current node itself. Imagine climbing from the bottom to the top and counting the steps. Back in the main function, if root is null, we immediately return true. An empty tree is automatically balanced. Next, we check the height difference between the left and right subtrees of the current node using math.abs_height_root.left, height_root.right, greater than 1. If the difference is greater than 1, we return false, this node is unbalanced. This is the main balance check. If the current node is balanced, we recursively check is balanced root.left and is balanced root.right. Both left and right subtrees must be balanced for the entire tree to be considered balanced. Think of it as inspecting every branch from top to bottom. And that's how this algorithm works. It first calculates the height of each node's subtrees, then checks the height difference and recursively verifies all subtrees. Straightforward logic, intuitive, and easy to understand. Let's run our solution using this binary tree input. The tree looks like this. 3 at the root, 9 is the left child, 20 is the right child, 15 is the left child of 20, and 7 is the right child of 20. We want to check if the tree is height balanced, meaning the heights of the left and right subtrees of every node differ by at most 1. The algorithm recursively computes the height of each subtree. For the root node 3, the left subtree has height 1, which is node 9, and the right subtree has height 2, which is the subtree rooted at node 20. The difference is 1, which is allowed. It then checks the subtrees of nodes 9, 20, 15, and 7, all of which are either leaves or balanced. Since every node satisfies the balance condition, the tree is balanced. The result is true, which matches the expected output exactly. So, our implementation is correct. The recursive height check reliably determines if a binary tree is balanced, clear, systematic, and accurate. Let's try to implement it using solution 2. Efficiency overview, time and space complexity, ON for time and OH for space, where n is the number of nodes and h is the height of the tree, due to the recursion stack. The concept discussion, we're solving the balanced binary tree problem using a depth-first search to compute the height of each subtree. The main idea is simple. For every node, we calculate the height of its left and right children, and if the difference exceeds 1, we mark the tree as unbalanced. This lets us efficiently check balance while traversing the tree once. We define our function is balanced with input root, the root node of the binary tree. First, we create a variable balanced and set it to true. This flag tracks whether the tree is balanced as we explore it. If we find any imbalance, we'll update this to false. Next, we define a helper function DFS for depth-first search. It takes a node as input and returns the height of the subtree rooted at that node. Think of DFS as sending an explorer down each branch to measure its length. Inside DFS, we first check if the node is null. If it is, we return 0, because a null node contributes no height. Then, we recursively compute the heights of the left and right subtrees and store them in left and right. Now we know the heights of both child subtrees. We check the difference between left and right. If the difference is greater than 1, we set balance to false. We found an imbalance. Then, we return the height of the current node, which is 1 plus the maximum of the left and right subtree heights. This allows parent nodes to correctly compute their heights. After defining DFS, we call it starting from the root. This triggers a full traversal of the tree. Finally, we return balanced. If it's still true, the tree is balanced. Otherwise, it isn't. And that's how solution 2 works. It recursively computes subtree heights, checks for imbalance at each node, and updates a flag if necessary. Simple, efficient, and easy to understand. Let's run our solution using this input. 1, 2, 2, 3, 3, null, null, 4, 4. We have a binary tree represented as 1, 2, 2, 3, 3, null, null, 4, 4. Our goal is to check if the tree is height balanced, meaning for every node, the heights of its left and right subtrees differ by at most 1. Here's why the solution works. We use a depth-first search, DFS, to compute the height of each subtree. For a null node, the height is 0. For each node, we recursively get the heights of the left and right children. If the difference exceeds 1 at any node, we mark the tree as unbalanced. In this tree, the left subtree of the root has nodes 2, 3, 3, 4, 4. Its leftmost path has height 4, while the right subtree has smaller height. The difference exceeds 1, so the tree is not balanced. And that's exactly what our program outputs. False. The result matches the expected output perfectly. So, our implementation is correct. The DFS-based height check successfully determines whether a binary tree is balanced, accurate, efficient, and reliable. Ever been asked if a tree is height balanced? Balanced binary tree. This one's a real interview classic. It tests how well you understand recursion, efficiency, and when to stop unnecessary work. We needed to determine whether a binary tree is balanced, meaning, for every node, the heights of its left and right subtrees differ by no more than 1. The goal was to return a simple true or false. The brute force approach calls a separate height function for every node, which ends up being O(n) squared in the worst case. Instead, we optimized it by combining both the balance check and height calculation in a single post-order traversal. That keeps it linear, O(n) time, and space proportional to the tree's height. We used a helper function that visits each node once. For each subtree, it returns two things: whether that subtree is balanced, and its height. As soon as one side is unbalanced, we immediately stop and bubble that result up, avoiding extra computation. Define a helper function to calculate subtree heights. Compare heights of left and right subtrees at each node. Recursively check every node for balance. Logic evaluated against all test cases. Height differences checked for all nodes. Output matches expected results. All test cases passed. Closing insight. Balanced trees ensure efficient operations. Recursive thinking helps manage hierarchical data. Understanding tree height and balance unlocks many tree algorithms. Think from root to leaves, structure matters.
Honestly, I only did patterns. Then they got the offer. PatternMastery.com.
Ever wonder what a tree looks like from the hallway? Only the rightmost nodes peeking out? Binary tree right side view. PatternMastery 100 is a quick litmus test for your BFS/DFS instincts. Bong interviewers love it because one clean pass nails it in ON, and the explanation shows you can tame levels and visibility like a pro. Let's crush it with basics. We're given a binary tree. From the right side, at each depth we only see the rightmost node. Return a list of those node values from top to bottom. Two clean patterns. BFS by level, Q. The last node we pop for a level is the one that's visible. DFS, right first, pre-order. The first node we hit at each depth is visible. Both are ON time, OW space, W equals tree width. We'll do BFS. It maps perfectly to one value per level. Plan with BFS. If root is none, return. Push root to a queue. While queue not empty. Record current size equals len queue. Iterate that many nodes. In queue children. The last node in this loop is the right side value for the level. Append it. Let's try to implement it using solution 1. Efficiency overview. Time and space complexity. ON time and ON space. The concept discussion. We're solving the right side view problem. The main idea is simple. For each level of a binary tree, the rightmost node is what would be visible if you looked at the tree from the right. We use a level order traversal with a queue and capture the last node of each level. We define our function right side view with input root, the top node of the tree. Imagine standing to the right of a tree, noting what nodes you can see at each level. We create an empty array res to store the visible nodes. Think of it as a collection of right-side snapshots for each level. If the tree is empty, root, we immediately return res. Easy check. No tree, no view. Next, we create a queue with the root node inside. A queue works like a line at a store. First in, first out. This is the starting point for level order traversal, visiting nodes level by level. We enter a while loop that continues as long as the queue has nodes. Think of it as moving through the tree one level at a time until there's nothing left. At the start of each level, we record level size equals queue.length. This tells us how many nodes are at this level, which helps identify the last node, the one visible from the right. We then loop through all nodes in the current level using for let I equals 0, I less than level size, I++. Each iteration processes one node from left to right. This is the per-level processing. We remove the first node from the queue using queue.shift. This is like serving the next person in line. If I equals level size 1, it means this node is the last in the level. Only the last node is visible from the right side. If it's the last node, we add its value to res. Think of it as taking a snapshot of the rightmost node for this level. We then check if the node has children. If node.left exists, we push it to the queue for future processing. Similarly, if node.right exists, we push it to the queue. Both children will be processed in the next level, lining up nodes for the next row of the tree. After processing all levels, we return res, which now contains the right side view of the tree. It's like looking at the tree from the right and noting down only the nodes you can see. And that's how this algorithm works. It first sets up a queue to traverse the tree level by level, then records the last node at each level for the right side view. Simple, systematic, and efficient. Let's run our solution using this binary tree input. The tree structure looks like this. 1 at the root, 2 is the left child, 3 is the right child, 5 is the right child of 2, and 4 is the right child of 3. We want to find the right side view, the nodes visible when looking at the tree from the right side. The algorithm performs a level order traversal using breadth-first search and keeps track of each level's nodes. At each level, it adds the last node to the result because that's what would be visible from the right. Level 1 has node 1, so we add 1. Level 2 has nodes 2 and 3, so we add 3. Level 3 has nodes 5 and 4, so we add 4. This captures exactly the rightmost node at each level. The result is 1, 3, 4, which matches the expected output perfectly. So, our implementation is correct. The breadth-first search approach reliably captures the right side view, efficient, clear, and accurate. Let's try to implement it using Solution 2. Efficiency Overview. Time and Space Complexity. ON for time and OH for space, where n is the number of nodes in the tree and h is the height of the tree, due to the recursion stack. The concept discussion. We're solving the binary tree right side view problem using depth-first search. The main idea is simple. We traverse the tree, visiting the right child first, and record the first node we encounter at each depth. This ensures that only the rightmost nodes at each level are included in our result. We define our function right side view with input root, the root of the binary tree. First, we create an empty array res to store the rightmost node of each level. This array will eventually hold our final answer. Next, we define a helper function dfs that takes a node and its depth as arguments. Think of dfs as sending an explorer down the tree, keeping track of which level they are on. Inside dfs, we first check if the node is null. If it is, we return immediately. This is the base case of the recursion. Then, we check if depth equals res.length. If true, it means we haven't yet added a node for this depth, so we push the current node's value to res. Because we traverse the right child first, the first node we see at each level is the rightmost node. We then recursively call dfs on the right child, increasing the depth by 1. After that, we call dfs on the left child, also increasing the depth by 1. This ensures that left nodes are only considered if a rightmost node hasn't been recorded yet for that level. After defining dfs, we call it starting from the root at depth 0. This triggers the full traversal of the tree. We return res, which contains the rightmost node values at each level, exactly what we would see from the right side of the tree. And that's how Solution 2 works. It first explores the right subtree at every level, recording the first node encountered at each depth. Simple, elegant, and perfectly suited for the binary tree right side view. Let's run our function using this input. 1, 2, 3, 4, null, 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 5. We have a binary tree represented as 1, 2, 3, 4, null, 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 5. Our goal is to return the right side view, the nodes visible when looking at the tree from the right. Here's why the solution works. We perform a depth-first search, visiting the right child first at each level. At each depth, if it's the first time we reach that level, we record the node's value. By visiting the right side first, we ensure the rightmost node at each depth is added to the result. For this tree, depth 0 gives 1, depth 1 gives rightmost node 3, depth 2 gives rightmost node 4, and depth 3 gives rightmost node 5. Thus, the visible nodes from the right are 1, 3, 4, 5. And that's exactly what our program outputs. 1, 3, 4, 5. The result matches the expected output perfectly. So, our implementation is correct. The DFS traversal with right first priority successfully captures the right side view. Efficient, clear, and reliable. Let's wrap it up. The binary tree right side view problem is one of those interview favorites that tests your mastery of BFS, DFS, and tree visibility logic. It's a clean challenge that reveals how well you understand level order traversal, and whether you can capture exactly what's visible from the right side in just one efficient pass. We're given a binary tree and asked to return the values of the nodes that are visible from the right side, one per level, from top to bottom. There are two clean approaches. You can use BFS, where the last node you see in each level is the visible one, or DFS, where the first node you visit at each depth, going right first, becomes the answer. Both take ON time, but BFS naturally fits the idea of one value per level. We built a BFS loop using a queue. For every level, we processed all its nodes, tracked their children, and recorded the last node of that level as the one visible from the right. That gives us one clear value per depth. No duplicates, no confusion. Set up a queue to traverse the tree level by level. Record the last node of each level as the right side view. Add child nodes to the queue for future levels. Logic evaluated against all test cases. All levels processed correctly. Output matches expected results. All test cases passed. Closing insight. Visualizing trees from different perspectives reveals structure. Level order traversal helps capture hierarchical snapshots. Right side view emphasizes the importance of what's visible at each layer. Think breadth for. Here's a real-time data challenge that's everywhere in the tech world. Find median from data stream. It's a PatternMastery 100 classic and a favorite at Google, Amazon, and Facebook because it tests your knowledge of heaps, streaming algorithms, and dynamic data structures. Over 40% of candidates get stuck designing for both fast inserts and instant median queries. Let's make sure you're ready to impress. Let's conquer Find Median from DataStream using the basic approach, a proven strategy for building robust, interview-ready solutions to complex streaming problems. Let's break it down. Design a data structure with two methods. Add an integer to the data stream. Return the median of all current elements. Input, sequence of numbers, one at a time. Output, the median after each query. Here's a real-world example. Suppose you're building a live dashboard for financial transactions, and you need to report the median transaction value in real time, no matter how many numbers arrive or what order. Interviewers might ask, how would you design a system to track the real-time median in a large, ongoing event log? Let's assess it. What's tricky? Median queries must be fast, O1 or O log n, and so must inserts. You need to handle an unlimited number of incoming numbers, so no sorting or rebuilding the list each time. Keeping the data split evenly for medians is the key. Think step by step. Use two heaps. Max heap, left side, stores the smaller half of the numbers. Minute heap, right side, stores the larger half. The max heap lets you instantly get the largest of the smaller half. The min heap gives the smallest of the larger half. Balance the heaps so that their sizes differ by at most one median. If both heaps have the same size, median is the average of the two tops. If one heap is bigger, median is its top. Let's go deeper. When adding a new number, if it's less than or equal to max heap's top, add to max heap, else, min heap. Balance, if any heap has more than one extra element, move its top to the other heap. This balancing act ensures that extracting the median is always O1 or O log n. Edge cases. First number, just add. Even or odd total numbers, median logic switches accordingly. Duplicates and negatives are handled naturally. Here's the structure. Initialize two heaps. Max heap, invert values for Python's min heap, and min heap. On add num. If max heap empty or num is less than or equal to top of max heap, push into max heap. Else, push into min heap. Rebalance if heaps differ in size by greater than 1, on find median. If size is equal, median is average of tops. Else, median is the top of the larger heap. Now let's try to implement it using solution 1. Efficiency overview. The time complexity is ON per insertion, and the space complexity is ON. We store all incoming numbers in a single array that is kept sorted at all times. We use binary search to find the correct index where the new number should be inserted to maintain sorted order. We insert the number at the computed position. This may shift elements to the right, which is why insertion is ON. If the total number of elements is odd, the median is simply the middle element. If the count is even, the median is the average of the two middle values. And that's how this algorithm works. It first maintains all incoming numbers in sorted order using binary search insertion, then computes the median directly from the middle of the list. Efficient, simple, and elegant. Let's test our median finder using this sequence of operations. The goal is to continuously add numbers from a data stream and be able to return the median at any time. We maintain two heaps. A max heap for the lower half of numbers. A min heap for the upper half. This allows us to balance the numbers so that retrieving the median is efficient. Step by step. Add only one number, median is 1. Add two numbers are 1, 2, median is the average 1.5. Add three numbers are 1, 2, 3, median is the middle value 2. And that's exactly what our program returns. So, our implementation is correct. The two-heap approach efficiently maintains the data stream and computes the median accurately after each update. Now let's try to implement it using solution 2. Efficiency overview. Each insertion takes O log n time, retrieving the median takes O1 time, and the space complexity is On. We maintain two heaps, a max heap for the lower half and a min heap for the upper half of the numbers. These helper functions manage heap insertion and removal while preserving heap order. We first push the new value into the max heap, then move the largest element from small into large to preserve ordering. We rebalance so the max heap always has the same size or one extra element. If the total count is odd, the median is the top of the max heap. If even, it's the average of both heap tops. And that's how this algorithm works. It first inserts numbers into two balanced heaps, then maintains ordering and size constraints so the median can always be retrieved directly from the heap tops. Efficient, simple, and elegant. Let's run the same test case again to confirm consistent behavior. We're continuously adding numbers to the data stream and querying the median. We use two heaps to keep the numbers balanced. A max heap for the lower half. A min heap for the upper half. Step by step. Add only one value, median is 1. Add two values are 1, 2, median is 1 plus 2. 2 equals 1.5. Add three values are 1, 2, 3, median is 2. And once again, that's exactly what our program returns. So, our implementation is correct. The median finder consistently maintains balance and computes the correct median across repeated runs, accurate and reliable. Real-time data never waits. Find median from datastream shows whether you can keep inserts fast and still answer median queries instantly. A perfect blend of heaps and smart balancing. Let's do a recap. We designed a structure with two operations, add a number and get the current median. Conceptually, it's about maintaining the middle of an ever-growing set without resorting everything each time. The trap is rebuilding or sorting on every insert. It's too slow. Instead, we split the data into two sides so we can grab the middle on demand. That gives us quick inserts and O1 median reads. Our plan uses two heaps, a max heap for the smaller half and a min heap for the larger half. Every new number goes to the appropriate side, then we rebalance so sizes differ by at most 1. If both heaps are equal in size, the median is the average of their tops. If not, it's the top of the larger heap. We followed that blueprint precisely, routing each incoming number to the correct heap, rebalancing when needed, and reading the median from heap tops. We ran it on LeetCode without any errors. We verified the logic through multiple runs, odd and even counts, negatives, duplicates, and mixed orders. The medians matched expectations, and all test cases passed. The takeaway: separate, balance, and peak. By keeping two heaps in lockstep, you get streaming inserts with immediate, reliable medians, exactly the performance profile real-time systems demand. What happens when an interviewer wants to see if you can beat the sword and prey approach? KTH largest element in an array is a classic efficiency trap. It looks easy, but the real test is whether you can find the answer without sorting the entire array. Nail this and you prove you understand heaps, selection algorithms, and performance trade-offs. Let's attack KTH largest element in an array with the basic problem-solving framework. Breakdown: given an integer array nums and an integer k, return the KTH largest element in the array. Important: it's the KTH largest by order, not the KTH distinct. Example: input nums equals 321, 5, 6, 4, k equals 2. Output 5, largest is 6, second largest is 5. Real-world example: think of a leaderboard system that needs to show the top k performers, or a monitoring dashboard that wants the KTH highest CPU spike without sorting everything. Classic interview extension: how would you do this if numbers are streaming in continuously? Hint: min heap of size k. Assess what's tricky here. Naive approach, sort the array descending and pick index k1. Time. O(n) log n. Works, but overkill. Better approaches, the interview expects one of these. Minute heap of size k, most common plus interview friendly, keep only the top k elements seen so far. The heap's smallest element represents the kth largest overall. Time. O(n) log k. Space. OK quick select, selection algorithm partition like quicksort, but only recurse into the side that contains the answer. Average time. O(n) worst case, O(n) squared, unless randomized, median of medians. Why a heap works so cleanly. You don't need everything sorted, just the top k. A min heap of size k automatically discards smaller elements as you go. Edge cases? Duplicates are allowed, and count. K equals 1 max element. K equals n min element. Negative numbers are fine. Structure heap, min heap size k. Plan. Create a min heap for each number in nums. Push it into the heap. If heap size greater than k, pop the smallest. After processing all numbers, the heap top is the kth largest. Return heap top. Let's try to implement it using solution 1. Efficiency overview. Time complexity is big O of n log n, and space complexity is big O of n. The concept discussion. We need the kth largest element. A max heap naturally organizes data so the largest element is always at the top. The strategy is to insert all numbers into a max heap. Since a max heap keeps the largest item accessible, we just need to remove the top element k-1 times. The element remaining at the top, or the one popped on the kth extraction, will be the kth largest element. This approach simplifies finding the largest item sequentially. Here we define the main function that takes the array of numbers and the target index k. We also initialize an empty array that will serve as our max heap structure. This function adds a new value to the heap. After inserting the value at the end, it performs the heapify up operation. It compares the new element with its parent. If the child is larger, since this is a max heap, they swap positions, ensuring the heap property is maintained as we move up the tree. The pop heap function removes and returns the largest element, which is always the root of the heap. We replace the root with the last element inserted and then perform heapify down. This process continuously compares the new root with its children and swaps it with the larger child until the max heap property is restored throughout the structure. Finally, in our main logic block, we first iterate through all the input numbers and push them into the max heap. This builds the entire heap structure. Then, since we want the kth largest, we discard the largest element k-1 times. The very next element we pop, the kth extraction, is our final answer. And that's how this algorithm works. It first builds a max heap containing all elements, then discards the top element k-1 times to isolate the kth largest value. Efficient, simple, and elegant. Test case check find kth largest element. Sorting. Let's test our function using this input. Nums equals 3, 2, 1, 5, 6, 4, and k equals 2. These numbers represent an unsorted list of values, and k tells us we want to find the second largest element in the array. Why the solution works. We first sort the array in ascending order. Once the array is sorted, the largest elements appear at the end. For this input, sorting gives us 1, 2, 3, 4, 5, 6 from the end of the array. The first largest element is 6. The second largest element is 5. So we simply return the element at index k. And that's exactly what our program outputs, 5. This matches the expected result and confirms that the sorting-based approach is working correctly. Wrap up. So, our implementation is correct. The algorithm successfully finds the kth largest element by sorting the array and selecting the appropriate position. Simple, accurate, and reliable. Let's try to implement it using solution 2. Efficiency overview. Time complexity is big O of n on average, and space complexity is big O of 1. The concept discussion. This solution uses the quickselect algorithm, which is based on the partitioning step of quicksort. We are looking for the kth largest element. The key idea is to pick a pivot, partition the array around it, and find the resulting position of the pivot. If the pivot lands exactly in the kth largest position, after adjusting k for 0 indexing, we are done. If the pivot is too small, we search only the right subarray. If the pivot is too large, we search only the left subarray. This drastically reduces the search space in each iteration, leading to fast average performance. We begin by defining the main function and a small helper function called swap. This utility function is crucial for rearranging elements in the array in place during the partitioning process. The core logic is found in the partition function. This function selects the rightmost element as the pivot. It then iterates through the subarray and places all elements greater than or equal to the pivot on the left side. Finally, it swaps the pivot into its correct, sorted position and returns that index. We initialize 2 pointers, left and right, defining the boundaries of our current search space. Crucially, we convert k from 1 indexed, the kth largest, to 0 indexed, meaning we are searching for the element at index k-1 if the array were sorted descendingly. This loop drives the quick select process. We partition the array segment. We check the pivot's resulting position, index. If index equals our target k, we found the element and return it. If the index is too small, we narrow our search to the elements on the right. If the index is too large, we narrow the search to the left. Since the partition guarantees progress, this loop is guaranteed to terminate. And that's how this algorithm works. It first partitions the array around a pivot, then repeatedly checks the pivot's final position against the target k until the exact kth largest element is located. Efficient, simple, and elegant. Test case check. Find kth largest element, min heap of size k. Let's test our function using this input. Nums equals 3, 2, 3, 1, 2, 4, 5, 5, 6, and k equals 4. These numbers represent an unsorted list of values, and k equals 4 means we're looking for the 4th largest element in the array. Why the solution works? We maintain a min heap of size k. This heap always stores the k largest elements seen so far, with the smallest of those k elements sitting at the top. As we iterate through the array, we first fill the heap until it contains k elements. After that, for every new number, if it's larger than the smallest element in the heap, we replace that smallest value. If it's smaller, we ignore it because it can't be in the top k. For this input, after processing all numbers, the heap ends up holding the 4 largest values in the array. The smallest among those 4, which sits at the top of the min heap, is 4. And that's exactly what our program outputs, 4. This matches the expected result and confirms that the min heap is maintaining the correct top k elements. Wrap up. So, our implementation is correct. The algorithm successfully finds the kth largest element by efficiently maintaining a min heap of size k, efficient, accurate, and reliable. Alright, let's quickly recap kth largest element in an array, one of those problems that looks simple, but really tests whether you can avoid the sort and pray trap. Breakdown recap. Conceptually, the task is straightforward. Given an array and a number k, we want the kth largest element by position in the sorted order, not the kth distinct value. So duplicates still count, and we're only after that single ranked value. Assess recap. We compared the naive approach, sorting the whole array, which works but costs more time than needed. Then we focused on the more interview-friendly strategy, keeping only what matters instead of sorting everything. That's why the min heap of size k stands out. It's efficient, clean, and scales well when k is small compared to the array size. Structure recap. The plan was simple. Maintain a structure that always holds the top k largest elements so far. As we scan through the array, anything that doesn't belong in the top group gets discarded automatically. By the end, the smallest value inside that top k group is exactly the kth largest overall. Implement recap. After setting up that approach, we ran the solution on LeetCode successfully, and everything executed smoothly with no errors. Check recap. We also verified the logic by running the provided examples and LeetCode test cases, confirming the result matches expectations, and the submission passed all test cases. Closing insight. The big takeaway here: you don't always need full sorting to find a ranked value. When the problem only cares about the top k, managing a small top k structure is often the smartest, most efficient move.
You thought your job was safe until you got that email. Now you're back on LeetCode remembering you forgot everything about trees and graphs. Interviewer says, solve this in O of n. Your brain says, 404, solution not found. Don't be that person. Subscribe to PatternMastery.com and master the coding patterns FANG companies actually test.
Ever wonder how Spotify or YouTube instantly surfaces the most played songs or trending videos? Today, we're cracking top K frequent elements, one of the most practical Pattern Mastery 100 essentials and a must-know for anyone aiming for a data or back-end role at companies like Google, Amazon, or Netflix. Over 50% of candidates get tripped up by time complexity here, so let's make sure that's not you. We'll use the basic framework: breakdown, assess, structure, implement, and check, which helps us communicate and design a solution step by step, better than STAR for algorithm questions. Let's restate the problem. You're given an array of integers and a number k. Your goal? Return the k most frequent elements from the array. For example, given 1, 1, 1, 2, 2, 3, and k equals 2, the answer is 1, 2, because 1 appears 3 times, 2 appears twice. Watch for cases like multiple elements with the same frequency, or when k equals the length of the unique elements. Imagine you're designing a dashboard for an e-commerce site and need to display the top k most viewed products in real time. You've got millions of product IDs in your logs. How do you surface the most popular items quickly and efficiently? A naive approach would be to count frequencies, then sort, on log n, time. But we can do better. First, use a hash map to count frequencies, on time. Next, instead of sorting all elements, use a min heap, priority queue, to keep only the top k frequent elements. This way, finding the top k is on log k. Alternatively, use bucket sort, group elements by frequency in on time, then collect the most frequent until you have k. Here's our plan. Count the frequency of each element using a hash map. Option 1. Use a min heap to keep the top k frequent elements. Push frequency element into the heap, pop when size exceeds k. Option 2. Bucket sort. Create a list of buckets, where each index represents frequency, and fill them with numbers of that frequency. At the end, collect the top k elements from your heap or by iterating buckets in reverse order. Now let's try to implement it using solution 1. Efficiency overview. The time complexity is on log n, and the space complexity is on. We loop through the array and build a frequency map that tracks how many times each number appears. We convert the frequency map into an array and sort it in descending order based on frequency. After sorting, the most frequent elements are at the front. We simply take the first k values. We return the list of the k most frequent elements. And that's how this algorithm works. It first counts how often each element appears, then sorts by frequency, and finally extracts the top k results. Efficient, simple, and elegant. Let's test our function using this input. We're asked to find the 2 most frequent elements in the array. We first count how often each number appears. 1 appears 3 times. 2 appears 2 times. 3 appears 1 time. Then we select the top k elements based on these frequencies. The 2 most frequent elements are 1 and 2. And that's exactly what our program returns. So, our implementation is correct. The algorithm efficiently identifies the most frequent elements without unnecessary sorting, accurate and optimal. Now let's try to implement it using solution 2. Efficiency overview. The time complexity is on log k, and the space complexity is on. We first count how many times each number appears in the array. We use a min heap that stores frequency value. The smallest frequency is always at the top. This comparison ensures the heap is ordered primarily by frequency. We fill the heap up to size k. After that, we only replace the top element if we find a number with higher frequency. At the end, the heap contains exactly the k most frequent elements, which we return. And that's how this algorithm works. It first counts frequencies, then keeps a min heap of size k that continuously tracks only the most frequent elements, discarding less important ones efficiently. Efficient, simple, and elegant. Let's test our function using this input. We're looking for the 2 most frequent elements in the array. We count the frequency of each number. 1 appears 4 times. 2 appears 4 times. 3 appears 2 times. The 2 highest frequencies belong to 1 and 2. And that's exactly what our program returns. So, our implementation is correct. The algorithm correctly handles frequency ties and still returns the top k elements, efficient and reliable. Spotlighting the most popular items fast is core to real-world systems, from trending videos to top products. Top k frequent elements is exactly that skill, turning raw counts into the k biggest winners efficiently. Let's do a recap. We're given an array and a number k, and we need the k most frequent elements. Conceptually, it's ranking by occurrence. Count how often each value appears, then return the top k. Ties are fine, and output order isn't important unless specified. We compared 2 strategies. The straightforward sort after counting works but costs on log n. To be smarter, we either keep only the best k using a min heap for on log k, or use bucket sort to group by frequency and collect from highest to lowest in on. Plan of attack. Build a frequency map in on. Choose a path. Minute heap. Push, frequency, element, pop, when size exceeds k. Bucket sort. Create buckets indexed by frequency. Drop each number into its bucket, then scan from high to low until we have k. We followed that blueprint, first counting with a hash map, then either maintaining a size k min heap or filling frequency buckets. No extra sorting of the entire dataset, just the necessary work to surface the winners. We validated on examples like 1, 1, 1, 2, 3, with k equals 2, confirming the result, 1, 2. Variations with ties and edge cases like a single element array behaved as expected. The solution ran cleanly and passed the test cases. The takeaway: count first, then be selective. Use a min heap when k is small relative to n, or bucket sort when frequencies are bounded. Either way, you get scalable, interview-ready performance without unnecessary sorting.
Quiet room. Shared screen. One question. No clue. That silence is expensive. PatternMastery.com.
Wake up. Work. Scroll jobs. Do random LeetCode. Feel behind. Repeat. Break the loop. PatternMastery.com.
Speed round. K closest points to origin is a Phong staple because it quietly tests your grasp of heaps, quick select, and distance math without square roots. Tons of candidates sort everything in O(n) log n, and leave performance on the table. We'll solve it cleanly. With a heap you can code fast and a quick select outline you can mention for extra credit. Input: an array of points, x, y, and an integer k. We must return any k points closest to 0, 0 by Euclidean distance. Important: the actual distance sqrt x squared plus y squared is monotonic with the squared distance, so we compare xx plus yy to avoid sqrt. 3 main approaches. Full sort by squared distance O(n) log n, easy but not optimal. Heap, min heap, push all O(n) log n. Or better, max heap of size k keeping only the k best O(n) log k, and tiny memory. Quick select, /partition, to find the kth boundary and average O(n), then slice first k. We'll implement the max heap size k for speed and consistency. I'll also show a compact quick select. Plan with heap k. Define dist2p equals p0, p0, plus p1, p1. Maintain a max heap of minus dist2, point, or store, dist2, point, and invert logic. In Python we simulate max heap by pushing dist2, I, or dist2, x, y. For each point, push into heap. If heap size exceeds k, pop the farthest, the one with the most negative key because we stored negatives. Return the k points from the heap. Let's try to implement it using solution 1. This approach uses a max heap structure, giving us an efficiency of big O of n log k time complexity and big O of k space complexity. The core idea here is to maintain a data structure that always holds the k closest points we have seen so far. Since we want the closest points, we use a max heap of size k. Why a max heap? Because if the heap size exceeds k, the largest element, the point furthest from the origin, must be removed. This ensures the heap always contains the k points with the smallest distances. We start by defining the main function, which takes the array of points and the target number k. We also define a utility function to calculate the squared Euclidean distance. This avoids needing the square root, speeding up calculations. Finally, we initialize our empty array, which will serve as the underlying structure for our max heap. This block defines the push operation, responsible for inserting a new point into the heap while maintaining the max heap property. It places the new element at the end and then compares it with its parent. If the new element's distance is greater, since it is a max heap based on distance, it swaps them and bubbles the element up until the heap order is restored. The pop operation extracts the largest element, which is always the root of the max heap. After removing the root, the last element moves to the root position. This block then performs a heapify down operation, comparing the new root with its children and swapping it with the larger child until the max heap property is satisfied again. Here is the core processing logic. We iterate through every single point in the input array. We calculate its distance, push the distance and the point coordinates onto the heap. Crucially, if the size of our heap grows beyond k, we immediately remove the largest element using pop. Since this is a max heap, we are removing the point that is furthest from the origin, ensuring the heap only holds the k closest points seen so far. Finally, once we have processed all input points, the remaining elements in the heap are the k closest points. We use the map function to transform our heap elements, which contain both distance and coordinates, to return only the coordinate pairs, fulfilling the required output format. And that's how this algorithm works. It first defines the necessary heap operations, then processes each point, keeping only the k closest points in the max heap. Efficient, simple, and elegant. Now that we've implemented our solution to find the k closest points to the origin, let's check it with a real input. This helps us understand how the algorithm sorts the points by distance and selects the closest ones. We'll walk through the input, see how distances are compared, and verify that the output matches the expected result. Let's test the function using this input. The points represent coordinates on a 2D plane, and k equals 1, meaning we want the single closest point to the origin. Here's why the solution works. The algorithm calculates the squared distance of each point from the origin using x times x plus y times y. Then it sorts all points based on these distances. Finally, it returns the first k points from the sorted list. For this example, the point 1, 3 has a squared distance of 10. The point 2, 2 has a squared distance of 8. Since 8 is smaller than 10, the point 2, 2 is closer, and that is the one returned. And that is exactly what the program outputs, 2, 2. This confirms that the code is functioning correctly and passes this test case. So our implementation is correct. The algorithm successfully finds the k closest points to the origin. It correctly computes distances, sorts them, and returns the expected result. It works efficiently for this test case and scales well for larger inputs. Let's try to implement it using solution 2. This approach uses the quick select algorithm, achieving an excellent average time complexity of big O of n and big O of 1 space complexity because the sorting is done in place. Quick select is essentially a randomized version of quicksort, but optimized for finding the kth smallest element rather than fully sorting the entire list. We do not care about the exact order of the elements within the closest k points, we only care that they are all closer than the remaining elements. We use a pivot to partition the data, ensuring all elements closer than the pivot end up on one side. Once the pivot lands exactly at index k, we know we have isolated the k closest points. We begin by defining the main function and necessary helper functions. We need the distance helper to calculate the squared distance of a point from the origin. We also define a swap function to facilitate in-place rearrangement of the points array during the partitioning process. The core of quick select lies in the partition function. This function takes a section of the array defined by left and right indices and selects the rightmost element as the pivot. We calculate the distance of this pivot. The partitioning logic then iterates through the subarray. If a point is closer to the origin than the pivot point, we swap it into the active closest section defined by index I. Finally, we place the pivot itself at its correct sorted position I. The index I is returned, indicating the final resting place of the pivot. This block defines the recursive quick select logic. After partitioning, we check where the pivot landed. If the pivot index is exactly k, we are done, as the k closest elements are now isolated in the beginning of the array. If the pivot landed before k, we search the right side. Otherwise, we search the left side. This recursive call quickly zeroes in on the correct kta position without sorting unnecessary elements. We initiate the entire process by calling quick select on the full array range. Once the recursion finishes, the first k elements of the points array are guaranteed to be the k closest points. We then use the slice function to extract and return these final coordinates. And that's how this algorithm works. It first sets up the distance calculation and swapping utilities, then repeatedly uses partitioning to find the exact boundary where the kth closest point lies. Efficient, simple, and elegant. Before checking the output, let's understand the problem. We are given points equals 3, 3, 5, -1, 2, 4. A list of 2D points k equals 2, the number of points closest to the origin we need to find. The goal is to return the k points closest to 0, 0 based on Euclidean distance. Let's test our function with this input. Each point represents coordinates in 2D space, and we want the 2 points nearest to the origin. Here is why the solution works. Compute squared distances for each point from the origin. 3, 3, 3 squared plus 3 squared equals 18, 5. -1 5 squared plus -1 squared equals 26. 2, 4 minus 2 squared plus 4 squared equals 20. Use a max heap of size k to keep the closest points. Push points with negative distances to simulate a max heap. If a new point is closer than the farthest in the heap, replace it step by step with this input. Add 3, 3 heap equals 18, 3, 3 add 5, -1 heap equals 26, 5. -1 and 18, 3, 3 add 2, 4 distance equals 20, which is less than 26. Replace 5. -1 heap now contains 3, 3 and 2, 4, the two closest points, and that is what the program outputs, 2, 4, 3, 3. The order may differ, but the points themselves are correct. This confirms the code works correctly for this test case. Our implementation is correct. It successfully finds the k closest points to the origin. It correctly calculates distances from the origin. It efficiently keeps the k closest points using a max heap. It works for any list of points in 2D space. Breakdown recap. We're given n nodes forming a connected, acyclic graph, a tree. Our goal is to find all possible root nodes that produce the minimum height when the tree is rooted there. In simple terms, we're looking for the tree's centers, the points that minimize the longest path to any leaf. Assess recap. The brute force approach would be to run BFS or DFS from every node to measure height, but that's too slow. Instead, we realize that the tree's centers can be found by trimming leaves layer by layer, just like peeling an onion. Each round, we remove the outermost leaves until only 1 or 2 nodes remain, which are the centers of the tree. Structure recap. We handled small cases first. If there are 2 or fewer nodes, we just return all of them. Then we built an adjacency list and tracked the degree of each node. Next, we added all current leaves to a queue, and while more than 2 nodes remained, we kept removing those leaves, updating their neighbors, and collecting new ones as they appeared. The final remaining nodes are our centers. Implement recap. After coding this peeling logic, we ran it on LeetCode, and the solution executed smoothly without any errors. Check recap. We verified it across multiple test cases, and each time, the output correctly identified the minimum height tree roots. Closing insight. The big lesson? Sometimes, finding the center of a problem means working from the outside in. By trimming layer by layer, we let the structure reveal its own core, efficiently, cleanly, and in linear time.
Breakdown. Assess. Structure. Implement. Check. 5 steps. Way less panic. PatternMastery.com.
Time travel debugging, but for keys. Time-based key value store is a PatternMastery 100 favorite because it blends hash maps with binary search. It's asked at Meta/Amazon to see if you can store version data and pull the value as of a timestamp, fast. Today we'll lock it down with basic and produce clean O-login. Lookups. We must design a class with set key, value, timestamp. Store the value for the key at timestamp. Get key, timestamp. Return the value for the key with the largest timestamp less than or equal to given timestamp. Return if none. Input guarantee. For each key, timestamps in set are non-decreasing. That means we can keep a sorted list per key. Naively scanning backwards at get is on and too slow. Because per key timestamps are sorted, we can binary search the last timestamp not exceeding the query, O-log_n, time. We'll store dict key, list of, timestamp, value, or 2 parallel lists, append on set, and use bisect_write on get. Keep store. Dict str, list tuple int, str. Set, store key, append timestamp, value. Get, binary search that list to find the rightmost pair with t less than or equal to query. If none, return. Let's try to implement it using solution 1. Efficiency overview. Time and space complexity. Big O of log n per get, big O of 1 per set, and big O of n space overall. Concept discussion. We are implementing a time map data structure. The core challenge is efficiently retrieving the correct historical value for a key given a specific timestamp. Since timestamps are always increasing, for each key, we store a sorted list of timestamp and value pairs. The set operation is simple, just appending to this list. The crucial part is the get operation. Since the internal list of timestamps is sorted, we can use binary search to quickly locate the largest timestamp less than or equal to the requested timestamp, ensuring optimal retrieval performance. We begin by defining the time map class and initializing our core data structure, a JavaScript map, which we name store. This map will hold all our data, where the key is the string identifier, and the value will be a list of timestamp and value pairs. Next is our set method. First, we check if the key already exists in our store. If not, we initialize an empty array for that key. Since timestamps are strictly increasing, we simply append the new timestamp and value pair to the array associated with the key. This operation is quick, taking only big O of one time. In the get method, we first handle the case where the key doesn't exist by returning an empty string. If it does exist, we retrieve the array of historical values. We initialize pointers left and right for our binary search, and a result variable to store the found value. This is the core binary search loop. We look for the largest timestamp that is less than or equal to the requested time. If the timestamp at the middle index meets this condition, we update our result to this value, and then move our left pointer up to mid +1 to search for an even larger, yet still valid, timestamp. If the middle timestamp is too large, we discard the right half by setting right to mid -1. Finally, after the binary search completes, result holds the value associated with the largest timestamp less than or equal to the input timestamp, or an empty string if no such entry was found. We return this result. And that's how this algorithm works. It first stores timestamp data efficiently using a hash map, then utilizes binary search to retrieve the correct historical value in logarithmic time. Efficient, simple, and elegant. Now that we've implemented our time map class, let's verify that it behaves correctly with a sequence of operations. This test will show how we can store key value pairs at different timestamps and retrieve the most recent value for a given time. We'll walk through the input operations, see how values are recorded and retrieved, and confirm that the output matches the expected results. Let's test our time map using this input. We perform a sequence of operations. Initialize a time map. Set key foo to bar at timestamp 1. Retrieve the value of foo at timestamps 1 and 3. Set key foo to bar 2 at timestamp 4. Retrieve foo at timestamps 4 and 5. Here's why the solution works. The algorithm stores all values of each key as a list of timestamp value pairs. When get is called, it finds the largest timestamp less than or equal to the requested timestamp using a binary search. Step by step, after set foo, bar, 1, the list for foo is 1, bar. Get foo, 1, returns bar because timestamp 1 exists. Get foo, 3, returns bar because the latest timestamp less than or equal to 3 is 1. Set foo, bar 2, 4, adds the pair, 4, bar 2. Get foo, 4, returns bar 2. And get foo, 5, also returns bar 2 as the most recent value less than or equal to 5. And that is exactly what the program outputs. Null, null, bar, bar, null, bar 2, bar 2, bar 2. This confirms that the code is functioning correctly and passes this test case. So our implementation is correct. The algorithm successfully handles timestamped key value storage and retrieval, efficient, accurate, and reliable. Our implementation is correct. It accurately stores multiple values per key with timestamps. It retrieves the latest value less than or equal to the requested timestamp using binary search. It passes the given test case and is efficient for larger inputs. Let's try to implement it using solution 2. Efficiency overview. Time and space complexity. Big O of n per get, big O of 1 per set, and big O of n space overall. Concept discussion. This approach uses the same core data structure as solution 1, a hash map where keys map to a list of timestamp and value pairs. However, instead of using binary search for retrieval, we opt for a straightforward linear scan. Since the timestamps within the list are always sorted in increasing order, we iterate through the list from beginning to end. We keep updating our result as long as the current entry's timestamp is less than or equal to the query timestamp. Once we find a timestamp that is too large, we stop the search immediately because all subsequent timestamps will also be too large. We start by defining the time map class and initializing our internal map to store key value history. The set function remains identical. We ensure the key exists, and then we append the new timestamp and value pair to the list. This maintains the sorted order necessary for efficient retrieval. Next is the get method. We begin by checking if the key exists in our store. If it does, we retrieve the list of values associated with that key and initialize an empty string result to hold the most recently valid value found so far. This is the core retrieval logic using a linear scan. We iterate through every stored time and value pair. If the stored time is less than or equal to the requested timestamp, we update our result. Because the list is sorted by time, if we encounter a time that is greater than the requested timestamp, we immediately break the loop, as all subsequent entries will also be invalid. This optimization prevents unnecessary checking. Finally, we return the result. This will be the value associated with the largest timestamp that did not exceed the requested query time. And that's how this algorithm works. It first handles storage in constant time, then iterates through the sorted history using a linear scan, stopping early when the requested timestamp is exceeded. Efficient, simple, and elegant. This is the time map, storing values with timestamps. Set saves a value, get retrieves the latest value at or before a timestamp. Like solution 1, we track boundaries, here, timestamps, to get the correct value efficiently. For key foo, timestamp 1 bar, timestamp 4 bar 2, get it 3 returns bar, the latest before 3. Output, null, null, bar, bar, null, bar 2, shows it works. Simple, accurate, and reliable. Breakdown recap. We needed to design a class with two main operations: set, which stores a key value pair with a timestamp, and get, which retrieves the most recent value at or before a given timestamp. If there's no valid timestamp for that key, we simply return an empty string. Assess recap. A naive way would be to scan backward through all stored timestamps each time we call get, but that's too slow. Since timestamps for each key are always added in non-decreasing order, we realized we could use binary search to find the correct version efficiently. That gives us a clean O log n lookup instead of ON. Structure recap. We stored all data in a dictionary that maps each key to a list of pairs, each pair containing a timestamp and its corresponding value. When setting a value, we just append it to that list. When getting, we perform a binary search to locate the rightmost timestamp less than or equal to the query time and return its value. Implement recap. After implementing the class with set and get methods, we ran it on LeetCode, and it executed smoothly without any errors. Check recap. We tested multiple scenarios, overlapping timestamps, missing keys, and boundary cases, and all produced the correct outputs. The main takeaway? Time-based storage problems reward structure and search efficiency. By pairing hash maps with binary search, we built a clean, scalable solution that handles versioned lookups in logarithmic time.
You thought your job was safe until you got that email. Now you're back on LeetCode remembering you forgot everything about trees and graphs. Interviewer says, solve this in O of n. Your brain says, 404, solution not found. Don't be that person. Subscribe to PatternMastery.com and master the coding patterns FANG companies actually test.
You've reached the end of this session. That already puts you ahead of most people. But this was never about finishing 100 problems. It was about spotting the patterns behind them. In a real interview, the next question might look totally new. But it's built from patterns you already know. When that moment comes, memory alone won't help you. You'll rely on recognition, on structure, on the system, basics, and all of it was practiced in JavaScript. Keep pausing. Keep thinking first. Keep finding the patterns before you code. Because the goal isn't just to solve problems, it's to think like someone who can solve anything. That's what being ready really means.